Okay. Good afternoon, everyone, and good afternoon, my dear students. I welcome you all once again to this wonderful channel by Unacademy NEET English. We are back. We are so back finally, and we will resume our today's session from where we left off last time. So, lock in, because this session is giving you everything. But before we move ahead, let me know in the chats if I am audible and visible to each and everyone quickly. Let me know in the chats if I am audible and visible to each and everyone. Let me know. Quick. Am I audible and visible? Let me know in the chats quickly. Okay, I think I'm audible and visible as well. Good afternoon. Good afternoon. So, my dear lovely students, in today's session, we will cover complete class 12th organic chemistry, starting from haloalkanes and haloarenes. Yes, definitely we will start from haloalkanes and haloarenes. So, I would want you all guys to mark the attendance by smashing the like button quickly. And do share the stream with everyone around. And I would also want you guys to be with me till end of this session, because this is very important session. This will be the very important session. Just a moment. So, should we start today's session? Are you guys super excited for today's session? And if you are super excited, show some Josh in the chats quickly so that we will start our today's session. Show some Josh quickly in the chats if you are super excited for today's session. Come on. Come on, my dear lovely students. That is great. That is great. That is great. Yes, I will start from first. Don't worry. I will start haloalkanes once again. Don't worry at all. So without wasting much more time, let's get started, my dear lovely students. And in today's session, we are going to complete, whole organic chemistry of class 12. But before that, let me tell you that I will be sharing handwritten PDF, handwritten notes of, today's session, PDF of handwritten notes of today's session on my Telegram, on my new Telegram channel, I can say. And the ID for that is t.me/KK Sir Chemistry class. So if you have joined already, then it's okay. But if you have not joined yet, join as soon as possible. So join quickly, my dear lovely students. So this is the Telegram channel where I will be sharing handwritten notes or PDF of handwritten notes of today's session. So this is my Telegram channel. It's KK Sir Chemistry class. So you can join this. So let's begin with this chapter, and that chapter is haloalkanes and haloarenes. So let's get started. First is methods of preparation of haloalkanes from alcohols. Listen carefully. This is alcohol. And from this, we have to prepare haloalkane. That means we have to prepare haloalkane. Now, what should we do? We will simply replace this OH group. Have a look. We will simply replace this OH group by, say X. So this is simply replacement reaction. That means this is simply what we call a substitution reaction. But this substitution reaction is, say nucleophilic substitution reaction. So whenever we get haloalkane from alcohols, these types of reactions, these reactions are examples of nucleophilic substitution, or you can say substitution nucleophilic reactions. So these are nucleophilic substitution reactions. Now, first of all, let's take first example or first reaction with the help of which we get haloalkane from alcohols. And that first reaction is a reaction of alcohol with HX. HX is known as hydrogen halide, or we can simply say halogen acid. Have a look. Reaction is like this. A reaction of alcohol with HX. Reaction of alcohol with HX to form RX, that means haloalkane, and water will be lost over here. Have a look. It will be simply like this. But remember, this type of reaction is generally taking place, or this reaction takes place, this type of reaction is generally taking place, or we will simply write down like this, that this reaction generally takes place. This reaction generally takes place via SN1 mechanism. That means this reaction is generally a unimolecular nucleophilic substitution reaction. So this reaction generally takes place via SN1 mechanism. Now, have a look. That means if we are having an alcohol, it first reacts with halogen acid, and what will happen over here? Have a look. First of all, we know this OH group is not a good leaving group, so we can simply say it's a poor leaving group. This lone pair will attack this proton of HX. That means protonation of alcohol will take place in first step. So protonation of alcohol results in the formation of protonated alcohol or oxonium ion formation first. Now, this OH2 with a positive charge is now a good leaving group. What will happen over here? It will be lost. It will be lost in the form of water. That means we will get a carbocation first. So this step is the slowest step, and hence this is the rate determining step of the reaction. So here rearrangement can take place. So we will simply say rearrange it. Rearrange the carbocation. Rearrange the carbocation if possible. What is meant by that? Rearrange the carbocation if possible. That means if after rearrangement it results in the formation of more stable carbocation, then just do this, say shift or rearrangement of this carbocation. Finally, what will happen? Have a look. Finally, my dear lovely students, here X minus, this one, this X minus will act as a nucleophile and it will attack on this carbocation, and this is a very fast step, hence rate independent step, and finally we will get Rx. Now have a look. This OH has been replaced by X, so this is substitution reaction, but this substitution reaction is known as nucleophilic substitution reaction, and this nucleophilic substitution reaction which takes place via formation of carbocation is known as SN1 reaction. So this is basically an SN1 reaction, and generally what is the value of this R? This R is actually either secondary or tertiary. That means secondary alcohols or tertiary alcohols prefer to undergo via SN1 mechanism. That means secondary and tertiary alcohols show this reaction via SN1 mechanism. Have a look. If R is primary, if R is primary alkyl, if R is primary alkyl, that is, at that time ROH is a primary alcohol. Listen carefully. Then primary alcohols actually favor or generally prefer, or I can simply say primary alcohols generally prefer SN2 reaction. That means this reaction, from which we get alkyl halide from alcohols, can be either SN1, it can be either SN2, but generally it is SN1, and this reaction is SN1 when this R is secondary alcohol, say when this alcohol is secondary alcohol or it is tertiary alcohol. But listen carefully, if alcohol is 1 degree alcohol, at that time it prefers to undergo this reaction via SN2 mechanism. That means this reaction generally takes place at that time via SN2 mechanism. But except those primary alcohols which are branched. For example, neopentyl alcohol. We know the structure of neopentyl alcohol is this one. So this neopentyl alcohol does not undergo this reaction via SN2. It prefers reaction via SN1. So this is neopentyl alcohol. So primary alcohols show this reaction via SN2 except those primary alcohols which are branched, or those primary alcohols which can form a stable carbocation. For example, allyl alcohol. For example, this one, allyl alcohol, because it can form a very stable carbocation. If OH is removed, it can form a stable carbocation, resonance stabilized carbocation, or benzyl alcohol. Say for example like this. So these are also 1 degree alcohols. Because OH is attached to 1 degree carbon. They are also 1 degree alcohols. But listen carefully. These prefer reaction via SN1 because they can form stable carbocation. So this is, the point which you have to remember forever. So primary alcohols generally prefer SN2 reaction if this reaction takes place. Secondary and tertiary alcohols undergo this reaction via SN1 mechanism. But there are few primary alcohols which are branched like neopentyl alcohol, or there are few primary alcohols which can form very stable carbocation, resonance stabilized carbocations. Such primary alcohols also undergo this reaction via SN1 mechanism. I hope this is clear to you. Now, after that, my dear lovely students, listen carefully. If R is now primary, and that primary which is not, that primary alcohol which is not a branched primary alcohol like neopentyl alcohol, or not that primary alcohol which can form a very stable carbocation. Now, if R is now a primary which cannot form a very stable carbocation, then it will react with HX via SN2 mechanism. Have a look. Now it will react with this HX via SN2 mechanism. So it will attack, first of all, it will attack this H positive or accept this H positive. So protonated alcohol will be formed first. So first of all, a protonated alcohol will be formed. After that, what will happen? As we know, this R is that primary which is not resonance, which cannot form resonance stabilized carbocation, or which cannot form very stable carbocation. Now, what will happen here? Nucleophile forms a bond with this electron deficient site, and here this bond is broken. That means bond formation and bond breaking takes place simultaneously. This is a concerted step, single step. This is known as what we call SN2 step or SN2 mechanism. So here alkyl halide is obtained from alcohol but via SN2 mechanism. I hope this is clear. After that, you have to remember these points. As reaction generally takes place via SN1 mechanism, that is why among alcohols, my dear lovely students, the decreasing order of reactivity is like this. It is 3-degree alcohol in general, which is more reactive than 2-degree alcohol, which is more reactive than 1-degree alcohol. So this is the decreasing order of reactivity. And remember, this order is on the basis of, stability of carbocation formed in RDS. Have a look. Here, if R is tertiary, it can form a tertiary carbocation. If this is secondary, then it forms a secondary carbocation. If it is primary, it forms a primary carbocation. We know tertiary carbocation in general is more stable than secondary carbocation, which in general is more stable than primary carbocation. As this is rate determining step, rate depends on stability of carbocation. That is why we have written over here that among alcohols, decreasing order of reactivity towards alcohols, among alcohols, reactivity order towards this reaction will be 3-degree, 2-degree, 1-degree, but this order is based on stability of carbocation. Point number one. Point number second. Among halogen acids, decreasing order of reactivity towards this reaction will be simply HI greater than HBr greater than HCl greater than HF. But HF is least reactive, that's why we will not take HF at all. We will remember these three. So can I say among alcohols, the most reactive alcohol is 3-degree, after that 2-degree, after that 1-degree, but actually it depends on, rate of any alcohol depends on stability of the carbocation formed in RDS, and among HX it is HI, then HBr, then HCl. After that, my dear lovely students, let's take reaction of alcohol. Let's take reaction of alcohol with HCl first. Let us discuss reaction of alcohol with HCl first. Have a look. First of all, we know alcohol can be 1-degree alcohol. Alcohol can be 2-degree alcohol. Alcohol can be 3-degree alcohol. So whenever you are having different alcohols, say for example 1-degree alkyl alcohol, 2-degree alkyl alcohol and 3-degree alkyl alcohol. So this is 1-degree example of 1-degree alcohol, simple 1-degree alcohol. This is an example of 2-degree alcohol, a simple 2-degree alcohol, and this is a simple 3-degree alcohol. Now what will happen? Listen carefully. When we react 1-degree alcohol with HCl or 2-degree alcohol with HCl or 3-degree alcohol with HCl, as we know, their reactivity is different. That's why they react with HCl in different, with different rates. Have a look. If we take here anhydrous zinc chloride as well, that means this is a catalyst, but both HCl and zinc chloride, let me write down over here, HCl and zinc chloride together is known as, this mixture is known as Lucas reagent. This is known as Lucas reagent. Listen carefully. And if reaction of alcohol with Lucas reagent takes place, that means if reaction of primary alcohol with Lucas reagent takes place, secondary alcohol with Lucas reagent takes place, and reaction of tertiary alcohol with Lucas reagent takes place at room temperature, what will happen? At room temperature, what will happen? Listen carefully. This primary alcohol is least reactive. It will not react with Lucas reagent at all. It will not react with HCl even in presence of anhydrous zinc chloride. So there will be no reaction. There will be no reaction at room temperature. But when this alcohol reacts with HCl, this is a secondary alcohol, it will undergo via SN1 mechanism. It will first form a carbocation, but in this case there will be no rearrangement. It will first form a carbocation. Once again there will be no rearrangement, and finally what will be the product over here? Product formation will be like this. Product formation will be like this. A secondary alkyl chloride will be obtained. In nutshell, an alkyl chloride is obtained in second reaction. But listen carefully. Secondary alkyl chloride is obtained. Once alkyl chloride is obtained, there will be a white or milkiness or cloudiness that is known as turbidity. That means due to formation of this product, we can simply say turbidity appears. We can simply say turbidity appears due to formation of this. Similarly here, turbidity appears due to formation of this tertiary alkyl chloride. But listen carefully, listen carefully. As we know, this is more reactive, this is less reactive. This will form product very immediately. That means turbidity in this case appears immediately. So turbidity here appears immediately. Turbidity appears immediately. But here, turbidity appears after some time, or you can say after 5 to 10 minutes. Why? Because we know this secondary alcohol is reactive, but it is not that much reactive as tertiary alcohol is. As tertiary alcohol is the most reactive among these alcohols, so it will form product very, very quickly. That means turbidity appears immediately. So listen, whenever primary alcohol is treated with Lucas reagent at room temperature, there will be no reaction. That means no product formation takes place, so no turbidity appears. So no turbidity appears. So can I say now, with the help of this turbidity, we can simply distinguish primary, secondary and tertiary alcohol. For example, if our test tube contains a primary alcohol, secondary alcohol or a tertiary alcohol, but we don't know which one. So how to identify whether the primary alcohol, secondary alcohol or tertiary alcohol is present in a test tube? We will add simply Lucas reagent. If turbidity appears immediately, we will simply say our test tube contains a tertiary alcohol. And if turbidity does not appear first, but after some time turbidity appears, we will simply say test tube contains secondary alcohol. And if turbidity does not appear at all, that means our test tube contains a primary alcohol. So with the help of this Lucas reagent, we can distinguish primary alcohol, secondary alcohol and tertiary alcohol. That test with the help of which we can distinguish primary alcohol, secondary alcohol and tertiary alcohol by using Lucas reagent is known as Lucas test. So my dear lovely students, you should know what is Lucas test. So first of all, you should know what is Lucas test. So Lucas test is simply test to distinguish. Simply it is used, Lucas test is used to distinguish. It's used to distinguish primary, secondary and tertiary alcohols by using Lucas reagent. So with the help of Lucas reagent, when we can distinguish 1 degree, 2 degree, 3 degree alcohols, that test at that time is known as simply Lucas test. So this is point number 1. Point number 2 you should remember is that the reaction, let me write down first of all, Groove's process. This is the another point which you should know. That means this is the reaction during which alcohols react with Lucas reagent to form to form alkyl chloride. So that reaction, with the help of which alkyl chloride is obtained by treating alcohol with Lucas reagent. Point number next is that primary alcohols can show turbidity, upon heating. That means primary alcohols can react with Lucas reagent and can form product. That means primary alcohols can show turbidity upon heating, means primary alcohols can react with what we call Lucas reagent and can form product, but only upon heating, not at room temperature. So I can simply say at that time reaction will be like this, that primary alcohol, this ethanol or ethyl alcohol, can react with Lucas reagent, but not at room temperature, but at high temperature. Let me show this with the help of a triangle. That means temperature should be more than room temperature. At that time, this OH will be replaced by Cl and we will get CH3CH2Cl as the product at that time. Once product is formed, so we will simply say turbidity appears. But it will not appear immediately, but turbidity appears. This is point number 3, what you have to remember. After that, next point you have to remember is that tertiary alcohols can react with HCl even in absence of anhydrous zinc chloride, because tertiary alcohols are very much reactive, so no need of catalyst is there. But this zinc chloride is very, very, very important as per secondary alcohol or primary alcohol is concerned, but primary alcohols can show this reaction, can form primary alkyl halide, but only upon heating. So this zinc chloride is very important for secondary alcohols. Now, I hope this is clear. After that, my dear lovely students, have a look. Once again, have a look. So this is primary, this is secondary, this is tertiary. This can react. It can show turbidity only upon heating, and it can show turbidity even without, it can form the product even without, say anhydrous zinc chloride. So these are the 2 points. And the reaction of alcohol with Lucas reagent to form alkyl chloride is known as Grove's process. But one very, very, very important point is that phenols on treatment with Lucas reagent, cannot, or we can simply say on treatment with Lucas reagent, never show turbidity. Even upon heating. So phenols cannot show turbidity. That means phenol cannot react with Lucas reagent to form aryl halide even upon heating. Because, have a look, because we know phenol is actually like this, OH directly attached to the aromatic ring, and we know this bond is actually not single bond, but it is a partial double bond character. This is having a partial double bond character as a result of resonance. That means this bond is very, very strong. That means this bond is strong. As this bond is strong, it is difficult to cleave. So we cannot cleave CO bond of what we call phenol, because this bond is strong due to partial double bond character as a result of resonance. Hence, it will not show turbidity. It will not form product. So, next point. Appearance of turbidity. Listen carefully, is directly proportional to It is directly proportional to reactivity of alcohol. It is directly proportional to reactivity of alcohols. And reactivity of alcohols is directly proportional to stability of carbocation. Directly proportional to stability of carbocation formed in RDS. Formed in RDS. So you just remember this formula as well. This point as well. So this is all about, when alcohols react with HCl. Now, you have to only remember over here that if alcohol is secondary alcohol or a tertiary alcohol, it will first form a carbocation, and you have to check whether that carbocation undergo rearrangement or not. If it undergoes rearrangement and it increases the stability, of carbocation, then rearrange the carbocation, and after that you have to form alkyl chloride. Second reaction is reaction of alcohol with HBr. Once again, my dear lovely students, if alcohol is tertiary or secondary, reaction with HBr will be SN1 mechanism, and if alcohol is primary, reaction with HBr will be a secondary, that will be an SN2 reaction. So reaction of secondary and tertiary alcohol with HBr will be once again SN1 reaction, and reaction of alcohol with HBr will be an SN2 reaction. Now have a look. If I write down like this, I will write down directly alcohol, and I will treat it with HBr, and reaction takes place in presence of little amount of sulfuric acid. Say for example, it's little amount of sulfuric acid is there, then what will happen? It will simply replace this OH by this Br, and we will get RBr. Now the question is, should we remove this OH and we will simply replace OH by Br? That depends on whether reaction takes place via SN1 or SN2. Now, if this is secondary or tertiary alcohol, first form carbocation. Now check whether rearrangement takes place or not, and accordingly form the product. But if it is primary alcohol, then directly OH replace this, remove this OH by Br, then the product will be this. But have a look, and this is a very important point, that H2SO4, this H2SO4 can be generated. This H2SO4 can be generated in situ. What is meant by that? That means this HBr can be generated within the reaction. How? Have a look. Say for example, you are having an alcohol which is treated with NaBr and H2SO4. Actually, we want reaction of alcohol with HBr, but HBr is not there. But that HBr can be generated within the reaction by these two. Positive part of this, that means H positive, and negative part of this, that means Br negative, will form HBr. So these two will form HBr within the reaction, and there will be Na, a positive part of this and negative part of this, NaHSO4. Among these two, alcohol will react with HBr, that means HBr is generated within this reaction in situ. So HBr will react with OH like this, that means it will form RBr. So these two form these two. Now this will react with this, so it will form RBr plus water. After that, this NaHSO4 remain as it is. So whether a reaction of alcohol with HBr directly takes place, or generally we form this HBr within the reaction, that means in situ, by treating H2SO4 with NaBr or H2SO4 with KBr. Hence KBr, H2SO4, NaBr and H2SO4 will form HBr. That HBr will react with alcohol and it will result in the formation of alkyl bromide. Now tell me, is this clear till now? Am I clear till now, my dear lovely students? Tell me, am I clear till now? Let me know in the chats quickly. Am I clear till now? But whether the reaction takes place via SN1 mechanism or via SN2 mechanism, you have to check whether alcohol is secondary or tertiary. Secondary, tertiary alcohol generally show this reaction via SN1 mechanism, and primary alcohol generally shows this reaction via SN2 mechanism. Now, let me know in the chats, is this reaction clear to you? Is reaction of alcohol with HX clear to you? Okay, that's great. That is great. After that, my dear lovely students, reaction number C. C type reaction is, that means third reaction is a reaction of alcohol. I mean say with HI. So let me write down directly reaction with HI. Reaction with HI. Directly. Reaction with HI. Have a look. Have a look. So it is a reaction of alcohol with HI. When alcohol reacts with HI, as we know, HI is very reactive. So it will react with this and it will result in the formation of alkyl iodide. Now, once again, if this is secondary or tertiary alcohol, reaction is SN1 mechanism. If it is primary alcohol, reaction generally is SN2 reaction. Now, remember once again that HI can also be generated, in situ. Can also be generated in situ. That means within the reaction. How? Have a look. If we treat basically alcohol with, say for example, we will treat it with like this. Here it was NaI or NaBr or KBr. Similarly, this can be NaI or Ki. Say for example, we will treat it with Ki, but here try to remember this. Acid is not H2SO4. Acid should not be H2SO4. Why? Let me tell you that. But first of all, you just remember this. Why? When this H3PO4 and Ki are treated together, they will result in the formation of HI, and that means positive part of this, negative part of this. Now, positive part of this and negative part of this, that means KH2PO4. Now this HI is generated within the reaction. Now it will react with this alcohol and it will result in the formation of Ri plus, I mean to say H2O plus this KH2PO4. I hope this is clear. Now the question is, why we have not taken H2SO4? Have a look. Have a look. Have a look. If we take H2SO4, what will happen? If we take H2SO4, what will happen? Listen carefully. It will first result in the formation of HI and then KHSO4. But once HI is obtained, we know HI is a reducing agent and H2SO4 is a strong oxidizing agent. So when strong oxidizing and strong reducing agents are together, then what will happen? Have a look. Have a look. This HI is simply oxidized to iodine because this is a strong oxidizing agent, and this H2SO4 is reduced to SO2 because this is a strong reducing agent. I hope this is clear. Now listen carefully. Listen carefully. It's iodine and it is SO2. Now how many hydrogens are there? 2 and 2, 4 hydrogens are there and 2 oxygen is there. So I can write down twice H2. So this will be oxidized with the help of this and this will be reduced with the help of this. In nutshell, there will be no HI produced during the reaction. So if we take H2SO4, HI formed gets converted to iodine. That means there will be no HI formation at all. That's why we take that acid, which is not oxidizing agent, which is not an oxidizing acid. So this is not an oxidizing agent. It cannot, oxidize this HI. That's why we will take H3PO4. I hope this is clear. I hope this is clear. Is this clear? Is this clear? Let me know in the chats quickly. Am I clear till now? So this was all about reaction of alcohol with HX. Is this clear? Let me know in the chats quickly. Let me know in the chats quickly, my dear lovely students. Quick. Let me know quickly. Is this clear? Is this clear? Okay, that's great. Now, next reaction is, just a moment. So next reaction is reaction of alcohol with PCl5. Now, listen carefully. Whenever you are having alcohol and it is treated with PCl5, what will be the product? What will be the product? What will be the product? For that, you can remember this reaction in this fashion. This is ROH. You can remember it like this. This is Cl, this is PCl3, and then it is Cl. This is in total PCl5. Now, have a look. Have a look, have a look. These will form RCl, then next will form POCl3, and next will form simply HCl. Next will form HCl. So, three products will be formed. RCl, let me write over here. RCl, POCl3, phosphorus oxychloride, and HCl. And this reaction generally takes place via SN2 mechanism. So this is basically the product which is formed via SN2 mechanism. That means you have to remove OH by a nucleophile, which is Cl over here. So this is reaction of alcohol with PCl5. After that, the reaction of alcohol with PX3. That means what will happen over here? Whenever you are having alcohol and you are having PX3, what will happen? What will be the product over here? Listen carefully, listen carefully. We can write down same reaction like this. We can write down alcohol 3 times so that we can balance the reaction. Have a look. Alcohol. Then we will write down P, then X, X and X. Simple trick like this. We will form simply H3PO3. We will form H3PO3 like this. We will form H3PO3 like this. So this is H, H, H. This is P, O, O, O. That means H3PO3. And then this R will form bond with X. R will form bond with X. R will form bond with X. In nutshell, what happened over here? We have to replace this OH by X. That means once again SN2 reaction is this. Normal SN2 replace OH by nucleophile, which is X over here. And after that, H3PO3 is formed. H3PO3 is formed. But if we want to balance the reaction, alcohol is thrice, so write down 3 times. If this is 3 times, then it is 3 times because RX, RX, RX. I hope this is clear. Now, this reaction can be like this, simply ROH plus PCl3. Then, what will be the product? Very, very, very simple. What will be the product? Replace OH by nucleophile. Nucleophile is Cl. So, we will get simply RCl plus H3PO3. Or you can balance the reaction like this 3 times and 3 times. Similarly, if you take ROH plus PBr3, then what will be the product? Product will be simply RBr and H3PO3. You can balance the reaction as well. Similarly, if you want, you can take PI3. Then what will be the product? Product will be simply replace OH by I. So Ri, H3PO3. But very, very important point is this, that generally this PBr3 and PI3 are generated in situ. That means they are generally not taken directly, they are prepared, we should prepare that, they are generated within the reaction. That means in situ. Now, how will we prepare PBr3 or PI3? It's very, very simple. Whenever you are having, listen carefully, whenever you are having bromine plus red phosphorus, or I can simply say bromine and phosphorus, or you can simply say bromine and P4, whenever you saw these three, whether it is bromine and bromine and red phosphorus, whether it is bromine and phosphorus, whether it is bromine and P4, remember it means PBr3. That means PBr3 can be generated with the help of phosphorus and bromine. Similarly, if it is iodine and red phosphorus, whenever you saw iodine and red phosphorus, or you saw iodine and phosphorus, or you saw iodine and P4, you should remember at that time it means PI3. That means with the help of these two, PI3 can be generated. Which means if I write down like this, if I write down a reaction like this, if I write down a reaction, say for example like this, and I will write down iodine red phosphorus over here. What does that mean, iodine and red phosphorus? That means it is PI3. So it is a reaction of alcohol and PI3 actually, because these two will form PI3. So it is simply a reaction of alcohol with PI3. So PI3 is generated from these two. So I will erase this one. So PI3 is generated from these two. So reaction will be simply SN2 reaction and OH will be replaced by amines AI. This is very, very simple reaction. And we know H3PO3 will be the side product. Now, I hope this is clear to you. Similarly, if reaction is like this, CH3, CH3, OH, that means a secondary alcohol is there. And if iodine red phosphorus is there, that clearly means that these two will form basically PI3 within the reaction, and that PI3 will react with this, and the main product or the alkyl halide formed will be alkyl iodide like this. Similarly, if it is a tertiary alcohol, my dear lovely students, whenever you saw alcohol as well as iodine phosphorus or bromine red phosphorus like that, replace OH by iodine or bromine depending upon if it is iodine red phosphorus, then replace OH by iodine. If it is bromine red phosphorus, replace OH by bromine. So the product or the main product of this reaction will be like this. Main product will be like this. It's very, very, very simple. After that, reaction with thionyl chloride. SOCl2 means thionyl chloride. SOCl2 means thionyl chloride. Remember, reaction of alcohol with thionyl chloride is known as Darzens procedure. This reaction is known as basically Darzens procedure. So whenever you are having an alcohol and it is treated with SOCl2, I mean say thionyl chloride, what will happen? You have to remember a reaction in this fashion simply. It's ROH, then it is Cl, and then it is SO, then it is Cl. So simply you just form RCl, SO2 and HCl from this. That means you will simply form RCl, SO2, this is a gas, it will evolve, and HCl. This is also a gaseous product, it will also evolve. Now listen carefully. This reaction can take place either in absence of, I mean say pyridine, or in presence of pyridine. Say for example, this is pyridine, and in absence of pyridine, same reaction will take place. I mean say product will be same, but there will be only difference in, what will be that difference? Have a look. Product will be same once again. Sulfur dioxide gas will be evolved, HCl gas will be evolved, but the only difference is this reaction in presence of pyridine, product will be formed via SN2 mechanism. That means here inversion will take place. But this takes place via SNI mechanism, which is not in your syllabus, but you should remember only one thing, that here product will be formed, but there will be no inversion, there will be retention. For example, I will give you one simple example. For example, this OH is attached to a chiral center whose configuration is R. Say for example, if OH is attached to a chiral center, suppose, and that configuration of that chiral center is suppose R, then what will be the configuration of this chiral center in the final product to which Cl is attached? It will be once again R. But what will happen over here? If configuration of the chiral center to which OH is attached is R, now that chiral center whose configuration was R, in the final product, the configuration of chiral center to which Cl is now attached will be S. That means here R changes to S or S changes to R, but R changes to S, S changes to R only if reaction takes place at chiral center. Here R remains as R, S remains as S if reaction takes place at chiral center. Or we can simply say here inversion takes place inside out. I mean say this molecule will turn inside out, but this molecule will remain as such. There will be retention, there will be inversion. One more point. Have a look. One more point. We can prepare alkyl chloride from alcohol on treatment with HCl. Number one. We can also prepare this alkyl chloride from alcohol by treating it with PCl5. We can also prepare, say this alkyl chloride from alcohol by treating it with PCl3. We can also prepare this alkyl chloride from alcohol by treating with thionyl chloride. And remember, this method is considered as best method, to prepare alkyl chloride from alcohols. So we can prepare alkyl chloride from alcohol by treating with HCl, with PCl5, with PCl3, with SOCl2. But this reaction of alcohol with SOCl2 to form RCl is considered as best method to prepare RCl from alcohol, because here side products are gases. Once they form, they will evolve and we will get RCl in the, pure form. So this is considered as best method. After that, next preparation is from hydrocarbons. That first reaction is from alkanes by, this is from alkanes, and this reaction is basically a free radical reaction. So I can simply say from alkanes by free radical halogenation. Now, what is this reaction? Have a look. We have already completed this reaction in class 11th chemistry, but let me show you once again. That means if we are having an alkane and this alkane on treatment with halogen, in presence of either light or in presence of high temperature, now what will happen? This reaction will simply be like this. H will be replaced by X and we will get alkyl halide over here. And this reaction is an example of free radical substitution reaction. This reaction is an example of free radical substitution reaction. And next point, among halogens, reactivity order towards this reaction is F2, very reactive than Cl2, reactive than Br2, and reactive than, I2. So this is the reactivity order. You should know this. Among halogens towards this reaction, which is a free radical substitution reaction, that means which is a free radical reaction. Intermediate of this reaction obviously will be a free radical. And among hydrogens, what will be the reactivity order towards this reaction? Towards free radical reaction, it will be simply 3 degree hydrogen, and it is more reactive than 2 degree hydrogen, is more reactive than 1 degree hydrogen. You should also know this. After that, my dear lovely students, listen carefully. After that, we will simply say that as this reaction is a free radical reaction, the mechanism taking place during this reaction is like this. First step is initiation step. So first step is initiation step, and in initiation step, what will happen? My dear lovely students? First of all, radicals will be formed in our reagent. Radicals will be obtained in our reagent. So first of all, with the help of light or high temperature, radicals will be obtained. Once radicals will be obtained, then these radicals will attack substrate, and that step is known as propagation. That is known as propagation or chain propagation step. And first chain propagation step is that these radicals which are formed from reagent will attack substrate. And form, radicals over here. Homolytic fission will take place. So this H is more reactive as compared to R radical, will react with this X, and it will result in the formation of what we call R radical plus HX. In second step, In second step, this R radical formed will react further with say R reagent, and it will react in such a way that first it will form X radical, then X radical will react with this R and it will form our product. So product is formed in say generally propagation step, and all the propagation steps must be exothermic in nature. After that, step third is termination. Because product is formed, we don't want reaction to proceed more. Now, we will simply try to stop this reaction, and that is termination. What will happen in termination? All these types of radicals which are formed in propagation will react together. That means R radical will react with R radical, and it will result in the formation of RR. Simply, X radical will react with X radical, and because two types of radicals are formed, and it will result in the formation of X2. Similarly, R radical can react with X radical and it can form Rx. That means product can also be formed in this, but generally product is formed during say propagation step. Now, so this is the mechanism. If this is the mechanism, then what will happen? What will happen during chlorination? What will happen during chlorination of alkane? Have a look. So first of all, it's chlorination of alkane. What will happen during chlorination of alkane? Have a look. Listen carefully. Listen carefully. Now, actually, if we take methane and chlorination of methane takes place in presence of light or heat, what will happen? This Cl will simply replace H. Cl will simply replace H. So we will get CH3Cl plus HCl first. Then, if chlorine is taken in excess, then this CH3Cl can further react with chlorine. But if chlorine is taken in excess under similar conditions, and it will replace one more hydrogen. So it will form CH2Cl plus HCl. Then this CH2Cl will further react with Cl2 under similar conditions, and it will form CHCl3 plus HCl. Finally, this CHCl3 can further react with Cl2, and it will result in the formation of CCl4. Now listen carefully, listen carefully. So can I say, actually whenever methane is taken with chlorine and chlorine is taken in excess, chlorine is taken in excess under similar conditions, that means in presence of light or heat, it can be a polyhalogenation reaction actually. That means first it forms CH3Cl, then it forms CH2Cl2, then it forms CHCl3, and finally all the hydrogens of alkane will be replaced by halogen. So major product at that time will be CCl4. But if methane is taken in excess, then major product will be this. So let me write down over here. If CH4 is taken in excess in this example, not chlorine. If CH4 is taken in excess, at that time, remember, it is this CH3Cl which will be the major product. At that time, CH3Cl will be the major product. I hope this is clear. I hope this is clear. After that, remember, the number of monochloro derivatives or products, number of monochloro derivatives, or you can say number of monochloro products, derivatives formed from an alkane during chlorination. It will be simply equivalent to number of different types of hydrogens, number of different types of hydrogens present in an alkane, So listen carefully. What is meant by this? That means we know methane is having only one type of hydrogen. We know ethane is having only one type of hydrogen. So if this is a type of hydrogen, this is also a type of hydrogen. Similarly, we know propane is having two types of hydrogens. These two are similar and this is different. Similarly, butane is also having two types of hydrogens. These two are similar and these two are similar. Similarly, if we talk about 2-methyl propane, 2-methyl butane, this is having one, say type of hydrogen, this is having another type, this is having another type, this is having another type. That means this is having 4 different types of hydrogens. Similarly, if we talk about this one, 2,2-dimethyl propane. So this is having only one type of hydrogen. Only one type of hydrogen. So it can form only one monochloro product. How? Replace only one hydrogen by Cl. Any one hydrogen, because all are similar types. Here you can replace either A or B by Cl. You can replace A or B. That means it will give 2 products. It will give 2 products. It will give, it will give 1 product. It will give 1 product. It will give 4 products. But number of products formed over here is excluding stereoisomers. Excluding stereoisomers. So remember this. Similarly, if you are having a cyclopentane, it's also having only one type of hydrogen extra. So these all can form number of monochloro products depending upon different types of hydrogens, but this formula is applicable excluding stereoisomers. But if question is including stereoisomers, then you have to first form these all products. After that, you have to check how many stereoisomers are present. For example, let me show you. For example, if you are having this one, we know this is having 4 different types of hydrogens. Now we can simply replace all these 4 hydrogens one by one by means of chlorine. Say for example, reaction takes place in presence of light, in presence of heat. So you can replace H of A, then product will be like this. Monochloro means only one hydrogen you have to replace. Only one hydrogen you have to replace. So this is product, what we call A. Similarly, if you want to replace this B hydrogen, then what will be the product? Product will be like this: CH3, then C, Cl, then CH3, then CH2, then CH3. So this is product B. If you want to replace C, then what will be the product? C hydrogen. If you want to replace C hydrogen, product will be like this. And if you want to replace D hydrogen, product will be like this. Product will be like this. I hope this is clear. So this is C product, this is D product. So how many products are formed excluding stereoisomers? Excluding stereoisomers, there are 4 products. But my dear lovely students, including stereoisomer, we know this is the chiral center, this is the chiral center. If this is chiral center, that means it's having 2 isomers. One is this, another is its enantiomer. That means including stereoisomers, there will be 6 products. How? One this, another its isomer, enantiomer. That means 2. This is 3. Then this is 4, its enantiomer is 5, and this one is 6. In total, there are 6 products. I hope this is clear. And listen, one more thing. During this reaction, this is the major product. How we can calculate that this is the major product? It's very, very simple. With the help of this one. 3-degree hydrogen is more reactive than 2-degree hydrogen, is more reactive than 1-degree hydrogen, we know that. But with respect to chlorine, this is 5 times more reactive than 1-degree hydrogen. And 2-degree hydrogen is 3.8 times more reactive than 1-degree hydrogen. This reactivity order is with respect to chlorine. Now, have a look. How many type A hydrogens are present in this alkane? 3 and 3, 6. So can I write down over here? Type A hydrogen are 6 in number. Type B hydrogen in this alkane, have a look. In this alkane is only 1 in number. It's 1 in number. Type C hydrogen in this case, Type C hydrogens are 2 in number, so I will write down 2. And type D hydrogens are 3 in number. But type A hydrogen is a primary hydrogen. It's a primary hydrogen. This one, have a look. It's a primary hydrogen because attached to primary carbon. This is a tertiary carbon. So hydrogen will be tertiary hydrogen. So let me write down tertiary hydrogen. This is a secondary hydrogen. This is a 1 degree hydrogen. And reactivity of 1 degree hydrogen is 1, 3 degree hydrogen it is 5, 2 degree hydrogen it is 3.8, and 1 degree hydrogen it is 1. But this is the reactivity of 1 degree hydrogen, 1 3 degree hydrogen, 1 2 degree hydrogen, and 1 degree hydrogen. But how many 1 degree hydrogens are there? 6. So I will multiply it by 6. I will multiply it by 1. I will multiply it by 2. I will multiply it by 3. So total reactivity of 1 degree hydrogens, which are 6 in number, that means of type A hydrogen, is 6. And total reactivity of type B hydrogen, which is tertiary, are 5. Total reactivity of this type C hydrogens, which are secondary hydrogens, are 7.6. And of this is 3. In total reactivity of A, B, C, D hydrogens is 21.6. So if you want to calculate percentage of this, it is simply 6 divided by 21.6 multiplied by 100. So you will get the percentage. You can calculate the percentage. Here it is 5 divided by 21.6 multiplied by 100. You will get the percentage over here. Here it will be 7.6 divided by 21.6 multiplied by 100. So you will get the percentage. Similarly, it is 3 divided by 21.6 multiplied by 100. You will get the percentage over here. And you will see, when you simply solve these questions, you will see this will become in highest percentage. That means this will become the major product. That means if C hydrogen is replaced by Cl, if C product is replaced by Cl, that will become the major product. But listen carefully. If we replace 1 degree hydrogen, first it will form a 1 degree, say radical. 3 degree hydrogen, if we remove 3 degree hydrogen, it will form a 3 degree radical. That means this product is formed by replacing 1 degree hydrogen. That means its intermediate is 1 degree radical. Its intermediate is, as it is formed from 3 degree radical, so intermediate is 3 degree radical. Here we have simply removed 2 degree hydrogen, so it is formed from 2 degree carbon free radical, and it is formed from 1 degree carbon free radical. Listen carefully. We know stability. We know stability of carbon free radical in general. Stability of carbon free radical in general is like this. It is 3 degree, 2 degree, and 1 degree. That means product which is formed from 3 degree carbon radical, that means most stable carbon radical, should be the major product. If that happens, that major product is formed from most stable carbon free radical, at that time reaction is known as selective reaction. The reaction is known as selective reaction. But here, have a look. If this is an example, this major product has been formed from 2 degree radical. This has been formed from 3 degree radical. Most stable radical from which product has been obtained is this one. B is formed from most stable carbon free radical. But this is not major. So that is why chlorination is not selective. It's non-selective reaction. Because selective reaction is that during which major product will be always that product which is formed from most stable carbon free radical. That means if a reaction is such that this radical which is formed from this product which is formed from most stable carbon free radical is major product, then we call that reaction as what we call selective reaction. But chlorination sometimes is selective, sometimes it's non-selective. In nutshell, you should remember this one. That chlorination is non-selective reaction. Chlorination reaction is a non-selective reaction. What is meant by that? That means during chlorination of alkane, major product can be formed from more stable carbon free radical, or it can be formed from less stable carbon free radical. That all depends on this one. That all depends on this. You have to calculate, So I hope this is clear. So this was all about chlorination. Now, second is bromination of alkane. Second is bromination of alkane. Second reaction is bromination of alkane. But here you have to remember that this reaction is taking place in similar manner as that of chlorination. That means this reaction takes place in similar manner as that of chlorination. That means, have a look. That means this reaction is an example of free radical. Chlorination, bromination, iodination, fluorination. In all these reactions, 3-degree hydrogen will be more reactive than 2-degree, more reactive than 1-degree. This is what we call mechanism. That means mechanism will be once again same as that of chlorination or bromination. But here, this was chlorination. Now, bromination will take place in similar manner. Means, if we replace this Cl2 by Br2, same products will be obtained, but instead of Cl, there will be Br. I hope this is clear. Similarly, this is same once again as per bromine is concerned. Once again, this formula will be same. Once again, all things will be same. I hope this is clear. But the only difference is here, major product will be formed from, that major product among this is this one. That means, which is formed from most stable carbon free radical. What does that mean? That means the only difference between chlorination and bromination is, point number one, that bromination is more selective than chlorination. It's more selective than chlorination. I hope this is clear. That means major product during bromination of alkane will be always from that carbon free radical which is most stable carbon free radical. That means if same reaction takes place, instead of Cl2, it will be Br2. This will become the this will become the major product because it is formed from more stable carbon free radical, which is a tertiary carbon free radical. I hope this is clear. Another thing which you have to remember is that among 3-degree hydrogen, 2-degree hydrogen and 1-degree hydrogen, more reactive is once again 3-degree hydrogen, but reactivity with respect to bromine will be like this. It is 1600 times more reactive. 3-degree hydrogen is 1600 times more reactive as per bromination is concerned as compared to 1-degree hydrogen. Similarly, 2-degree hydrogen is 82 times more reactive than 1-degree hydrogen. I hope this is clear. After that, my dear lovely students, next is fluorination. Of alkane. Fluorination of alkane. Remember only one point, that direct fluorination is not possible because fluorination is too violent. So remember, direct fluorination of alkane is not possible. It is not possible because reaction is too violent to be controlled. Reaction is very, very violent, very, very explosive. Reaction is very highly exothermic. So that's why it's uncontrolled and explosive one. After that, we will be having iodination of alkane. And listen carefully. Direct iodination of alkane is not possible. Remember, if we want direct iodination, that means if we want to prepare, say for example, methyl iodide from from this methane by treating it with iodine, reaction is not possible because reaction is reversible. So direct iodination is once again not possible because reaction is reversible due to formation of this one, because it acts as a strong reducing agent. And it converts, once it's formed, it converts this alkyl iodide back to alkane. So if we want to prepare alkyl iodide from alkane, Hi should be removed, and it is possible only and only. That means direct iodination is possible so that reaction becomes irreversible. It is possible only It is possible only in presence of strong oxidizing agents like HNO3, like HGO, or HiO3, or sometimes HiO4 is also there. So in presence of these, Hi will be removed. So there will be no, reaction which is reversible at that time, because once Hi is replaced, Hi is removed. So when Hi is removed with the help of this, so Hi will be not there. So reaction will be not a reversible one. It will be an irreversible one. So direct iodination is not possible unless and until we use these. If we use this, then direct iodination is possible. I hope this is clear. I hope this is clear. Now, another is from alkenes by addition of HX. By addition of HX. Remember, first of all, this reaction is an example of electrophilic addition reaction. You should remember this, that this reaction is an example of electrophilic addition reaction. After that, the intermediate over here, intermediate of this reaction is a carbocation, or you can simply say a classical carbocation. That means that carbocation which is having positive charge fully developed on carbon. So rearrangement can be possible. So therefore rearrangement can be possible. Whenever classical carbocation is there, so rearrangement can be possible. So rearrangement can be possible. Rearrangement can be possible. Listen carefully. If you are having an alkene like this, say for example, and you are having HX, then what will happen? What will happen? Listen, what will happen? First of all, addition of proton to alkene takes place. Addition of proton to alkene takes place, and it will result in the formation of either this carbocation. If H positive is added to this, carbocation will be this, or it can form this carbocation. Both carbocations can be possible, but remember, this is more stable. More stable, and this is less stable. Have a look, only 2 alpha hydrogens here, 3 alpha hydrogens are there, and if we don't know the value of R, if R is also CH3, then 6 alpha hydrogens, and this is having only 2 alpha hydrogens. So I mean to say, this is more stable because of hyperconjugation and inductive effect as compared to this one. Now, after that, remember, you have to rearrange them. Rearrange if possible. Rearrange if possible. So if after rearrangement carbocation becomes more stable, then rearrange this. And this step is formation of carbocation is slowest step. Hence this is the rate determining step of the reaction. After that, have a look. After this, what will happen? After this X minus will attack, and it will act as a nucleophile, and this is the fast step. It will attack on this carbocation or this carbocation. That means we can form products like this over here. But the product which is formed from more stable carbocation is this one, will be always major product. So our focus should be on major product now, not on minor. But sometimes question can be asked, how many possible products are how many products are possible? Or question will be like this, can this be formed during this reaction? Yes, this can be formed, but as minor product, we have to, focus now on this major product. So this is the major product of the reaction. So this is the mechanism of the reaction. This is the mechanism of the reaction. Now, during this reaction, HX is used and alkenes are used. So remember this point. Among HX, what will be the reactivity order towards this reaction? It will be HI, then it will be HBr, then it will be HCl, then at the end it will be HF. And among alkenes, reactivity order will be simply like this. Rate of reactivity of alkenes is directly proportional to stability of carbocation formed in RDS. So those alkenes which can form more stable carbocation in alkenes, which can form more stable carbocation in RDS, will show this reaction much faster as compared to that alkene which forms less stable carbocation in RDS. I hope this is clear. So the alkene, which forms more stable carbocation, will show this reaction faster, and alkene, which forms less stable carbocation, shows obviously this reaction slowly. I hope this is clear. After that, have a look. Remember this thing. Whenever HX is added, to unsymmetrical alkene, it generally takes place via, or generally takes place according to Markovnikov's rule. So first thing is clear that Markovnikov's rule is applicable. If reagent is HX, that means if reagent is unsymmetrical and substrate is also unsymmetrical. So whenever substrate is unsymmetrical, reagent is unsymmetrical, addition of reagent to substrate takes place according to a rule. That rule is known as Markovnikov's rule. So Markovnikov's rule. What is this rule? It states, what is the statement of this? Whenever unsymmetrical reagent is added to unsymmetrical substrate, negative part, listen carefully, negative part of addendum means molecule to be added. And we know our molecule which we have to add is reagent. That's why I will write down or reagent, and our reagent is HX. For this reaction it is HX. So negative part of HX goes to that carbon-carbon double bond, which contains lesser number of hydrogens, So that carbon-carbon double bond which is having lesser hydrogens, we have to add negative part of HX, negative part of unsymmetrical reagent, negative part of addendum. That means we have to add X minus, for example, like this. If you are having an alkene like this, then what will be the major product over here? Major product will be according to Markovnikov's rule, according to the statement of Markovnikov. What is that? First of all, H positive will be added. We have to form more stable carbocation. Carbocation will be like this. Have a look. It will be like this. Mechanism will be like this. This is the slowest step of the reaction. This will be the rate determining step of the reaction. So we have to form the major product. So I will form this carbocation only. But we have to check whether this carbocation undergoes rearrangement or not. We know this will not undergo rearrangement. Finally, what will happen? X minus will attack on this, and we will get this as the major product. This will be the major product of this reaction. So this will be the major product of this reaction. So look towards this reaction. Can I say negative part of this addendum, that means X minus, goes to that carbon-carbon double bond. That means this one which is having lesser number, carbon-carbon double bond among these two, having lesser number of hydrogen is this. That means X minus goes to this. Double bond is, change this double bond to single bond, then X minus goes to this and positive part goes to this. That means this will be the product. So can I say this product is what we call a Markovnikov's product. So Markovnikov's rule states that whenever unsymmetrical reagent is added to unsymmetrical substrate, at that time negative part is added to that carbon-carbon double bond which is having lesser number of hydrogens. So you have to add, unsymmetrical reagent to unsymmetrical substrate according to Markovnikov's rule. But there are few exceptions. There are, exceptions to Markovnikov's rule. That means the major product is not always according to Markovnikov's rule. That's why this is the exception. Exception to Markovnikov's rule. When Markovnikov's rule is not forming the major product. Point number 1 is if rearrangement takes place. If rearrangement takes place. If rearrangement takes place during reaction. Number 1. And number second point. If electron withdrawing group is attached to carbon-carbon double bond. Now, let's take these examples one by one. Have a look. For example, you are having example number 1 like this. CH3C, CH3, CH3, single bond CH, double bond CH2. And this is an unsymmetrical substrate. And you want to add this unsymmetrical reagent. According to Markovnikov's rule, this negative part should go to this. And this H should go to this. And that should be the major product. But here, what will happen? Have a look. What will happen? Have a look. Major product is always formed from more stable carbocation. So first of all, we will form more stable carbocation. And more stable carbocation first formed will be like this. It will be like this. It will be like this. That means H positive goes to this one and then carbocation forms. X minus will leave. This is the slowest step, rate determining step of the reaction. But now what will happen? We know here this methyl with electron will shift or this methyl will shift. That means it is 1,2 methyl carbanion shift. Now, after 1,2 methyl carbanion shift, what will happen? A new carbocation will be obtained which is more stable than this one. That's why this shift is possible, rearrangement is possible. Have a look. This carbocation was stabilized by 3 alpha hydrogens as per hyperconjugation is concerned and inductive effect. But this carbocation is stabilized by 7 alpha hydrogen as per hyperconjugation is concerned as well as inductive effect. So this is more stable as compared to that. So major product is always formed for more stable carbocation. So this is the most stable carbocation of this substrate. Hence, this will be first formed. After that, negative part will attack this X minus will attack this carbocation. Then the major product of this reaction is like this. So this is the major product. But this is the major product of the reaction. Now tell me. According to the statement of Markovnikov's rule, X minus should go to this. X minus should go to this carbon, but X minus goes to this. That means this is not according to Markovnikov's statement. That is why this is known as a rearranged product because this has been formed after rearrangement. So rearranged product is formed as the major product. It is not the Markovnikov's product. Or we can simply say that this product was not expected as per statement of Markovnikov's rule as per statement of Markovnikov's rule is concerned, this was not expected as the major product. Hence, we can simply say this is an unexpected product. Unexpected product according to the statement of Markovnikov's rule. So this is not according to the Markovnikov's rule. That product should be like this, X should go to this. So X can go to this, but that will not be the major product. Markovnikov's product here will be not the major product. So remember, Markovnikov's product is not always the major product. Major product is always that product which is formed from most stable carbocation. So this is exception to what we call Markovnikov's statement. After that, second is, if electron withdrawing group is attached, say for example, nitro group is attached to CH double bond CH2. Now, what will happen? First of all, addition takes place always so that it can form a more stable carbocation. So it will attack H positive, X minus will be lost. This is the slowest step, rate determining step. And we know if H goes to this, carbocation is formed over here and that carbocation will be destabilized because of electron withdrawing group. So we will simply form more stable carbocation like this because this is more stable carbocation as compared to if we form carbocation over here, because this is electron withdrawing. Whenever electron withdrawing group is directly attached to carbocation, it destabilizes that carbocation. So this is more stable carbocation of this reaction. There will be no rearrangement. Finally, X minus will attack. it will act as a nucleophile, a very fast attack. Then product will be, major product of this reaction will be this. So this is the major product of the reaction. But this is also not according to Morkonikoff's rule, because according to Morkonikoff's rule, X should go to this carbon. But this is not according to Morkonikoff's rule. I hope this is clear. I hope this is clear. Let me know in the chats, is this clear? Let me know in the chats, is this clear? Please quickly let me know in the chats, is this clear? Is this clear, my dear lovely students? Quick. Okay, that's great. That is great. That is great. Now, after this, listen carefully. Listen carefully. Listen carefully. Listen carefully. So here, now it is clear. It is clear now that whenever you are having an unsymmetrical reagent, unsymmetrical substrate, generally Morkonikoff's product will be the major product, except if rearrangement takes place or if there is an electron withdrawing group attached to carbon-carbon double bond. That means, now, if we are having few examples like this, if you are having CH3CH double bond CH2, and then you want to add HF, you want to add HF to this, or this is reaction number 1, you want to add, say for example, HCl to this. This is reaction number 2. Listen carefully. You want to add HBr to this. That means these are HX values. I mean say changing value of HX in different reactions. 4th reaction is CH3CH double bond CH2 plus HI. Now what will happen? What will happen? Now listen carefully. When you have already seen this reaction, have a look. Look towards this reaction. This is propene. Whenever HX is added to it, it forms a carbocation, but there will be no rearrangement. So propene, in case of propene, carbocation is formed, but there is no rearrangement. When there is no rearrangement, addition should be according to Morkonikoff's rule. So what will be the product of first reaction? Product of first reaction will be simply CH3CHF and then CH3. That means negative part should go to that carbon-carbon double bond, which forms more stable carbocation. I mean say that carbon-carbon double bond, which is having lesser number of hydrogens, and this lesser number of hydrogen obviously forms more stable carbocation. Or here, negative part of this HX goes to that carbon-carbon double bond, which is having lesser number of hydrogens. Similarly, it will be like this. Have a look. Similarly, it will be like this. And all these products are Morkonikoff's products, because these products are formed as major products according to Morkonikoff's rule. All are Morkonikoff's products. And all these reactions are electrophilic addition reactions. These all reactions are electrophilic addition reactions. And in all these 4 reactions, what is the intermediate? Intermediate here is the carbocation, classical carbocation. I hope this is clear. Now, if same reactions are repeated, but now I will write down, listen carefully, I will write down now peroxide over here, peroxide over here. Now in 6th example, once again it is propene, an unsymmetrical alkene, and HCl, that means an unsymmetrical reagent, in presence of this peroxide. What will happen now? Similarly, CH3 single bond CH double bond CH2 plus HBr in presence of peroxide. Listen carefully. After that, CH3CH double bond CH2 HI in presence of peroxide. Now listen my dear lovely students. Except this reaction number 7, product will be once again according to Morkonikoff's rule. product will be once again according to Markovnikov's rule. What does that mean? That means whenever we add HF, HCl or HI in presence or absence of peroxide, in presence or absence of peroxide, product, major product will be always Markovnikov's product. Major product in these reactions will be Markovnikov's product. That means this is a Markovnikov's product. This is a Markovnikov's product. This is a Markovnikov's product. And this reaction is once again an electrophilic addition reaction. This reaction is once again an electrophilic addition reaction. This reaction is once again an electrophilic addition. Can I say all these 8 reactions except reaction number 7, they are electrophilic substitution, electrophilic addition reactions, and intermediate in these reactions is carbocation, and the product formation will be always, major product will be always according to Markovnikov's statement. That means Markovnikov's product. But whenever there are 3 things, peroxide, HBr and unsymmetrical alkene. Remember, unsymmetrical alkene, HBr and peroxide, this reaction is not electrophilic addition reaction. This is free radical addition reaction, and product here is anti-Markovnikov's product. Product here is anti-Markovnikov's product, and intermediate of this reaction is carbon free radical. So listen carefully, whenever you are having unsymmetrical alkene, HBr and in presence of peroxide, 3 things are there: unsymmetrical alkene, HBr, peroxide. At that time product is anti-Markovnikov's product, intermediate is carbon free radical, and reaction is free radical addition reaction. I hope this is clear to you. I hope this is clear to you. And this reaction is known as reaction 7. Reaction 7, example of reaction 7 is simply a peroxide effect. We can simply call it as peroxide effect, or we can call it as Khursheed's effect. This is peroxide effect or Khursheed's effect. And in this reaction, let me show you once again reaction 7. And in this reaction there are 3 things: unsymmetrical alkene, HBr and peroxide. Whenever these 3 things are there, product should be anti-Markovnikov's product, and that product is simply taking place via formation of carbon free radical, and reaction is free radical addition reaction. I hope this is clear to you. After that, there is another reaction, that is addition of halogen. Addition of halogen. Listen carefully. This reaction is once again electrophilic addition reaction, but intermediate over here, here is a cyclic halonium ion. Intermediate is a cyclic halonium ion. And remember, no rearrangement takes place during this reaction. No rearrangement takes place during this reaction. So there will be no rearrangement. No rearrangement takes place during this reaction. Point number 1, electrophilic addition reaction. Point number 2, intermediate of this reaction is cyclic halonium ion, so there will be no rearrangement. If there is no rearrangement, what we have to remember is simple, very simple. Whenever you are having alkene, addition of halogen takes place. Addition of halogen takes place in presence of CCl4, that means non-polar solvent. Then what will happen? You have to add simply halogen. But remember, you have to first of all break this bond and add halogen to these carbons. But addition of halogen is anti-addition. That means this reaction is actually anti-addition reaction. It is actually anti-addition reaction, and here vicinal dihalides are obtained. What is meant by vicinal dihalide? Those dihalides, those dihalogen compounds in which 2 halogens are present at 2 adjacent positions. Here, what is X? X is either Cl or Br. But if X2 is Br2, its color is reddish brown color. Remember. Now, if it is reddish brown color, what will happen? Have a look. This bromine, reddish brown color, what will happen to it? it will result in the formation of vicinal dibromide, and this vicinal dibromide is colorless. It's colorless. Its color was reddish brown. So this reddish brown color has been decolorized. If reaction takes place with unsaturated alkene or unsaturated alkyne, because what will happen in alkyne? First pi bond will be broken, Br will be added. After that another pi bond will be broken, another Br and Br will be added. That means tetrabromide will be obtained in case of alkyne. In nutshell, this will be added only if there is pi bond. That means if it is unsaturation, and during unsaturation, reddish brown color of bromine is decolorized. That is why this reaction can be used as a test. So we can simply say this reaction can be used as a test for unsaturation. Reaction can be used as a test for unsaturation. Very, very important point. Similarly, my dear lovely students, if halogenation takes place, once again, it can be generally, or let me write down like this. So halogenation takes place once again, but in polar solvent. That means solvent here is water, polar solvent. It is not CCl4, it's not non-polar solvent. Or we can write down like this, HOX as well. This is hypohalous acid. Then what will happen over here? Product instead of vicinal dihalide will be simply like this. Halohydrin will be obtained. Once again, this is an anti-addition reaction. That means addition of X and OH will be on opposite side. If X is below the plane, OH will be added from above the plane. If this is present on wedge bond, this will be on dash bond. If this is on dash bond, this will be on wedge bond. So this is the reaction. Here, X is not equal to F. Remember this. That means if you are having simply like this, if you are having this one, remember this OH is having negative part and this X means positive part. If you are having this one, there is no rearrangement. That means if there is no rearrangement, then at that time there will be no exception to Markovnikov's rule. Negative part should go to that carbon-carbon double bond which is having lesser number of hydrogen. That means here product will be simply like this. Negative part should go to this and positive part should go to this. Very, very simple. Here once again, if X2 is Br2, then we can simply say that Br2H2O means bromine water. So this bromine water can be used as a test for unsaturation, because once again reddish brown color is decolorized. I hope this is clear. After that, so this was addition of halogen. After that, let me add one more reaction over here. That is like this. Allylic halogenation. Now listen carefully. What is meant by allylic halogenation? Have a look, my dear lovely students. Allylic halogenation means halogenation taking place at allylic position. Have a look. So, alkene should contain at least one allylic hydrogen. So, this is alkene which contains at least one allylic halogen. Now, what will happen? If reaction takes place with halogen, but reaction takes place in presence of light or high temperature, say for example 773 Kelvin. Have a look. This is a reaction taking place with halogen. This is the reaction of alkene taking place with halogen, but in darkness. There is no temperature, high temperature, so there is no light. So this is taking place in darkness and obviously at low temperature. But when reaction takes place at high temperature, Addition of halogen across carbon-carbon double bond becomes reversible. That's why it is not addition reaction. This is simply a free radical substitution reaction. So this is an example of free radical substitution reaction. What will happen? This hydrogen will be replaced by X. But first of all, what you have to remember is just try to form a radical at allylic position. Try to form a radical at allylic position, as this is having only one allylic position. It's having only one allylic position. That means only one type of allylic radical will be obtained. When only one type of allyl radical is obtained, obviously X goes to that position and there will be only one allylic halide product formed. Sometimes there are more allylic radicals, different allylic radicals are formed, then different allylic halide will be obtained. So after that, H of this position and X, another X, it will form HX. Now listen carefully. Listen carefully. This X here is either Cl or Br. That means if Cl2 is used instead of X2, this is allylic chlorination. If Br2 is used, this is allylic bromination. Remember, allylic chlorination or allylic bromination can also be carried out like this. If this is treated with SO2Cl2, I mean say sulfuryl chloride, in presence of light at a temperature of 475 Kelvin and traces of peroxides or traces of peroxides, or my dear students, N-chlorosuccinimide is used, then these are the reagents in which chlorine is there. So these are suitably used for allylic chlorination. These are used for allylic chlorination. So this is the main product. If SO2Cl2 is used, then side product will be SO2 and HCl. And if N-chlorosuccinimide is used, what is N-chlorosuccinimide? Let me show you. This is N-chlorosuccinimide. This is N-chlorosuccinimide. Now, if this is used, then Cl goes to this and this H goes to this. That means at that time, or this is obtained. This is known as succinimide. This is known as succinimide. So this is the product. These are the side products. If SO2Cl2 is used and if NCS is used, then this is the side product. After that. Similarly, if NBS is used, N-bromosuccinimide is used, then major product will be simply, our product will be allylic bromination takes place at that time. That means it will be allylic bromide plus obviously N-bromosuccinimide means if instead of Cl, Br is present at N position, then obviously side product will be this succinimide. Side product will be this one. So in nutshell, allylic chlorination can be allylic chlorination can be carried out by using chlorine at high temperature or in presence of light, or by sulfuryl chloride, or by N-chlorosuccinimide. And allylic bromination can be taking place by using bromine at high temperature or in presence of light, or by using NBS. I hope this is clear. But how many products will be obtained during allylic chlorination or allylic bromination? That depends on how many different types of allyl radicals are obtained during this reaction. After that, we will be having halogen exchange reaction. In this, first one is Finkelstein reaction. First one is Finkelstein reaction. Listen carefully. What is meant by Finkelstein reaction? What will happen during Finkelstein reaction? Very simple. If you are having an alkyl chloride or alkyl bromide, let me write down, this is either alkyl chloride or alkyl bromide. If you are having alkyl chloride or alkyl bromide, and if it is treated with sodium iodide or potassium iodide in dry acetone, sodium iodide or potassium iodide in dry acetone, what will happen? Halogen exchange will take place. That means Cl or Br will be replaced by I. That means we get alkyl iodide, and then NaCl or NaBr will be precipitated out during this reaction, because in dry acetone NaCl or NaBr are partly soluble or insoluble. It will precipitate out, and this is completely soluble in dry acetone. So simply this reaction is favored by Finkelstein, this is favored by Le Chatelier's principle as well. So what is Finkelstein reaction? It is simply halogen exchange reaction in which chlorine or bromine is replaced by iodine. Another reaction is Swarts process. Another reaction is Swarts process. Swarts process is also what we call halogen exchange reaction, but here what will happen? This alkyl chloride or alkyl bromide, that means once again it is Cl or Br. Alkyl chloride or alkyl bromide is treated with heavy metal fluorides, say for example HGF, but heavy metal fluoride can be AGF, it can be HGF2, it can be Hg2F2, it can be COF3, it can be SBF3, it can be ASF3, etc. So heavy metal fluorides on treatment with alkyl chloride or alkyl bromide, heavy metal fluorides on treatment with alkyl chlorides or alkyl bromides, what will happen? Alkyl chloride or alkyl bromide on treatment with heavy metal fluorides, here only halogen exchange will take place. That means Cl or bromine will be replaced by F, and then we will get AgCl or AgBr, which gets precipitated out. So halogen exchange takes place. If chlorine or bromine is replaced by fluorine of heavy metal fluoride, reaction is known as Swarts process. With the help of this reaction, we get alkyl fluoride. And with the help of Finkelstein, we get alkyl iodide from alkyl chloride or alkyl bromide. I hope this is clear. After that, there is methods of preparation of haloarene, my dear lovely students. And haloarenes are obtained directly from, say, hydrocarbons, but those hydrocarbons are aromatic hydrocarbons, and with the help of a reaction known as halogenation. Halogenation means introduction of halogen to aromatic hydrocarbon. And this halogenation can be either nuclear or side chain halogenation. What is meant by this? First of all, this nuclear halogenation is an example of electrophilic substitution reaction. Remember point number 1. This is electrophilic substitution reaction. Point number second. The intermediate of this reaction is Wieland's intermediate. It's Wieland's intermediate, also known as sigma complex or simply a carbocation. Now listen carefully. Point number three. What you have to remember is that this reaction takes place in presence of Lewis acid, generally presence of Lewis acid, and in absence of light. Very, very simple reaction. Now have a look. That means if this is an aromatic hydrocarbon, say for example benzene, this on treatment with, say for example X2, say halogen, in presence of Lewis acid, say AlCl3 anhydrous or FeBr3 anhydrous. Generally, if X is either Cl or Br, why not I2? Because once this reaction takes place, what will happen over here? Have a look. H of this will be replaced by X. That means it will result in the formation of haloarene plus HX. Now, if X is I, then HI will be formed, and that is a reducing agent, and reaction at that time will be reversible. And if X is F, that means F2. F2 is very, 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 reactive, and reaction becomes explosive and uncontrolled one. That's why we do not use fluorine or we do not use iodine, but we can use iodine only in presence of strong oxidizing agents. Now, I hope this is clear, because here, with the help of these, basically electrophile of the reaction is X positive, halonium ion. Halonium ion goes to that carbon which is having highest electron density, but we know in benzene electron density at each carbon is same. After that, say for example, you are having haloarene like this. Suppose you are having chlorobenzene. Now you want further chlorination in it. Reaction takes place in presence of AlCl3, Lewis acid. Now what will happen? These two will form an electrophile, that's Cl positive. Now this electrophile goes to that position of this benzene ring which is having higher electron density. We know this chlorine is having a lone pair. With the help of this lone pair, it will show plus R. it will show resonance and it will donate electron towards benzene ring and increases electron density of the ring at ortho and para position because of plus R effect. So electron density at ortho and para position is rich. That means this is ortho para directing group. Cl positive will go to either ortho or to para position. So its product will be like this, or another product will be like this. But remember, my dear lovely students, chlorine has been introduced, halogen has been introduced into the ring. Halogen has been introduced into the ring. That's why this is known as nuclear halogenation. And this nuclear halogenation is an electrophilic substitution reaction, and intermediate of this reaction is this carbocation. I have not shown the mechanism, no need of mechanism, but first of all, when it gives electron to this, whenever it gives electron to this, there will be a positive charge on carbon of this ring. That's known as sigma complex or valence intermediate. This will become the major product. And this is minor. Why this is minor? Because these chlorines are closer to each other. Their electron clouds will repel. Because of that repulsion, it becomes less stable and hence minor. Similarly, if you are having a hydrocarbon like this, methyl benzene or toluene, this is also hydrocarbon. If this hydrocarbon undergoes chlorination or bromination, in nutshell halogenation. Now, reaction takes place generally in presence of, say for example, Lewis acid. Then what will happen? These two will form, this Lewis acid will help to form Br positive from Br2. Now, Br2 positive will be obtained. Now, it will go to that carbon of the ring which is having higher electron density, and we know CH3 group, alkyl group donates electron towards ring because of hyperconjugation and increases electron density of the ring at ortho and para position. Hence, alkyl groups are also ortho para directing because of hyperconjugation. So product will be either ortho bromotoluene or product will be para bromotoluene. But major product will be once again this one. So once again, halogen has been introduced into the ring, into the nucleus, into the ring. That's why this is known as nuclear halogenation. This is known as nuclear halogenation. I hope this is clear. I hope nuclear halogenation is clear. After that, there is another one, that is side chain halogenation. This reaction, point number 1, this reaction is free radical substitution reaction. This is free radical substitution reaction. Point number 2. Intermediate of this reaction is free radical, obviously. So intermediate here will be a free radical. Here no carbocation will be obtained. It will be a free radical. Point number 3. Reaction takes place in presence of light or high temperature. And in absence of Lewis acid. So if you have a reaction simply like this, you are having aromatic hydrocarbon and you are having Br2 as well, or Cl2, say halogenation. Why not F2? Because that reaction is very reactive. Why not I2? Because generally Hi formed will simply, once Hi will be formed, that iodo, that product which will be obtained over here will be converted back to, the substrate. That means that will be a reversible reaction. That is why we generally take either chlorine or bromine. So bromination takes place. Now have a look. This is also methyl benzene or toluene and bromine. This is also methyl benzene or toluene and bromine. But the only difference is here it is light or high temperature. Here it is Lewis acid in absence of light and in absence of high temperature. So in presence of Lewis acid, it is in presence of light or high temperature, in absence of Lewis acid. This is what we call free radical substitution reaction. What will happen? Free radical will be formed at this benzylic position. That means first of all this will be obtained. First of all, it will be formed like this. Free radical will be formed like this. Finally, Br radical will go to that place. In nutshell, let me write down the product. product will be simply CH2Br, and HBr will be the side product over here. So this reaction is also known as benzylic halogenation. Why? Because this halogenation generally takes place at benzylic position. For example, if you are having this one, benzyl bromide, this one, and you want to perform one more bromination over here, that means if bromine is taken in excess, then what will happen? If bromine is taken in excess over here, it will replace all these hydrogens. Then another product will be like this. It will be CHBr2, then HBr. Similarly, if this is like this, CHBr2 plus Br2, what will happen now? What will happen now? Have a look. What will happen now? It will result in the formation of CBr3. And now reaction will not take place because there is no hydrogen now which we can replace by bromine. Similarly, if you are having a reaction like this, if you are having more than one carbon inside chain having hydrogens, then bromination generally takes place at which place? Bromination takes place at benzylic position. Which is benzylic position? Carbon which is directly attached to benzene ring, because that can form more stable carbon free radical. So this will be the product of the reaction. So generally halogenation takes place at benzylic position. That's why this is also known as benzylic halogenation. I hope this is clear. So remember, this is side chain halogenation is benzylic halogenation, and it's example of what we call free radical substitution reaction. Intermediate is free radical and takes place only in presence of light or heat in absence of sunlight. Okay. Now have a look. So this is what we call simply benzylic halogenation or side chain halogenation reaction. Now this side chain halogenation or side chain chlorination or side chain bromination can also be carried out like this. Have a look. If you are having this one, and if it is treated with SO2Cl2 at a temperature of 475 Kelvin in presence of light and traces of peroxide, then here it is Cl will replace this H, then benzylic chlorination will take place over here. It will be benzylic chlorination, HCl and SO2 will be the side product. Similarly, if you are having toluene, say hydrocarbon, and if it is treated with NCS in presence of light, then what will happen? Once again benzylic chlorination will take place, and we will get succinimide over here. Succinimide will be the side product. But if this toluene is treated with NBS, so remember the function of NBS, NCS, their function is either allylic bromination or now benzylic bromination or benzylic chlorination. So here NBS will simply help in benzylic bromination and side product will be this one. I hope this is clear. Let me know in the chats if I am clear till now. Let me know quickly. My dear lovely students. Let me know quickly. Quick. Let me know quickly, my dear lovely students. Is this clear? Okay, that's great. That is great. After that, we will be having another reaction, methods of preparation of haloarene, but from aromatic, what we call amines. Have a look. If you are having an aromatic primary amine known as aniline, this is aromatic primary amine known as aniline. Whenever you are having aniline, that means aromatic primary amine, if it is treated with NaNO2, an excess of acid, say for example HCl, or these two can form within the reaction nitrous acid, that means nitrous acid is formed within the reaction in situ, and acid is taken in excess at a temperature of 0 to 5 degrees Celsius, what will happen over here? They always result in the formation of benzene diazonium salt. So benzene diazonium salt, benzene diazonium chloride is formed over here, plus say water. And this benzene diazonium chloride is stable up to this temperature. But once temperature is greater than 5 degrees Celsius, then it becomes unstable. It gets decomposed to, say, phenol if water is there. So it is stable, but even this is stable only up to 5 degrees Celsius. After 5 degrees Celsius, if temperature is increased above 5 degrees Celsius, it gets decomposed. Now, this benzene diazonium salt, listen carefully. Say for example, benzene diazonium chloride, once obtained. Now, if it is treated with, listen carefully. If it is treated with cuprous chloride, Cu2Cl2HX, let me write down over here like this, Cu2X2HX, cuprous halide, or CuXHX, this is cuprous halide and hydrogen halide. X here is either Cl or Br. Then what will happen? This N2 will be replaced by N2 of benzene diazonium salt will be replaced by halogen. That means it will be replaced by chlorine or bromine. That means we get chlorobenzene or bromobenzene, and N2 will be evolved at that time. This reaction, with the help of which we can get chlorobenzene or bromobenzene on treatment with benzene diazonium salt with cuprous halide in presence of HX, this reaction is known as Sandmeyer's reaction. This is known as Sandmeyer's reaction. So, reaction is basically preparation of aromatic amine, preparation of what we call this haloarene from aromatic primary amine. Aromatic primary amine first form benzene diazonium salt, then we can get chlorobenzene or bromobenzene with the help of what we call Sandmeyer's reaction. Or you can use copper instead of cuprous Cu positive, you can use copper and HX. X once again is Cl or Br. That means once again we can get chlorobenzene or bromobenzene here, but reaction is known as Gattermann's reaction. Reaction is known as Gattermann's reaction. That means we can prepare chlorobenzene or bromobenzene with the help of either Sandmeyer reaction or Gattermann reaction, but yield of haloarenes is more in Sandmeyer reaction. As compared to Gattermann's reaction. So yield of haloarene will be more in Sandmeyer reaction as compared to Gattermann's reaction. I hope this is clear. If this reaction is, if this benzene diazonium halide is treated with Ki, aqueous Ki and then warm, then simply this N2 will be replaced by I. That means we can get iodobenzene. So we can form chlorobenzene or bromobenzene with the help of these two reactions. We can form iodobenzene with the help of this, or we can form like this. We can treat it with HBF4 first, then this Cl minus will be replaced by BF4 minus. That means we will get benzene diazonium tetrafluoroborate first. Finally, this is heated. This is heated and we will get fluorobenzene, N2, and obviously BF3 will be also lost. Now, this reaction with the help of which we get fluorobenzene from benzene diazonium salt is known as Bals-Schimmann reaction. That means with the help of benzene diazonium salt, with the help of primary aromatic amine, we can get chlorobenzene, bromobenzene, we can get fluorobenzene, we can get iodobenzene. In nutshell, we can obtain haloarene with the help of these amines or benzene diazonium salts. After that, there is chemical reactions of haloalkane, and there are first reaction is chemical reaction of haloalkane. First reaction is nucleophilic substitution reaction. Have a look. This is what we call haloalkane, and we want to perform its chemical reaction. We want to perform its chemical reaction. Now listen, and these chemical reactions are nucleophilic substitution reactions. So let's take examples of nucleophilic substitution reactions one by one. Let's take examples of nucleophilic substitution reactions one by one. Listen, whether you use H2O, whether you use KOH, whether you use NaOH, whether you use, I mean to say, AgOH, this X will be replaced by OH. That means finally product will be alcohol. But in first case it will be HX, in second case it will be KX, in third case NaX, in fourth case AgX will be the side products. But this will be simply nucleophilic substitution reaction. In second reaction, if I write like this, if I write RONA, sodium alkoxide or potassium alkoxide, R and R, to differentiate these two, let me write down R prime over here. We know this is negative part, this is positive part. Nucleophile will attack, X minus will leave. So these are SN2 reactions simply. So what will be the product? This is R and then this OR will be obtained there. Let me write down prime. So this is ether plus NaX will be the side product. Similarly, if we use, my dear lovely students, sodium phenoxide over here, potassium phenoxide over here. So what will happen? This phenoxide will act as a nucleophile. Once again a normal SN2 reaction. Once again an ether will be formed plus NaX will be the side product. Such reactions with the help of which alkyl halide on treatment with alkoxide or phenoxide results in the formation of ether. Such reactions are known as Williamson's synthesis or Williamson ether synthesis. So Williamson's synthesis, or you can say Williamson's ether synthesis. Very, very simple reaction. After that, if we treat this with NaSH, sodium hydrosulfide, this is negative, this is positive, what will happen? This negative part, nucleophile will attack, X minus will leave. So we will get RSH, thioalcohol plus, thiol plus NaX side product. Okay, now if NaSR is used, sodium mercaptide is used to differentiate this R from this R. Let me write down a dash over here. So this is Na positive, SR negative. SR negative will act as a nucleophile. So we will get thioether plus NaX as the side product. Similarly, if we use NaN3, this is sodium azide, Na positive, N3 minus. So nucleophile is N3 minus. So what will happen? Nucleophile will attack, X will leave. So RN3 means alkyl azide plus NaX will be the side product. Very simple SN2 reaction is this. After that, if I write down Na positive, then C triple bond C and then R having a dash and negative on this carbon. So this alkynide part will act as a nucleophile. So it will attack this, X will be lost. That means it will be R, then this C, then triple bond C, single bond R prime. That means higher alkyne will be obtained and NaX will be the side product. I hope this is clear. After that, if I write down this one, R, or let me write down this in this fashion, Ag positive, O C double bond O and R. To differentiate this R and R, this is R prime. So can I say this is sodium, this is what we call silver salt of carboxylic acid. So this will attack as a nucleophile, this negative part, and we will get R, O, C double bond O and R prime. Or you can write down R prime, C, O, O, R, that means ester, plus AgX will be the side product. I hope this is clear. Now, have a look. Other reactions can be like this. Have a look, my dear lovely students. If I write KCN, it is K positive, CN negative. But listen. This is an ionic compound and this Cn minus is an ambident nucleophile. So this is ambident nucleophile. What is meant by that ambident nucleophile? That nucleophile in which there are two different donor sites, two different nucleophilic sites. One is carbon, another is nitrogen, but carbon nucleophilic site is stronger as compared to nitrogen. So carbon will attack more, and when carbon attacks, carbon-carbon bond, stronger bond will be formed. So major product of this reaction will be RCN will be the major product. RCN, cyanide will be the major product, and side product will be KX. After that, if AgCN is used, this is a covalent compound. No positive negative charge is there. This nitrogen will form. This nitrogen will attack and will form bond with R. When nitrogen forms bond, major product will be RNC. Major product will be isocyanide. This is the major product, and side product will be AgX. I hope this is clear. After that, if we use KNO2, it is K positive, then it is O having a negative charge. KNO2 is K positive, O having negative charge. Then it is N, double bond O. This is once again an ambidentate nucleophile. So here it is O minus, which is stronger nucleophile as compared to neutral nitrogen. So the major product is when O minus forms bond. So it is ONO. Alkyl nitrite is the major product. Alkyl nitrite is the major product, and what we call KX will be the side product. After that, it's an ionic compound. Now, if AgNO2 is there, it's a covalent compound. That's why oxygen and nitrogen here are neutral. Neutral oxygen and neutral nitrogen. Neutral nitrogen is more nucleophilic, so nitrogen will attack much more. So normal SN2 reaction, so this should be a better alkyl halide should be, say 1 degree alkyl halide. So nitrogen will be attacked more. When nitrogen forms a bond, then this is known as nitroalkane. Nitroalkane at that time will be the major product, or you can form like this. This is O minus. This is N having a positive charge. So this is nitroalkane, which is major over here. So ionic covalent, major, cyanide, isocyanide, alkyl nitrite, nitroalkane. Remember these things. Similarly, if you use Grignard's reagent, RMgX, it is R having negative part, Mg having positive part. So this R, let's differentiate this R by from this R by putting a dash over here. So this R minus will attack. That means nucleophile will attack. So R will be the product. R prime of this and R of this will be the product. Alkane will be the product. Similarly, if ammonia is there as the nucleophile, nitrogen will attack. Finally, it will lose H. X and H will be lost. Then we will get primary amine. Listen carefully. We will get primary amine. So if ammonia is taken in excess, primary amine is major product. So if ammonia is taken in excess, this is the major product. But if alkyl halide is taken in excess, first primary amine will be obtained. Primary amine is obtained. After that, as alkyl halide is taken in excess, then primary amine reacts with alkyl halide and results in the formation of secondary amine. Then as alkyl halide is taken in excess, then it will result in the formation of tertiary amine. Now, reaction will not stop. As alkyl halide is taken in excess, it will result in the formation of quaternary ammonium salt. This reaction, remember, this reaction in which alkyl halide is taken in excess and is treated with ammonia results in the formation of quaternary ammonium salt via formation of primary amine, secondary amine and tertiary amine. This reaction is known as Hoffman's ammonolysis method, or Hoffman's ammonolysis of alkyl halide. Hoffman's ammonolysis method, or Hoffman's ammonolysis of alkyl halide. Hoffman's amonolysis of alkyl halide. These are few examples of nucleophilic substitution reactions. After that, my dear lovely students, elimination reactions. Elimination reactions of what? It is of alkyl halides. That means dehydrohalogenation reaction. Dehydrohalogenation reaction of haloalkane. And the reaction which are given in your NCERT is like this. Whenever you are having an alkyl halide, say for example this one, and its dehydrohalogenation takes place by using alcoholic potassium hydroxide at high temperature. Remember, whenever alcoholic potassium hydroxide is there, reaction is an example of E2 reaction. And whenever reaction is E2 reaction, halogen attached to carbon is alpha and to that carbon is beta. What we have to do is, we have to remove alpha, we have to remove halogen from alpha position and we have to remove hydrogen from beta position. Hence, we will get an alkene like this. Because if halogen is removed from alpha, hydrogen from beta, form double bond between alpha and beta. It will be like this. So remember, among alkyl halides or haloalkanes or among alkyl halides, what will be the reactivity order towards this reaction? I mean, say, which is dehydrohalogenation or E2 reaction. It is always 3 degree alkyl halide greater than 2 degree alkyl halide greater than 1 degree alkyl halide. Remember this point. And number second, because this X can be F, Cl, Br or I. So among, and this is R, among Ri, Rbr, RCl and Rf, reactivity order will be simply like this. Among Ri, Rbr, RCl, Rf, reactivity will be like this because rate of E2 is directly proportional to leaving ability of the group. It is directly proportional to leaving ability of the group. It is directly proportional to leaving ability of the group. I hope this is clear. I hope this is clear. I hope this is clear. Now, for example, you are having like this. You are having like this. You are having like this. Structure is like this. Listen carefully. Listen carefully. But remember, X here is not equal to F. That means X is either Cl, Br or I. Then what we have to do is, if this is alcoholic potassium hydroxide, I mean to say if this reaction is E2, what we have to do is, we have to first of all find out alpha carbon and beta carbon. As there are two different beta carbons, so we will compare their hydrogens. Here number of hydrogens are 3, here number of hydrogens are 2. So I will say this is beta carbon having lesser number of hydrogens. So this is poor with respect to hydrogen in comparison to this, and this is rich with respect to hydrogen in comparison to this. Now, if hydrogen is removed by this base from this position, then this beta and alpha will form double bond after replacement of this X. If hydrogen has been replaced, removed by base from this position, then this beta and alpha will form double bond. So what will be the products over here? How many products will be formed? One will be formed from rich position, one will be formed from rich position, and the product formed from rich position is known as Hoffman product, and another will be formed from poor position, and the product formed from poor position is known as Sadzef, and this is what we call a Sadzef product. And remember, this Sadzef product is the major product for this reaction. This will be the obviously minor product of this reaction. I hope this is clear. But if same reaction takes place, listen carefully. If same reaction takes place, but now halogen is a poor leaving group and that halogen is F. It's a poor leaving group. If same reaction takes place, same products will be obtained. Same reaction takes place, same products will be obtained, but same products will be obtained over here. First of all, we have to find out this is alpha, this is beta, this is beta. So same products will be formed. This is what we call poor with respect to hydrogen. This is what we call rich with respect to hydrogen. So what will be the product? Products will be same. Hoffman product will be CH2 double bond CH, single bond CH2, single bond CH3. This will be the Hoffman product, and Sadzef product will be CH3, single bond CH, double bond CH, single bond CH3. Well, listen carefully. This is Hoffman product. This is Sadzef product. When X is not equal to F, you have to check among these products which one is more stable. This product is more stable because this is having 6 alpha hydrogens and this is having only 2 alpha hydrogens. More stable product is always major product if X is not equal to F. But if X is equal to F, which one is major, which one is minor, we have to form a carbanion at that time at beta position. Form carbanion at beta position. And we know this carbanion is more stable as compared to this. Which carbanion? The carbanion which is more stable is this one as compared to this. And the product formed from more stable carbanion means this one will be the major product. Listen carefully. This is major and this will be minor. So listen once again. If X is not equal to F, if X is ClBrI and reagent is this one, and substrate is like this, suppose, at that time form products, the product which is more stable is major. But if same reagent, I mean say same substrate is here, but instead of X there is F, at that time form carbanion at beta positions. The carbanion which is more stable, the product formed from more stable carbanion is always major product if X is F. Similarly, here X is once again F. Have a look. X is once again F. X is once again F. Now, we have to form products over here. Alcoholic potassium hydroxide. Once again E2 reaction. What we have to do is, we have to check this is alpha, this is beta, this is beta. This beta is having 3 hydrogens, so this is rich as compared to this, because this beta is having only 2 hydrogens, so this is poor. What we will do, we will simply replace, we will remove hydrogens from this beta first. When we remove hydrogen from this beta, this is poor beta position, so this is the product at that time. So product formed from poor is Sadzef, and product formed from what we call Hoffman, from rich is Hoffman. So this will be the Hoffman product. So if we remove hydrogen from this, so it will form double bond with this because F will be lost. So this will be Hoffman, this will be Sadzef. But as F is the poor leaving group, what we have to do is we have to form carbanion. Carbanion over here, carbanion over here. This carbanion is resonance stabilized, more stable as compared to this. So the product formed from this, that means this one will be the major product. So this is the major product and this is the minor product. So this was all about elimination. This was all about elimination. After that, reaction with metals. Reaction of what? Reaction of haloalkane with metal. Have a look. If your haloalkane is this and metal is magnesium, what will happen? What will happen? Always magnesium, whenever treated with that compound which is having CX bond, magnesium comes in between C and X. That means we will get RMgX, known as alkyl magnesium halide, also known as Grignard's reagent. So this is having negative part, this is having positive part. That means whenever alkyl halide or haloalkane is treated with magnesium, we will get Grignard's reagent. But this Grignard reagent, on treatment with any acidic hydrogen containing compound, say for example water, positive part, negative part, any acidic hydrogen containing compound will lose H positive. That H positive will be accepted by this R minus. That means it will act as base and it is an acid. So normal acid base reaction will take place. So we will get alkane. We will get alkane. So whenever alkyl halide reacts with magnesium, it first forms Grignard reagent. But if Grignard reagent is treated with any acidic hydrogen containing compound, for example water, alcohol, phenol, carboxylic acid, HCl, any acid, any acidic hydrogen containing compound, at that time it will give alkane, and this reaction is known as Zerivatinov's reaction. This is known as Zerivatinov's reaction. So this was first reaction in which alkyl halide reacts with magnesium. So this is first. Another reaction is in which alkyl halide reacts with sodium. In which alkyl halide reacts with sodium in presence of dry ether. What will happen during this reaction? Just try to break this carbon X bond if it reacts with sodium and forms a radical over here. Once radical is formed, then combination of this radical takes place. That means it will result in the formation of an alkane. This reaction is known as Wurtz reaction. This is known as Wurtz reaction. And we have already discussed Wurtz reaction in class 11th. Now, after that, see reaction of alkyl halide with zinc. Actually, it first results in the formation of dialkyl zinc known as Frankland's reagent. Finally, that Frankland's reagent reacts with alkyl halide once again and results in the formation of alkane. So what is the trick? Trick is simply, whenever CX bond is there, zinc is there, form a radical. It's not the, correct mechanism, but this is the trick. R radical once formed, it results in the formation of RR. Symmetrical alkanes are obtained and reaction at that time will be known as Frankland's reaction. Frankland's reaction. Similarly, if alkyl halide reacts with, copper. If alkyl halide reacts with copper and finally, it first reacts with, lithium, then it reacts with cuprous halide. And finally, if you are having a reagent like this, known as Gilman's reagent, if you are having a reagent like this, lithium dialkyl cuprate on treatment with alkyl halide, when reaction takes place in presence of dry ether, what will happen? Any one alkyl from this attacks this and X will be lost. Normal SN2 reaction. So R and R prime, that means alkane will be obtained, but this alkane can be either symmetrical or unsymmetrical and reaction is known as what we call Cori-Haas reaction. So RCU and LiX will be also there. RCU plus LiX will be also there. This is known as Cori-Haas reaction. So all these reactions are actually discussed in class 11th syllabus. So in that session where we have completed 11th class organic chemistry. So this is Cori-Haas reaction. So we have completed this in what we call class 11th session. So this can be, unsymmetrical alkane can be prepared in a pure form in this reaction as compared to these. So to prepare unsymmetrical alkane, Cori-Haas reaction is preferred over Wurtz reaction or Frankland's reaction. I hope this is clear. After that, there is reduction reaction. That means reaction of alkyl halide. Reduction reaction. Let me write down over here. It's reduction of alkyl halide to alkane. Now what we have to do is we have to replace X by H. So number one reagent is zinc in presence of acid. That means active metal in presence of acid. Say for example HCl. Another, you can use zinc copper couple in alcohol. Number third, you can use zinc in, what we call acetic acid. Or you can use zinc in basic medium as well, or active metal in, or active metal dissolved in base as well. You can use HI in red phosphorus as well. You can use H2 in presence of catalyst, say for example PDC. You can use, let me write down over here, H2 in presence of catalyst. For example, PD, palladium with small amount of carbon. You can use lithium aluminium hydride. You can use sodium borohydride. You can use triphenyl tin hydride. So that alkyl halide gets converted to alkane. But only thing what you have to remember is that sodium borohydride cannot reduce alkyl halide to alkane. Number second point. Tertiary alkyl halides cannot be converted. Tertiary alkyl halides, let me write down this. Tertiary alkyl halides cannot be converted to alkanes by using lithium aluminium hydride. But instead, remember, if tertiary alkyl halide is there, lithium aluminium hydride is there, then it results in the formation of alkene instead of alkane. Otherwise, all can be used. After that, chemical reactions of haloarenes, nucleophilic substitution reactions of haloarenes. Remember, haloarenes do not undergo nucleophilic substitution reactions under normal conditions, or do not show nucleophilic substitution reactions under normal conditions because of few reasons. Because first reason is simple, resonance. First reason is resonance. What? Have a look. We cannot break this CX bond, because this CX bond due to resonance becomes partial double bond. That means this is actually the partial double bond because of resonance, and due to that this bond becomes strong. So to cleave this bond, it is very, very difficult to cleave CX bond. It is very, very difficult to cleave CX bond of haloarene, because CX bond is a very strong bond due to partial double bond character as a result of resonance. Second point is difference in hybridization. Difference in hybridization. Difference in, that means second factor is hybridization. Difference in hybridization to which halogen is attached. Have a look. Here halogen is attached. In case of haloarene, halogen is attached to sp2 hybridized carbon. In case of haloalkane, halogen is attached to sp3 hybridized carbon. Here S character is 25%. Here S character is 33.33%. Now, what is meant by that? We know bond strength is directly proportional to S character. We know this. So more S character is present in this. So this CX bond is more stronger as compared to this. Bond is stronger, hence it is difficult to cleave as compared to this. That's why nucleophilic substitution reaction takes place easily in haloalkane, but it is very difficult, or we cannot, say these haloarenes cannot undergo what we call nucleophilic substitution under normal conditions, because this bond is very strong. It is difficult to cleave either due to partial double bond character because of resonance, or this bond is strong. Why strong? Because bond strength is very, very, more in this as compared to this. That means this bond is shorter, this bond is longer. So shorter bond means bond is very, very strong. After that, point number third, electronic repulsions. Electronic repulsions. What is meant by this? Have a look. We know this is halogen, and we also know that there are p orbitals which are perpendicular to the plane but parallel with respect to each other. So these p orbitals can overlap like this. So electron cloud is above the plane as well as, below the plane. So electron cloud is above the plane as well as below the plane. When nucleophile approaches to this carbon, it cannot attack from above the plane, neither it can attack from below the plane, because electron cloud will repel this nucleophile electron cloud. Hence there will be electronic repulsions, electron repulsion. That means electron cloud of this and electron cloud of this will repel each other. So there will be no attack of nucleophile on that carbon to which halogen is attached. Hence there will be no nucleophilic substitution reaction. Point number 4 is instability of a carbocation. Instability of carbocation. What is meant by that? That means, say for example, let us suppose this CX bond is broken. Then if this is broken, it will result in the formation of an unstable carbocation. Phenyl carbocation is highly unstable because positive charge is present on that carbon which forms a double bond. So this is highly unstable carbocation. So such carbocation which is highly unstable, That means we cannot form such type of carbocations, hence there will be neither SN2 reaction nor SN1 reaction. So there will be no nucleophilic substitution reaction under normal conditions. But we can perform nucleophilic substitution reaction of haloarene but under drastic conditions. For example, here reaction is Dow's process. For example, this is the amine say chlorobenzene. This chlorobenzene on treatment with NaOH, sodium hydroxide, at a temperature of 623 Kelvin and at a pressure of 300 atmosphere, followed by acidification. Then what will happen? Phenol is obtained. This reaction from which we get phenol from chlorobenzene by using sodium hydroxide at a temperature of 623 Kelvin, 300 atmospheric pressure, followed by acidification. This is known as what we call Dow's process. And Dow's process is simply a reaction known as aromatic nucleophilic substitution reaction. It's aromatic nucleophilic substitution reaction. But remember, aromatic nucleophilic substitution reactions are of two types. One is aromatic nucleophilic substitution taking place in the form of elimination addition. Another is aromatic nucleophilic substitution reaction taking place in the form of addition elimination. This type of reaction is Dow's process is elimination addition reaction. This is elimination addition reaction, and the intermediate of this reaction is benzene. That means the mechanism which takes place over here is basically benzene mechanism. Benzene mechanism. Number next. If remember, if we talk about this aromatic nucleophilic substitution reaction, rate of aromatic, remember, nucleophilic substitution, it is directly proportional to electron withdrawing groups present in haloarene. If we talk about haloarenes, then you have to remember this point. If haloarene contains electron withdrawing groups, rate of aromatic nucleophilic substitution or rate of aromatic nucleophilic substitution, that means nucleophilic substitution reactions of haloarene at that time increases. That means if NO2 group is present at para position, rate of this reaction will be very much fast. That means this reaction will take place easier as compared to this. That is why here temperature is at high, this takes place at more drastic, more elevated temperature as compared to this, because this can take place even at lower temperature for 43 Kelvin. And what will happen? The Cl will be replaced by OH group. So this will be the product. Remember, if this is first reaction Dow's process, this is second reaction. First one is Dow's process and is an example of benzene mechanism. That means this is aromatic nucleophilic substitution elimination addition reaction. But this second or this third one, have a look. If number of electron withdrawing groups are increased, reaction will be much more faster. Reaction will be much more faster. Listen carefully. Reaction will be much more faster. That means reaction now can take place at, say for example, 368 Kelvin temperature, and product will be like this. Product will be like this. So similarly, if reaction 4 is like this, it is Cl, then electron withdrawing groups are more in number, then reaction can take place easily. For example, we can use water, a weaker nucleophile as compared to, NaOH, and even on warming reaction takes place. So this Cl will be replaced by OH. So we will get 2,4,6-trinitrophenol, 2,4,6-trinitrophenol, commonly known as picric acid. So listen and try to remember. This second reaction, third reaction, and fourth reaction are examples of this. And here intermediate is Mason-Hammer complex. This is the intermediate of the reaction. And this Mason-Hammer complex is more stable if electron withdrawing fluorine is attached as compared to chlorine, as compared to bromine, as compared to iodine. That means those reactions in which elimination addition takes place, say for example any one among these, say for example this one, if here it is fluorine This one will become much more faster reaction as compared to this one, as compared to this one. You have to remember this, as compared to this one. But remember, this rate will be much more increased only and only if electron withdrawing groups are present at ortho and para position instead of meta position. I hope this is clear. This is Dow's process. This one is Dow's process, and these are different examples of these nucleophilic substitution aromatic reactions. After that, electrophilic substitution reactions are there. Electrophilic substitution reactions are there. Have a look, have a look, have a look. Let us suppose you are having haloarene, suppose chlorobenzene, and we want to perform electrophilic substitution reactions in chlorobenzene. Generally, electrophilic substitution reactions of chlorobenzene are, say for example, like this. First is halogenation. Halogenation can be once again chlorination or bromination. Suppose chlorination, Cl2AlCl3, or you can perform bromination, Br2FeBr3. So both these will form Cl positive as electrophile. So electrophile goes to ortho or para position. Why ortho or para position? Why not to meta position? Because halogens are ortho para directing. Why halogens are ortho para directing? Because they donate electron because of resonance, because of plus R effect towards ring, and increases electron density of ring at ortho and para position. That's why this electrophile goes to, say ortho or para. So as chlorine is introduced into the ring at ortho and para position, so this is halogenation taking place at ortho and para position. Now after that, reaction can be nitration, and nitration generally takes place by using nitric acid and sulfuric acid, known as nitrating mixture. This sulfuric acid here acts as an acid and nitric acid here acts as a base, and this H2SO4 acts as a catalyst. Its function is to generate NO2 positive electrophile from HNO3. So HNO3 can form NO2 positive nitronium ion electrophile, and that electrophile will be formed with the help of H2SO4. So this electrophile goes to either ortho or to para position. So either ortho or to para position. But remember, the para product in these cases is the major product, because in case of ortho there will be repulsion. So para will be the major product. So nitro group has been introduced. That's why this is known as nitration. After that, sulfonation. Say for example, sulfonation. Electrophile here is SO3 generally. That SO3 goes to either ortho or para position. When that goes to ortho and para position, that becomes SO3 minus. Finally, that will abstract hydrogen from the medium, so it becomes SO3H. So sulfonic acid group, SO3H group has been introduced. That is why reaction is known as sulfonation. But remember, sulfonation reaction is a reversible reaction. Remember this. After that, if we use alkyl chloride in presence of AlCl3, here alkyl carbocation acts as the electrophile, and this electrophile is alkyl carbocation. Hence, rearrangement can take place. So rearrange if possible. So I will write down rearrange if possible. So remember these things, because whenever electrophilic substitution reaction will come in different chapters, these are already done. Now, at that time, after that, this R positive, that means alkyl carbocation, will go either to ortho position or to para position. But major in these will be always para, until and unless in ortho there will be chelation or intramolecular hydrogen bonding. Once intramolecular hydrogen bonding will be present in ortho, at that time ortho is major. But here in these examples, para is major product. After this, my dear lovely students, it will be acid chloride or acid anhydride on treatment in presence of, say Lewis acid. Then here it will form this electrophile, but this electrophile will not undergo rearrangement because it is stable because of back bonding. So there will be no rearrangement, and the product will be simply Cl, chlorobenzene. Then, and this chlorobenzene, this C double bond OR, acyl group will be introduced. That's why acylation reaction. That is why this is known as acylation reaction. Why? Because acyl group has been introduced. Now listen, here halogen has been introduced, halogenation. Nitro group has been introduced, so nitration. Sulfonic acid group has been introduced into this ring, sulfonation. Alkyl group has been introduced, alkylation. Acyl group has been introduced, acylation. But these two reactions, alkylation and acylation, these are Friedel-Crafts reactions. So these are Friedel-Crafts reaction. That means first one is alkylation, that means Friedel-Crafts alkylation. Second one is acylation, that means it is Friedel-Crafts acylation. I hope this is clear. I hope this is clear. Sometimes it is like this. Chlorobenzene reacts with chlorobenzene. Let me write down 2 molecules of chlorobenzene so as to balance the reaction. Sometimes chlorobenzene is treated with chloral. Chloral means trichloroethanol or trichloroacetaldehyde. This is known as chloral. In presence of H2SO4. In presence of H2SO4, what will happen over here? Have a look. Water will be lost. That means its one bond will be less and its 2 bond will be less. So it will form bond with this. So it will result in the formation of this one. It will result like this. It will result in the formation of this one. CHCCl3. Similarly, it is like this. So this is known as what we call DDT. What is DDT? Diphenyl trichloroethane. This DDT is used as an insecticide. It's used as an insecticide, a very cheap, insecticide, and it is effective. Against, let me write down, DDT is effective against Anopheles mosquitoes. Which causes, malaria. So it is very effective against Anopheles mosquitoes. That means it is very effective against malaria. And it is effective against, lice. That may carry typhus. So remember its points, that it is effective against Anopheles mosquitoes and lice. That means it is effective against malaria and typhus. Point number 3. It is fat soluble. Point number 4. It is non-biodegradable. Now, let me know in the chats if this is clear till now. If everything is clear till now, let me know in the chats. Then another reaction will be reaction with metal. Let me know in the chats. Is everything clear till now? Let me know quickly. Is everything clear till now? Is everything clear till now? Let me know quickly. Come on everyone. Thank you. Okay, beta, thank you. After that, it's a reaction with metals. Listen carefully, beta. Whenever you are having haloarene, once again a CX bond is there. Whenever CX bond is there, magnesium is there. What will this magnesium do? This magnesium will be simply, this magnesium will come in between C and X. That means it will result in the formation of, once again, phenyl magnesium halide, once again a Grignard reagent. But if this Grignard reagent, this is having negative part, this is having positive part. If this Grignard reagent is once again treated with any acidic hydrogen containing compound, say for example water, what will happen? Negative part will accept this H positive, so it will result in the formation of benzene, plus it is MgX and OH, hydroxy magnesium halide. So it will be like this. Second reaction. This alkyl halide, this haloarene aryl halide can react. It can react with sodium in presence of dry ether, like that of Wurtz reaction. This bond will be broken, CX bond will break, then it will result in the formation of a radical. Then this radical will combine together with similar type of radical and bi-aryl will be obtained. So reaction of aryl halide with sodium resulting in the formation of bi-aryl is known as Fittig reaction. This is known as Fittig reaction. Similarly, if alkyl halide as well as aryl halide both react together with sodium in presence of dry ether, then major product will be, it will result in the formation of alkyl radical, it will result in the formation of phenyl radical. Then these two will react together and this will be the major product. That means alkyl benzene will be the major product over here. This is known as Wurtz-Fittig reaction. This is known as Wurtz-Fittig reaction. Similarly, if you are having iodobenzene and this iodobenzene is treated with copper and heated, then this bond will be broken and it will result in the formation of a radical over here. These radicals will combine together and will form phenyl rings. Biphenyl will be obtained over here. This reaction is known as Ullmann bi-aryl synthesis. This reaction is known as Ullmann bi-aryl synthesis. So this is all about your first chapter, that is haloalkane and haloarene. Now, are you ready for next chapter right now? Are you ready for next chapter right now? Let me know in the chats quickly. Are you ready for next chapter? Are you ready for next chapter? Tell me quickly. Let's complete alcohol phenol ether first. After that, I will give break. First, we will complete alcohol phenol ether. Then, we will take break. Let's complete alcohol phenol ether first. It will take 1.5 hours. That means 1 hour 30 minutes, 1 hour 40 minutes maximum. Tell me. So, should I start now? We will first complete this one. After that, we will take break. 1 hour 40 minutes maximum to complete alcohol phenol and ether. Yes, handwritten notes. I will share PDF on my Telegram, on my new Telegram channel, which I have given you the ID of that. Come on. Let me know. Should I start? Break will be after this chapter. Break will be after this chapter. Come on. So let's get started. There will be no break till unless and until alcohol phenol ethers are completed. Now, so first is methods of preparation of alcohols from alkenes by acid catalyzed hydration. Have a look. This is acid catalyzed hydration. This is an alkene. This alkene on treatment with water in presence of acid, protonic acid, generally H2SO4. Now, have a look. This is acid catalyzed, what we call hydration. Now, what will happen over here? For that, you should know the mechanism. Of this reaction, because this reaction is very, very important. It's like this. Alkene plus H2O and H positive. Can I write down it as H3O positive in this fashion? Can I say like this? So first of all, protonation of alkene takes place. That means water will be lost. Over here. First of all, protonation of alkene will take place, and this step is the slowest step and the rate determining step of the reaction, and hence here it will be a carbocation, formation of carbocation. After that, rearrange if possible. That means intermediate of the reaction is carbocation. Now, after that, my dear lovely students, now this water will act as a nucleophile. This nucleophile will attack on this, and we will get RCH, CH3. Then it is OH H with a positive charge on oxygen. Finally, what will happen? Finally, what will happen? H positive will be lost. That means first H positive have been used. Finally, it has been lost. That means H positive will act as a catalyst. H positive will act as a catalyst. We will get this one. Now listen carefully. So from this to this, can I say OH has been added to this and H has been added to this? That means this is an addition reaction taking place via classical carbocation. So this is simply electrophilic addition reaction. Point number one, electrophilic addition reaction. Point number second, intermediate of this reaction is once again, intermediate of this reaction is carbocation. Point number third, listen carefully. Point number third, this is unsymmetrical. If this is unsymmetrical, addition takes place according to Markovnikov's rule. That means major product will be Markovnikov's product, but exceptions are there. Already discussed in chapter before this. Now, exception to Markovnikov's or the major product according to Markovnikov's rule, exception will be only if rearrangement takes place or if this alkene is having, say electron withdrawing group attached to it. I hope this is clear. This is acid catalyzed hydration. After that, listen carefully. Oxymercuration, demercuration. Once again, this is indirect hydration of alkene. This is indirect hydration of alkene. Listen. What is oxymercuration, demercuration? Oxymercuration, demercuration is reaction of alkene with, say mercuric acetate and H2O. Then NaBH4, OH minus. Whenever you saw this type of reagent, you have to add water at that time across carbon-carbon double bond according to Markovnikov's rule. So there is no rearrangement. Now add, I mean to say simply what we call water according to Markovnikov's rule. That means negative part goes to this, positive part goes to this, because there is no rearrangement. Hence, product will be always according to Markovnikov's rule. So this is the major product. This is the Markovnikov's product. No rearrangement takes place over here. After that, hydroboration-oxidation. Very, very simple reaction. Alkene. Once again, indirect hydration of alkene. But diborane or borane is the reagent number one. Reagent number two, H2O2 in presence of basic medium. And remember, whenever you are having these types of reagents, we have to add water across carbon-carbon double bond according to anti-Markovnikov's rule. No rearrangement will be over here. This reaction takes place via cyclic, say four-membered cyclic transition state. So there will be no rearrangement. Add water, but according to anti-Markovnikov's rule. That is like this. Anti-Markovnikov's rule, it's like this. That means we have added H and OH across carbon-carbon double bond. But remember, we have to add H and OH from the same side because this is syn addition. That means if H is added on wedge side, that means above the plane, this is OH should also be added from wedge side, that means above side. So this is what we call hydroboration-oxidation, indirect hydration of alkene, but according to anti-Markovnikov's rule. After that, from carbonyl compounds by reduction of aldehydes and ketones. Have a look. This can be aldehyde, this can be ketone. So if it is an aldehyde or if it is a ketone, listen carefully. What we have to do is, we have to simply, listen carefully. We have to simply break one, bond between carbon and oxygen. Add hydrogen to carbon and add hydrogen to oxygen. Then what will be the product? Product is very, very simple now. It becomes CH and it becomes OH. So alcohol is obtained. Now the question is, with the help of which reagent we can convert aldehyde to, alcohol. This is alcohol. Now, if it is an aldehyde, it will result in the formation of primary alcohol. So remember, aldehyde during this reaction gives 1 degree alcohol. And ketone during this reaction gives secondary alcohol. Listen carefully and try to remember these points. And now, what are the reducing agents? Point number one, reducing agent is number one, lithium aluminium hydride. Number second, you can use sodium borohydride. Number third, you can use Na in alcohol, sodium in alcohol. Number four, you can use H2 in presence of catalyst. Catalysts can be generally nickel, platinum, palladium, Raney nickel, so on and so forth. So these are the reducing agents in general which converts aldehyde to alcohol. After that, by reduction of ester, listen, this is ester, have a look, this is ester, and we have to convert ester into alcohol. Now, how to reduce ester? Listen, just try to break this bond, give H to this, H to this. After that, let me use another, color. Let me use another color. Break bond between carbon and hydrogen, give H to this and H to this. That means it becomes RCH2OH. So one will be RCH2OH, and this part will be R prime OH. That means it will become R prime OH. Very, very simple. Now the question is, this is ester. From ester, we get alcohols. Now, what are the reducing agents which can convert ester to alcohol? Point number one, lithium aluminium hydride. Point number second, you can use, H2 in presence of catalyst. You can use nickel, you can use platinum, you can use palladium, you can use Raney nickel, you can use copper chromite. Its formula is CuOCuCr2O4. That means, or you can say it is Cu2Cr2O5. You can use nickel, you can use platinum, palladium, so on and so forth. You can use, point number third, sodium in amalgam. Sodium in alcohol. You can use this as reducing agent as well. But listen, my dear lovely students, if you use this one, and you produce alcohol from, ester, by using this, then reaction is known as Bowald-Blank reduction. Reaction at that time is known as Bowald-Blank reduction. So what is Bowald-Blank reduction? Reduction of ester by using sodium in alcohol to alcohol is known as Bowald-Blank reduction. But remember one more point, NaBH4 cannot reduce ester. For example, if you are having a compound like this, then what will happen? If here I will write down lithium aluminium hydride, and here I will write down sodium borohydride. Lithium aluminium hydride can reduce ester as well as this ketone, because this is ketonic functional group, this is ester functional group. So it will result in the formation of this one. Break this bond, give H and H to this, so that will be the product. And after that, break this bond, give H to this, so it is ethanol and it is CH2OH. So this is CH2OH plus ethanol, ETOH. So this is with the help of lithium aluminium hydride followed by hydrolysis or lithium aluminium hydride. Okay, what about this? It will result in the formation of this one, but there will be no effect on ester functional group. So sodium borohydride cannot reduce ester, so you can write down like this. After that, reduction of carboxylic acid. This is carboxylic acid. Now you have to reduce it. Now listen how to reduce it. Just try to break this bond, give H to this, H to this. Break this bond, give H to this, H to this. So this is RCH2OH will be the product. So RCH2OH will be the product, and side product will be this one, order. Now this can be done, number one, by using B2H6 followed by hydrolysis, or you can use lithium aluminium hydride followed by hydrolysis. We generally do not use H2 in presence of catalyst. We do not use sodium in alcohol. We do not use sodium borohydride. Now, so we generally use these things. But remember, lithium aluminium hydride is a very expensive reagent. It's an expensive reagent. That is why it is used to prepare, to synthesize special chemicals only. So it is used to synthesize. It's used to synthesize special chemicals only. Special chemicals only. Now, if we want to prepare this alcohol from acid, but not by using lithium aluminum hydride, then we should use diborane, or we can convert this into that like this. First of all, we will react this carboxylic acid with alcohol, but that alcohol should not be this one, or this alcohol is obtained by any other method. So first of all, we will react these two, and then esterification takes place. Water will form over here. First, water will be lost and ester will be formed over here. So this ester is obtained after that. We know in case of ester, we have to break this bond, give H to this and H to this, break this bond, give H to this, give H to this. That means after reduction, we will get RCH2OH, and this is the alcohol which we want to prepare from this one. This is the alcohol which we want to prepare from this, but indirectly. After that, R prime OH will also be obtained. Now, with the help of which we can use lithium aluminum hydride, but we do not want to use lithium aluminum hydride as that is an expensive reagent. So you can use number one, H2 in presence of catalyst, or you can use sodium in alcohol. So this is very, very simple. Very, very simple. After that, from Grignard's reagent, have a look. Aldehyde and ketone is this one. This on treatment with Grignard's reagent, can I write down Grignard reagent like RMgX? R is having negative part, MgX positive part. So this negative part can also act as a nucleophile. This negative part of Grignard reagent can act as acid, it can act as a nucleophile, but it prefers, it can act as a base, it can act as a nucleophile, but it prefers to act as base if there is acidic hydrogen, but there is no acidic hydrogen. So in presence of dry ether, what will happen? A normal nucleophilic addition reaction will take place. Nucleophilic addition reaction takes place. So it will result in the formation of this O minus. Then MgX positive will be attracted to this. I hope this is clear. This is known as addition product because R and MgX has been added across carbon double bond oxygen. So this is addition product, also known as adduct. This adduct has been obtained, but listen. Now what will happen? We will do hydrolysis of this. Then give H positive to this and OH to this. So we will get like this. We will get like this. We will get alcohol from aldehyde or ketone. This is aldehyde or this is ketone. It can be aldehyde or it can be ketone, and this is simply alcohol. Now, dear students, listen carefully. If aldehyde is formaldehyde, my dear lovely student, if aldehyde is formaldehyde, we get, that means this is H, we get primary alcohol at that time. If aldehyde is other than formaldehyde, that means R is not equal to H. This is aldehyde, but this is not formaldehyde. That means once again, here it is R, it is H, then we get secondary alcohol. We get secondary alcohol. But if it is ketone, if we react ketone with Grignard's reagent and R is not equal to, say H, then we will get tertiary alcohol during this reaction. So try to remember these things. Try to remember these things. Try to remember these things. Adduct means addition product. I hope this is clear. After that, a reaction with ester. This is Grignard reagent, RMgX, partial negative, positive. Ester means RC double bond OOR. Now, this R, to distinguish this R and this R, let me write down prime over here, double prime over here. Then what will happen? Normal nucleophilic addition reaction first takes place. Nucleophilic attack, this bond will be broken. Now, this becomes R prime, C, this becomes O minus, to this O minus, MgX will be there. And this is OR double prime, and this is this R. Reaction takes place in presence of dry ether. Once again, this is an adduct, but Listen, my dear lovely students, this O minus will be back. I mean, say this O minus will form a double bond back, I mean, say form a pi bond with this carbon. That means it can form pi bond and this will be lost. Once this will be lost, as this is a good leaving group, here there was no leaving group. There was no leaving group. So it cannot form a pi bond. There was no leaving group because here either it was H or it was carbon. They are bad leaving groups. Now, this is a good leaving group as compared to carbon or hydrogen. So it will leave. So loss will be loss of, I mean say this R double bond, this O having negative charge and this MgX takes place. And it will result in the formation of R prime, then C, then it is double bond O, now single bond R. So it will be formed like this. After that, another molecule of RMgX will be used. Once again, this R in presence of dry ether will attack on this and we will get R prime, C, R. This is also R. This becomes O minus MgX. But there is no good leaving group over here because this is either R, this is, I mean say carbon, or this can be carbon or hydrogen. So what will happen? In presence of dry ether, once again, not in presence of dry ether, now we will simply hydrolyze this. Hydrolysis takes place. O minus becomes OH, so it will result in the formation of OH. Then it's R, and alcohol is obtained. Alcohol is obtained and side product will be MgX-OH. Now listen. This is an ester. This is an ester. From ester we get alcohol. So if this R prime is H, it is like this. It is like this. This is known as formic ester. Listen carefully. So can I say, if formic ester is there, we will get, that means R prime is H, we will get secondary alcohol. But if R, C double bond O, R double prime is there, but R prime is not equal to H, that means ester other than formic ester is there, then this is carbon, so we will get tertiary alcohol at that time. We will get tertiary alcohol at that time. Try to remember this. After that, methods of preparation of phenols. Number one, Dow's process. Can I say done in previous chapter? Haloarene is done in previous chapter. I mean say this Dow's process. From benzene sulfonic acid, have a look. This is benzene sulfonic acid. My dear lovely students. If this benzene sulfonic acid is treated with base and acid and base react together, water will be lost and we will get sodium salt of benzene sulfonic acid. So SO3Na will be formed. Now this SO3Na on treatment with, say for example, NaOH at a temperature of 523 to 573 Kelvin approximately, what will be the product over here? Side product will be Na2SO3. Na2SO3 will be lost and then phenol will be formed. Another NaOH will result in the formation of sodium phenoxide over here. So sodium phenoxide will be formed. Finally, my dear lovely students, acidification will take place. O minus will abstract H positive, NaCl will be lost. So we will get phenol over here. But listen carefully. This benzene sulfonic acid can be prepared from benzene by sulfonation. So next reaction from benzene diazonium salt. This is benzene diazonium salt. Simple reaction, benzene diazonium salt. Benzene diazonium salt is stable, but if temperature is greater than, listen carefully, if temperature is greater than 5 degrees Celsius, or we can simply say if we warm this, then it decomposed, then final product will be that N2 of benzene diazonium salt will be replaced by OH. So we will get phenol. Over here. I hope this is clear. Then from isopropyl benzene, what is isopropyl benzene? This is isopropyl benzene, my dear lovely students. Listen, This is isopropyl group. This is benzene, also known as cumene. This cumene on treatment with oxygen, that means upon oxidation at a temperature of 368 to 408 Kelvin, means high temperature. What will happen? Between C and H, oxygen is added in the form of peroxide. This is a free radical reaction. Free radical reaction takes place over here. So first of all, cumene results in the formation of cumene hydroperoxide. Cumene hydroperoxide is obtained first. Now, after that, this on treatment with dilute H2SO4 or dilute acid, you can say, at a temperature of 323 to 363 Kelvin, mechanism is something different. Now, listen carefully, you can remember a trick. Break this oxygen-oxygen bond, break this carbon-carbon bond. Oxygen-carbon bond will form a double bond, that means it will form acetone. And this bond and oxygen will form and it will result in the formation of phenol. So, product is phenol and side product is acetone, CH3, CH3 and then double bond O. I hope this is clear. I hope this is clear. Then after that, we will be having chemical reactions of phenols and alcohols. Remember, alcohol and phenol can act as nucleophile, but when they donate their lone pair of electron to electron deficient site, say for example carbocation, and oxygen will acquire a positive charge there, they finally will lose H positive, and in this fashion, alcohol and phenol will act as what we call, nucleophile. But alcohols in its protonated form can act as electrophile, not phenol, alcohol. Alcohol first accepts H positive, becomes protonated alcohol. Now this protonated alcohol can accept electrons from the nucleophile, so it can act as an electrophile at that time. So now different reactions in which it acts as a nucleophile and it can act as electrophile. Have a look. Reaction number 1 is reactions involving cleavage of O and H bond. O and H bond. We have to cleave O and H bond over here. Now, that means if O and H bond is broken, H positive will be lost. So, H positive, any species which donates H positive is known as an acid. So, these reactions simply, explain acidic character of alcohols and phenols. So, first of all, reaction with metal. Whenever your reaction of alcohol takes place with any metal, say for example sodium, potassium, magnesium, aluminium. So, whenever alcohol is reacted with metal, any metal, remember, it simply results in the formation of alkoxide of that metal to which reaction of alcohol takes place. That means if it is magnesium, then magnesium alkoxide. If it is aluminium, aluminium alkoxide. Here it is sodium, so sodium alkoxide is obtained and hydrogen gas will be evolved. Hydrogen gas will be evolved. Similarly, if phenol reacts with any metal, active metal, like sodium, potassium, magnesium, calcium, aluminium, then what will happen? Here it will result in the formation of phenoxide of that metal. Phenoxide of that metal, not it forms alkoxide of metal, it forms phenoxide of metal and hydrogen gas will be evolved. I hope this is clear. And hydrogen gas is evolved only if O and H bond is broken. Phenoxide or alkoxide is formed only if O and H bond is broken. When O and H bond is broken, H will be lost as H positive. That clearly indicates acidic nature of alcohol and phenol. But we know phenol is stronger acid as compared to alcohol. After that, there is esterification. What is meant by esterification? It's very simple. Listen carefully. If you are having a phenol or you are having an alcohol, that means you are having OH directly attached to aromatic ring or OH is not attached to aromatic ring. That means you are having an alcohol or a phenol. If it is treated with this one, carboxylic acid. If it is treated with carboxylic acid, listen carefully. If it is treated with carboxylic acid, then what will happen? OH from carboxylic acid and H from alcohol or phenol will be lost in the form of water. Let us suppose this is having O18, oxygen 18, then we will get AR, that means aromatic ring or alkyl part, then it's oxygen. and hydrogen of alcohol or phenol will be replaced by COR, means acyl group. So we will get like this. So what has happened in this reaction? What has happened in this reaction? Look towards the board. This hydrogen of alcohol or hydrogen of phenol has been replaced by acyl group. So we can simply say this is acylation. This is acylation reaction. But during this reaction, we can simply say R prime COOR or R prime COOAR. That means ester is obtained. So this is also known as esterification. So reaction of alcohol or phenol with carboxylic acid resulting in the formation of ester is simply acylation reaction of alcohol or acylation reaction of phenol, or this is simply known as what we call esterification reaction, and generally takes place in presence of HCl or H2SO4. But that esterification which takes place in presence of HCl, esterification is known as Fischer-Sippier esterification. That esterification is known as Fischer-Sippier esterification. That esterification which takes place in presence of, say, HCl. And one more thing, rate of esterification, that means rate of this reaction, is inversely proportional to the size of, listen carefully, size of what we call this, size of this R prime in COOH in R prime COOH, or it is inversely proportional to size of R in ROH. That means whether the size of alkyl part increases or whether the size of R prime of this, say alkyl part of carboxylic acid increases, rate of esterification decreases. Remember this. That means the best known example of carboxylic acid in which esterification will be fast is formic acid. If this R is H, smaller value of R. And this will be methanol. That means methanol and formic acid will form ester very, very fast. Rate of esterification will be very fast. Similarly, if you are having an, say a phenol or an alcohol, and then it is treated with acid chloride. It is treated with, say for example, acid chloride, or it is treated with phenol. Once again, what will happen? Acylation will take place. Once again. And reaction generally takes place in presence of base. Now listen carefully. This H will be replaced by COR. Alcohol, H of alcohol or phenol will be replaced by COR, that means acyl group, either from acid chloride or from acid anhydride. So the product will be once again R, ARR, then it is O, then it will be COR. That means ester plus HCl. Here once again it will be an ester. That means esterification takes place. Formation of ester means esterification, or replacement of H by acyl is also known as acylation. So plus R prime COOH. So this is the reaction. But remember. In case of acid chloride, if R is CH3, then RCOCl becomes simply what we call, or let me write down over here like this. If COR, RCO, if R is CH3, then this part, then RCO becomes CH3CO. This part is known as acetyl. That means if H is replaced by COCH3, reaction is known as acetylation at that time. So similarly, if number one, R is equal to this. If R is equal to C6H5, then R is equal to C6H5, then R C double bond O becomes C6H5 C double bond O. And at that time, this is known as benzoyl. So listen carefully. If H is replaced by COR, reaction is acylation. But if COR is COCH3, reaction is acetylation. If COR is COC6H5, reaction is known as benzoylation. That means this acylation can be either acetylation, it can be either benzoylation. It can be either benzoylation. But listen carefully. If you are having like this, if you are having like this, if you are having like this, you are having an acidic hydrogen containing compound. Acidic hydrogen containing compound means that compound which can donate H positive, acidic hydrogen containing compound, for example phenol. And if it is treated with benzoyl chloride, C6H5 COCl, C6H5 COCl is known as benzoyl chloride. If any acidic hydrogen containing compound like phenol is treated with benzoyl chloride in presence of aqueous NaOH, that means in presence of base, what will happen? This H will be replaced by benzoyl group. That means benzoylation will take place. So listen carefully. Benzoylation will take place. So this is simply a benzoylation reaction. This is simply a benzoylation reaction. This is simply a benzoylation reaction. Why benzoylation? Benzoylation of what? Benzoylation of phenol. What is phenol over here? Any acidic hydrogen containing compound. It is basically acidic hydrogen containing compound. So I will write down, instead of phenol, it can be any acidic hydrogen containing compound or any acidic compound, any acidic hydrogen containing compound. So listen carefully, listen carefully. Benzoylation of phenol or any acidic hydrogen containing compound. And by the way, another product will be HCl, but instead of, this is acid, this is what, this is base and acid reacts together and will result in the formation of water and NaCl after that. So that's why I have not written side products, but side products will be water plus NaCl. So remember, benzylation of any acidic hydrogen containing compound by using benzoyl chloride in presence of aqueous NaOH is known as Schotten-Baumann reaction. That is known as Schotten-Baumann reaction. So this is one of the examples of Schotten-Baumann reaction. This is one of the examples of Schotten-Baumann reaction. Okay. After that, my dear lovely students, a reaction of alcohol or phenol with Grignard's reagent. This is alcohol, this is phenol. Have a look. This is alcohol and phenol. If AR is attached, OH is attached to aromatic ring, it is phenol. If R is attached to OH, it is, it is what we call alcohol. So it can be alcohol or a phenol. On treatment with Grignard's reagent. Grignard reagent is this one, R having negative part, MgX positive. To differentiate this R and this R, let me write down R prime over here. What will happen? What will happen? This will act as a base and it will abstract this H positive. So it will result in the formation of R prime H. So alkane will be obtained, but R is of Grignard reagent and H is of either alcohol or phenol in presence of dry ether. Plus, then this is Mg. On one side it's X, on another side it is either OR or OAR. That means this is the what we call alkoxy magnesium halide or aryl oxy magnesium halide, but this is alkane. That reaction, listen carefully, a reaction of Grignard reagent with any acidic hydrogen containing compound to form alkane, whether it is water, alcohol, phenol, any acidic hydrogen containing compound to form alkane is known as Zerevatinov's reaction. So this is Zerevatinov's reaction. So this is Zerevatinov's reaction. After that, reactions involving cleavage of carbon-oxygen bond in alcohols. Reaction with HX done in previous chapter. What was the previous chapter, by the way? Haloalkanes and Haloarenes. Reaction of alcohol with HX. That was the first preparation of, haloalkane. After that, reaction with PCl5 done once again in previous chapter. PX3, this is also done in previous chapter. Then SOCl2, Darzens reaction, once again done in previous chapter. Done today itself. Then dehydration of alcohol. Listen carefully. This is alcohol. Simple example. This is alcohol. This is alcohol. This alcohol is a primary alcohol. This is a primary alcohol. Have a look. If this primary alcohol is treated with, say for example, H2SO4, at a temperature of 443 Kelvin, what will happen? Intramolecular dehydration takes place. Intramolecular dehydration takes place. Within the molecule, dehydration takes place, and it will result in the formation of a product. Secondary alcohol like this. Secondary alcohol like this. On treatment with, say for example, you can use basically acid. Let me write down over here. This reaction is basically an example of E1 reaction. E1 reaction. Point number one. Point number second, intermediate of this reaction is carbocation. Point number third, reagents used generally are H2SO4 or H3PO4. Now listen carefully. Secondary alcohol on treatment with H3PO4, you can use H2SO4, you can use H3PO4, suppose, but not 100%, only 85%. And at a temperature of 440 Kelvin, what will happen? First, OH will be lost, carbocation will be obtained, there will be no rearrangement. Finally, the position which is attached to carbocation will lose H positive, and it will result in the formation of an alkene like this. Once again, intramolecular dehydration takes place. Similarly, if we use tertiary alcohol, listen carefully. Tertiary alcohol on treatment with H3PO4, but only 20% of H3PO4, and that too at a temperature of 358 Kelvin. That means lower temperature is decreased. That means reaction goes towards normal conditions. Now, here from this to this drastic condition, from this to this normal condition, what will happen? Once again, tertiary alcohol undergoes dehydration, intramolecular dehydration, resulting in the formation of this one. So, it is clear from these reactions that 3-degree alcohol is more reactive than 2-degree. 2-degree is more reactive than 1-degree. Why is it so? Have a look. So, first of all, let me write down among alcohols. Reactivity order will be 3-degree, greater than 2-degree, greater than 1-degree. By what? But why is it so? Let's have a mechanism, have an eye on mechanism, because mechanism for this reaction is very important. So let's try to understand mechanism with the help of tertiary alcohol. You can use any other alcohol. So have a look. First of all, this is an alcohol, tertiary alcohol. First of all, either from, say carboxylic, what we call sulfuric acid, or H3PO4 phosphoric acid, H positive, it will abstract H positive. First of all, it becomes protonated alcohol. That means from poor leaving group, it becomes a good leaving group. First of all, it becomes a good leaving group. So this is a good leaving group. It was a poor leaving group. Now, what will happen? This leaving group will leave. And it will result in the formation of a carbocation. And this step, formation of carbocation, is actually the rate determining step of the reaction. This is slowest of the step of the reaction, rate determining step of the reaction. Now, so tertiary alcohol forms tertiary carbocation, secondary alcohol forms secondary carbocation, primary alcohol forms primary carbocation. So can I say tertiary carbocation is more stable as compared to secondary carbocation, as compared to primary carbocation in general? That's why it will show reaction much faster as compared to this, So that means basically this is dependent on, this rate of dehydration is actually directly proportional to stability of carbocation formed from alcohol in RDS. That means the alcohol which can form more stable carbocation in RDS can undergo dehydration much faster as compared to the alcohol which forms less stable carbocation. Now, We have to rearrange, as carbocation is the intermediate, we have to rearrange that if possible. But here, there is no rearrangement possible in this reaction. If rearrangement here is not possible, then finally what will happen? H positive will be lost. That means this will act as a catalyst, but it will be lost from any position which is attached directly to carbocation. Therefore, the product formed over here is CH2 double bond C, CH3, CH3. Only one product will be obtained over here. Why? Because all these carbons, all these hydrogens these hydrogens are of one type, single type. All these hydrogens are same type hydrogens. So any one hydrogen can be lost. But if carbocation is attached to that carbon which is having different types of hydrogens, then those all hydrogens will be lost and different products will be obtained. So here only one product will be obtained. I hope this is clear. For example, example is like this. For example, we are having this one. For example, we are having this one. For example, we are having this one. We are having an alcohol like this. And suppose it is treated with H positive. What will happen? What will happen? First of all, it gets protonated. Upon protonation, it will result in the formation of this one. It will result in the formation of this one. And here, this is a good living group. It will be lost in the form of water. So this group will be lost in the form of a water and it will result in the formation of a carbocation. Now, we have to check whether rearrangement occurs or not. But we know here there will be no rearrangement. As there will be no rearrangement, we will check the hydrogens or the carbons to which this carbocation is attached. These are of similar type of different type. These are different types. This is CH3, this is CH2, different types because surroundings is different, This hydrogen, this carbon contains only 2 hydrogens, so this is poor. This hydrogen contains 3 hydrogens. In comparison to this is rich. Now what will happen? During elimination, hydrogen will be lost. Hydrogen will be lost, H as H positive. If it is lost from poor, product formation, pi bond formation takes place over here. If it is lost from rich, then pi bond will be formed like this. So this is formed when rich position loses hydrogen. So this is Hofmann product. And this, when this rich position, poor position will lose hydrogen, it will form a Sedgwick product. So once again, this is elimination. But remember, this is that elimination which takes place via formation of carbocation known as E1 reaction. And in E1, major product is always Sedgwick. In E1, major product is always Sedgwick. So this is dehydration by using acid or acidic dehydration. This is what we call acidic dehydration of alcohols. I hope this is clear. Now, if I give you one example, one question. Suppose you are having this one. You are having this alcohol. You are having this alcohol. Listen carefully. And you are having this alcohol. And you have to tell me which alcohol undergoes dehydration very fast, or what will be the rate of dehydration among these alcohols. Listen, first of all, we will remove OH. We will form a carbocation. We will form a carbocation over here. We will form a carbocation over here. And we know the most stable carbocation is this one because of more resonance after this. Because this is also having resonance. No resonance is present over here. It's stable only due to inductive effect or hyperconjugation. So this will be the stability order. Stability order of carbocations. Now, this forms more stable carbocation. Hence, dehydration, rate of dehydration, or what we call reactivity. This will be simply rate of dehydration among these alcohols will be simply, it is 3, 2, 1. Why? Why third shows much faster reaction as compared to second as compared to 1? Because third can form more stable carbocation as compared to second as compared to first. So this is what we call dehydration of alcohols. After that, it is oxidation of alcohol. Listen carefully. Listen carefully. This is alcohol. This is alcohol. This is alcohol. This is alcohol and this is its alpha position. 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 What we have to do during oxidation? We have to break this bond and we have to break this bond. That means during oxidation of alcohol. Remember, during oxidation of alcohol, we have to remove hydrogen, that means dehydrogenation. Removal of dihydrogen from alcohol means dehydrogenation. That means you have to remove hydrogen. Dehydrogenation. Take? Okay, now, if dehydrogenation takes place, that means oxidation takes place. So, oxidation takes place, that clearly means this bond has been broken. This bond has been broken. Oxygen and carbon forms double bond. So, it will result in the formation of this. It will result in the formation of this. Now, listen carefully. Listen carefully. Listen carefully. This oxidation can be done. This oxidation can be done by using, either strong oxidizing agents or mild oxidizing agents. Listen, either by using strong oxidizing agents or by using mild oxidizing agents. First, let's take examples of strong oxidizing agents. That means, first of all, let's take oxidation of alcohols by using strong oxidizing agents. First of all, you should remember strong oxidizing agents. You should remember the list of strong oxidizing agents. Let me write down list over here. Strong oxidizing agents. List of strong oxidizing agents. Number 1, KMnO4, whether alkaline, whether neutral, whether acidic. Number 1. Number 2, K2Cr2O7, generally acidic. Say for example H2SO4. Number 3, CrO3 aqueous means CrO3 plus water, means H2CrO4, known as chromic acid. Remember. Number 4, it is CrO3 plus H2SO4, known as Jones reagent. Remember. Number 5, HNO3. Number 6, KMnO4 hot. Or number 7, you can use K2Cr2O7 hot. Hot KMnO4, hot K2Cr2O7. These are generally the strong oxidizing agents which you generally use during your, organic chemistry. Now, have a look. If you are having a primary alcohol, listen carefully. What is the trick? You have to remove. What? Have a look. You have to remove, by using strong oxidizing agents, you have to remove simply oxygen. You have to remove hydrogen attached to oxygen and hydrogen attached to alpha carbon. Then you have to form a double bond between alpha carbon and oxygen. So let me show this like this. Have a look. It's like this. C, then it is H, this was alpha, and we have broken this bond, and this bond was carbon hydrogen bond of alpha carbon. Now this is primary alcohol. Now tell me, what will be the product? During, this is, try to remember. Now, I will now tell you clearly what will happen during this reaction if strong oxidizing agent is present. Now, it will result in the formation of RCHO double bond O. RCH double bond O. That means this is an aldehyde. But listen carefully. When strong oxidizing agent is there, we cannot obtain aldehyde. Aldehyde is not obtained isolated if strong oxidizing agent is there, because strong oxidizing agent further oxidizes this aldehyde to carboxylic acid. It will result in the formation of this one. So this aldehyde group is converted to carboxylic acid. That means if strong oxidizing agent is there, first it will result in the formation of aldehyde if this is primary alcohol, but aldehyde is further oxidized to carboxylic acid if strong oxidizing agent is used. So that means primary alcohol on treatment with strong oxidizing agents gives us carboxylic acid. Listen carefully. It will result in the formation of carboxylic acid. Primary alcohol will result in the formation of carboxylic acid. But if carboxylic acid is methanoic acid, it is further oxidized to carbon dioxide and water. But other acids are not further oxidized by using strong oxidizing agent. But if it is, say methanoic acid, if it is HCOOH, that means formic acid, it is further oxidized to carbon dioxide and water. Point number second. Point number second. Listen carefully. Point number second. If you have secondary alcohol, then in presence of strong oxidizing agent, what will happen? First of all, bond between OH and bond between CH of alpha position. Alpha position is that position to which functional group OH is attached. It will result in the formation of a ketone. Then reaction will stop. That means ketones do not undergo further oxidation. But if vigorous oxidation of ketone takes place, in presence of strong oxidizing agents, then reaction takes place as follows. That means listen carefully. Primary alcohol forms basically carboxylic acid in presence of strong oxidizing agents. But secondary alcohols form ketone in presence of strong oxidizing agents. But if this strong oxidizing agent is used and after that ketones are not further oxidized in general. But under vigorous conditions, under strong conditions at elevated temperatures, if strong oxidizing agent is used, then ketones are further oxidized. At that time, ketones are further oxidized. That means, have a look. Ketones do not undergo further oxidation. That means ketones basically resist towards further oxidation. But if vigorous oxidation, that means if oxidation takes place at elevated temperature by using strong oxidizing agents, then ketones are further oxidized and reaction takes place as follows. For example, my dear lovely students, suppose our ketone is like this. Suppose our ketone is like this. Let me write down over here. Ketone is like this. R and this is R. Listen carefully. Ketone is like this. Can I say this is symmetrical ketone? And if I write down like this, this is RCH2, C double bond O, then CH2 and then R prime. And let me write down R is not equal to R prime. R and R prime, they are different. That means this is unsymmetrical ketone. Now what will happen? One secondary alcohol results in the formation of ketone in presence of strong oxidizing agents, reaction will stop. But if we use vigorous conditions, under drastic conditions, suppose strong oxidizing agents are there, but conditions are vigorous, or drastic conditions are there, vigorous conditions. Under vigorous conditions, no need for vigorous condition as per primary alcohol is concerned, as per aldehyde is concerned. Why? Because it can undergo easily with the help of strong oxidizing agents. But if we want to oxidize ketones will be oxidized only and only by strong oxidizing agents if we use vigorous conditions or if we use drastic conditions. Then what will happen? Listen, we have to break this bond. How many carbons, the fragment containing number of carbons you have to convert this into carboxylic acid, this part into carboxylic acid. That means R remains as it is, this one, and convert this into carboxylic acid. So let me show some example over here. Let me write down like this. CH3 and CH3. Listen carefully, my dear lovely students. So this part will become 2 carbon. This part is having 2 carbons, so it will form 2 carbon carboxylic acid which contains 2 carbon. That means CH3COH. And this carbon contains only that carboxylic acid which contains only 1 carbon. But this contains only 1 carbon and it will result in the formation of formic acid. But I have already told you that formic acid is further oxidized to carbon dioxide and water. So let me erase this one and let me write down carbon dioxide and water. So the product over here is carbon dioxide and water plus acetic acid. Similarly, if I take an example like this is also a symmetrical ketone. Listen carefully. We have to break C bond. I mean say carbon of alkyl and carbon of C double bond O bond. We have to break this. So which one will we break? This and this, both are identical. So any one, either this one or this one. So this is having 3 carbon fragment, this is 3 carbon fragment, and this is 2 carbon fragment. That clearly means this acid will be of 3 carbons. That means CH3, CH2 and COH. This acid will be of 2 carbon. One will be CH3, another will be COH. So this will be the product. But have a look. This is an unsymmetrical ketone. Let us suppose this is carbon number 1. Let us suppose this is carbon number 2. This is carbon number 3. As this is unsymmetrical, we can break carbon 1 and 2. We can break carbon 1 and 2. Then it will form RCOH. Then RCH2COH. If carbon 1 and carbon 2 is broken, then RCOOH plus, I mean say R prime CH2COH will be formed. But this is formed only by breaking, by cleavage of carbon 1 and carbon 2. This is formed by cleavage of carbon 1 and carbon 2 because this forms RCOH, RCH2COH, that one. If we break carbon 2 and 3, then it will result in the formation of RCH2COOH plus this one is R prime, then it is R prime COOH. But this will be formed only by cleavage of, I mean say C2C3 bond. C2C3 bond. I hope this is clear. But listen carefully. Here it is up to us whether we will break this bond or break this bond. We can form the products. But here it is not up to us because this cleavage of this bond results in the formation of one type of acids and cleavage of this bond can form another type of acid. That's why in case of unsymmetrical alkenes, in case of unsymmetrical ketones, cleavage is done according to Popoff's rule. Which says that smaller alkyl group stays with C double bond O group. So the major product will be like this. Have a look. If we write CH3, C double bond O, CH2, CH3, this is larger group, this is larger alkyl group, this one is smaller alkyl group around C double bond O group. So whenever strong oxidizing agents under vigorous conditions are used, then under vigorous conditions there will be oxidation of ketone as well by using strong oxidizing agents. Now The major product will be by breaking this bond. Why? Because smaller alkyl group should stay with C double bond O. So this is 2 carbon fragment means CH3COH. This is 2 carbon fragment means CH3COH. That means our major product will be CH3COH. But if I break this bond, then it will become CH3CH2COH, and this will become carbon dioxide plus water because it is HCOH. HCOH in presence of strong oxidizing agent will be carbon dioxide and water. I hope this is clear. I hope this is clear. I hope this is clear. So, how secondary alcohol undergoes oxidation, how primary alcohol undergoes oxidation, this is clear to you. This is clear to you now. So, primary alcohol results in the formation of carboxylic acid. Secondary alcohol results in the formation of ketone in presence of strong oxidizing agents. But if vigorous conditions are used, then by using strong oxidizing agents, ketones can be further oxidized, but symmetrical ketones can be further oxidized like this. But as per unsymmetrical ketones are concerned, we have to oxidize them by using Popoff's rule so that major product will be obtained. After that, my dear lovely students, have a look. Tertiary alcohols are not further oxidized by using strong oxidizing agents directly. But we can first treat them. Treat these, tertiary alcohols with acid or protonic acid, and then we can oxidize them. What is meant by this? Have a look. Directly we cannot oxidize tertiary alcohols, but my dear lovely students, if your tertiary alcohol is like this, you can treat it with H positive, say for example protonic acid. So first of all, it will simply result in the formation of OH2 positive, that will be lost, carbocation will be formed, then E1 reaction takes place, and finally we will get alkene like this. Similarly, if your alcohol is like this, if tertiary alcohol is like this, then the major product during E1 reaction will be a SEDZ product over here, and product will be like this: CH3C, CH3, double bond CH, single bond CH3. So first of all, it will be lost in the form of OH2 positive, carbocation will be formed over here, then H positive will be lost either from this or from this, but this is a poor form SEDZ product, so I will write down this major product. So first of all, tertiary alcohol, convert tertiary alcohol to alkene, otherwise there will be no oxidation of tertiary alcohol. So you can convert tertiary alcohol to alkene. Tertiary alcohols cannot be oxidized by using strong oxidizing agents, but it can be converted to alkene. Then this type of alkene can be oxidized by using strong oxidizing agents. How? We know this. We have already discussed such type of reactions in, alkenes in 11th class session. So just break this, convert double bond CH2 into CO2 plus water, and product will be like this. One will be carbon dioxide plus water, plus this part will become ketone. So it will be like this. And here, break this bond, this will become ketone and this will become acid. So it will become like this. One will become ketone, and another, this part, it will become COH. CH3 is attached to that. So CH3COH will be the product. So we can convert alcohol to ketone or what we call carboxylic acid, but not directly. We have to convert them first into alkene. After that, strong oxidizing agent will, oxidize. So tertiary alcohols are not oxidized by using strong oxidizing agents. Primary alcohol are oxidized by using strong oxidizing agents to carboxylic acid via aldehyde. Secondary alcohols are oxidized to ketone, but if vigorous conditions are used, then ketone is further oxidized to carboxylic acid, otherwise not. Tertiary alcohols will not oxidize at all. Now, after that, second is oxidation of alcohols. Oxidation of alcohols by using mild oxidizing agents. Have a look. What are mild oxidizing agents? Try to remember their list. Mild oxidizing agents. First mild oxidizing agent you have to remember is Serret's reagent. What is Serret's reagent? Serret's reagent is CrO3 and pyridine C5H5N in the ratio of 1:2. And solvent here is also pyridine C5H5N. Second is Tollens reagent. Same formula, CrO3 and C5H5N, that means pyridine, in the ratio of 1:2, but here solvent is dichloromethane. After that, another is Khoury's reagent, also known as pyridinium chlorochromate, short form PCC. Okay, now formula is CrO3, C5H5N and HCl in the ratio of 1:1:1, or we will write down C5H5NH positive and then CrO3 having a negative charge, pyridinium chlorochromate. Fourth, pyridinium dichromate, short form is PDC, and formula is simply C5H5NH whole twice and then Cr2O7 having 2 negative charges. This is having 1 positive and it's twice, so 2 positive, 2 negative neutralized. After that, 5, CrO3 but anhydrous, it's anhydrous form. So these are the mild oxidizing agents which you have to remember, and remember such oxidizing agents will simply convert primary alcohol, like this, secondary alcohol like this, to corresponding aldehyde and ketone. Have a look. Just break this bond and break this bond at alpha carbon. Break this bond and break carbon hydrogen at alpha carbon. Here product will be like this. RCH double bond O, that means aldehyde. So mild oxidizing agents will convert primary alcohol to aldehyde and secondary alcohol to ketone, and reaction will stop after that. That means these are the reagents with the help of which primary alcohol can be converted to aldehyde and reaction will stop. Similarly, secondary alcohol can be converted to ketone and reaction will stop. And the best and common among these reagents to convert primary alcohol to aldehyde and secondary alcohol to ketone is this Khoury's reagent. This is the most common reagent used for conversion of primary alcohol to aldehyde and secondary alcohol to ketone. Tertiary alcohols do not show this reaction. Tertiary alcohols are not oxidized by using mild oxidizing reagent. So there is no reaction. So tertiary alcohols are not oxidized by using mild oxidizing agent or by using strong oxidizing agents directly. After that, action of hot copper on alcohols. Have a look. This is what we call a primary alcohol. This is a primary alcohol. This is a secondary alcohol. Let's take an example of a primary alcohol like this, CH3. This is a secondary alcohol. Say for example, this is secondary alcohol. Simple example of secondary alcohol. And this is simple example of tertiary alcohol. What you have to do is, when it is treated with copper at high temperature, that means copper at a temperature of 573 Kelvin, what will happen? In case of primary alcohol, this and this bond will be broken. In case of secondary alcohol, this and this bond will be broken. But in case of tertiary alcohol, there is no hydrogen at alpha position. That is why you have to remove hydrogen from beta position. So let me show like this. You have to break beta hydrogen and carbon bond and alpha and OH bond. That means here H and OH has been lost. That means water will be lost. Here dehydrogenation and dehydrogenation will take place. So primary alcohol will form aldehyde and will undergo dehydrogenation. Secondary alcohol will form ketone and dehydrogenation will take place. But tertiary alcohol will simply undergo dehydration. Tertiary alcohol will undergo dehydration. So with the help of oxidation or with the help of action of hot copper, we can distinguish, with the help of final product, we can distinguish whether our starting material is primary alcohol, secondary alcohol or tertiary alcohol. That's why distinguishing test with the help of oxidation and action of hot copper, we can distinguish primary, secondary and tertiary alcohols as well. After that, my dear lovely students, there is the reaction of phenol, aromatic electrophilic substitution reactions. Number one is halogenation. Remember, halogenation of phenol is solvent dependent. It is solvent dependent. Listen carefully. It is solvent dependent. That means if halogenation of phenol, say for example bromination or chlorination, if halogenation of phenol takes place in, say for example, non-polar solvent or sometimes less polar solvents, then halogenation takes place at ortho or at para position. That means normal substitution, mono substitution will take place. Monohalogenation or monobromination or monochlorination will take place. And major product will be simply what we call para product. Major product will be para product. This is in non-polar solvents. But if solvent is polar protic solvent, say for example, we take bromine water, chlorine water, bromine and solvent is water. So bromine water or chlorine water, then polybromination or polychlorination will take place depending upon whether it is bromine water or chlorine water. That means here monobromination will not take place. Here bromine as an electrophile goes to both ortho positions and para position. That means this will be the product. Polybromination takes place. Now the question is, why is it so? Because in case of water, this water will oxidize, water will ionize this one. Have a look. Water will ionize phenol to phenoxide ion. But this will not change phenol to phenoxide ion. You have two oxygens. One is phenol, in which oxygen donate electron towards ring. Another is phenoxide ion having more electron density. It will simply donate electrons much more towards ring and it will activate this ring or increases electron density of this ring much more as compared to this. Because of that, electron density of ring is very, very increased in case of this one when water is solvent, because it is phenoxide at that time. Hence, electrophile goes to each and every position where electron density has been increased. That's why polyhalogenation takes place. In nutshell, this polyhalogenation product 2,4,6 tribromophenol shows a white precipitate. That's why with the help of this reaction, we can distinguish phenol from alcohol. Suppose we have a doubt that whether test tube contains a phenol or alcohol, we will add bromine water. If white precipitate occurs, it is phenol because it will result in the formation of 2,4,6 tribromophenol. Otherwise, if it is alcohol, there will be no white precipitate. So with the help of bromine water test, we can distinguish alcohol and phenol. After that, it is sulfonation. Have a look, listen carefully. Actually, sulfonation of phenol is actually temperature dependent. So sulfonation of phenol is actually temperature dependent. Halogenation was solvent dependent. This is temperature dependent actually. What is meant by that? Listen carefully. Basically, sulfonation takes place. We know this is ortho-para directing group. Sulfonation takes place at ortho as well as para position. That means sulfonation, sulfonic acid group will be introduced to ortho as well as para, But listen carefully. Sulfonation reaction is actually it is actually what we call a reversible reaction at low temperature. This will become the major product. Why? Because its activation energy is low. To form this product, there is a very less activation energy. That means energy barrier is less. But for this, activation energy is high. Now tell me, if activation energy is high, that means at low temperature this cannot be obtained. That's why at low temperature this will become the major product and this product will be formed easier. That means this is kinetically controlled product. Rate of formation of this product will be faster as compared to this, as activation energy is low for this. Okay, but this is what we call its activation energy is high. But among these products, this is thermodynamically controlled product because this is much more stable product. If this is thermodynamically controlled product at high temperature, if I increase the temperature, say for example 373 Kelvin, at high temperature this can be formed, this can also be formed, but this is much more stable as compared to that. That means at high temperature this will become the major product. And even we know these are in equilibrium with respect to each other as they are reversible reactions. So can I say at high temperature, if I increase the temperature of this at 373 Kelvin, it prefers to go to this side because this is the major product. So in nutshell, at high temperature, this is major, at low temperature, this is major. Otherwise, both products can be obtained. Now, if this sulfonic acid is taken in excess, say for example 2 moles of this, then sulfonic acid SO3H can be introduced at ortho as well as para position. That means at that time 2,4-disulfonic acid, say phenol 2,4-disulfonic acid can also be obtained. Now nitration. Phenol can undergo nitration by using dilute HNO3 or concentrated HNO3. By using dilute HNO3, listen carefully, by using dilute HNO3, it will result in the formation of orthonitrophenol and paranitrophenol. But paranitrophenol will be the minor product and this will be the major product because of intramolecular hydrogen bonding or chelation. And as this is what we call showing, this paranitrophenol can form an intermolecular hydrogen bonding with other, paranitrophenols, but this will undergo intramolecular hydrogen bonding. So this is steam volatile as compared to this one. Now, after that, this is minor, this is major. Okay. Now, listen carefully. Here, this is major at high temperature. This is major at low temperature. But in this case, this is minor, this is major. So, ortho product is only major, only if in case of ortho there is, chelation or intramolecular hydrogen bonding. Similarly, if phenol is treated with nitric acid, concentrated nitric acid, or either concentrated nitric acid or with nitric acid in presence of H2SO4, one and the same, then it will result in the formation of, at that time, 2,4,6-trinitrophenol known as picric acid. But listen carefully, this nitric acid, concentrated nitric acid, is also an oxidizing agent. So as it is also an oxidizing agent, it can oxidize this phenol to benzoquinone, and there are many terry products as well. So there are terry products as well. I mean to say, if these products are also obtained, that means the yield of this will be obviously low. So this will be having lower yield. Now, if this is having lower yield, we want to increase its yield, then these products should not be obtained. That's why nowadays what we will do is, we first of all treat this with sulfuric acid so that it undergoes sulfonation. Once it undergoes sulfonation, it forms phenol 2,4-disulfonic acid. Phenol 2,4-disulfonic acid. Then it is treated with nitric acid. Now, this nitric acid will now replace these SO3H groups and provide NO2. And by doing so, it will result in the formation of picric acid. But this picric acid will now be of high yield because there will be no oxidation of this ring when sulfonic acid groups are there. So this will be in high yield now. So without sulfonic acid groups, without these electron withdrawing groups, it can undergo oxidation. But in presence of these sulfonic acid electron withdrawing groups, there will be no oxidation of ring further. So that's why with the help of this, we can increase the yield. After that, Kolb's reaction. What is Kolb's reaction? Have a look. Whenever you are having phenol, if this phenol is treated with NaOH, we will obtain first of all sodium phenoxide. That means sodium salt of phenol. And when this sodium salt of phenol is treated with carbon dioxide, number one, followed by acidification, it will result in the formation of salicylic acid. Orthohydroxybenzoic acid as the major product. So salicylic acid becomes the major product. Para-hydroxybenzoic acid can also be obtained, but as minor product. Now, you have to remember its application. If salicylic acid, my dear lovely students, is treated with, if it is treated with acetic anhydride, say for example like this, now what will happen? This H of OH group attached to, say this ring, that means phenolic part of salicylic acid will lose H positive, and instead of that H positive, this COCH3 group is added to this. That means H will be replaced by acetyl group. That means acetylation will take place. Once acetylation will take place, it will result in the formation of acetyl salicylic acid. So what is this? This is acetyl salicylic acid, or this is 2-acetoxy-benzoic acid. So this is acetyl salicylic acid, or this is 2-acetoxy-benzoic acid, or this is aspirin. And remember, the use of aspirin is used as an analgesic. That means pain reliever. It can be used as a pain reliever, or it can be used as antipyretic, or you can say febrifuge. That means it brings down the body temperature. I hope this is clear. After that, we will be having another application of this Kolb's reaction. This salicylic acid can be treated with phenol, and then in presence of POCl3, phosphorus oxychloride will act here as a dehydrating agent. Water will be lost. OH of this phenol and H of this acid, and it will result in the formation of this one, this COO of this, and then C6H5 of this. This is known as phenyl salicylate. Phenyl salicylate, commonly known as Salol. And this Salol is used as an intestinal antiseptic. Intestinal antiseptic. I hope this is clear. I hope this is clear. Now, after that, if you are having this salicylic acid on treatment with alcohol, say for example methanol, this, what will happen? Have a look. In presence of H2SO4 concentrated, once again it will lose water molecule. But water molecule will be lost, OH will be lost of this alcohol and H of this acid, and it will result in the formation of methyl salicylate, COOCH3. This is known as methyl salicylate. And this methyl salicylate is basically the chief or major constituent, of oil of wintergreen. That is why, because this is the major constituent of oil of wintergreen, that's why methyl salicylate is also known as oil of wintergreen, and it is used as a flavoring agent, in perfumery. I hope this is clear. After that, we will be having very important reaction, that is Reimer-Tiemann reaction. And what is Reimer-Tiemann reaction? Have a look. Whenever you are having phenol, and if this phenol is treated with chloroform in presence of basic medium at a temperature of approximately 340 Kelvin, now what will happen? First of all, it will result in the formation of this one. And this is basically an intermediate. So this is an intermediate. After that, this intermediate is treated with NaOH. It is treated with NaOH. Okay, now have a look. It is treated with NaOH. That means it undergoes hydrolysis. So it results finally in the formation of this one, ONA, and this group becomes CHO. And finally, this is treated with acid. And this O- will abstract H from this, and we will get orthohydroxybenzaldehyde or salicylaldehyde as the major product. So salicylaldehyde is the major product of Reimer-Tiemann reaction. But remember, the electrophile of this reaction, as this is electrophilic substitution reaction, electrophile of this reaction is dichlorocarbene. And let me tell you, here electrophile is carbon dioxide. Here, this is the electrophile of the reaction. In Kolb's reaction, this is the electrophile. And in Reimer-Tiemann reaction, dichlorocarbene acts as an electrophile. But you have to remember one more point. If CCl4 is used instead of CHCl3, then major product will be salicylic acid instead of salicylaldehyde. So during Reimer-Tiemann reaction, if instead of CHCl3, instead of chloroform, we use CCl4, then instead of salicylaldehyde, salicylic acid will be the major product. After that, coupling reaction. It's very, very simple reaction. Have a look. It's a reaction of benzene diazonium salt, say for example benzene diazonium chloride, for example like this. This on treatment with phenol, results in the formation of basically a dye, but this reaction takes place at a pH of 9 to 10, that means in presence of basic medium. What will happen? This N, this diazonium ion, this acts as an electrophile and this will attack, say phenol, or this will couple phenol at para position. That means it will replace hydrogen. So this is the electrophile of the reaction, this diazonium ion. So this is the electrophile and this electrophile will be attached to this phenol at para position. But if phenol is not having any hydrogen at para position, that means if any other group other than hydrogen is present at para position, at that time we say phenol is blocked at para position, then this coupling will take place at ortho position with respect to phenol. So here it will take place at para position, but if para is blocked, then coupling takes place at ortho position. This is known as 4-hydroxy or para-hydroxy azobenzene. And this is an azo dye. This is an azo dye. Its color is orange color. That's why it's also known as orange dye. And with the help of this reaction, we can distinguish alcohol and phenol under the name orange dye test. Because suppose we are having doubt between alcohol and phenol, suppose we are having doubt that this test tube contains either alcohol or phenol, what will we do? We will simply add benzene diazonium salt in basic medium. If orange color takes place, so this is phenol. If orange color does not appear, then it is alcohol. So with the help of this reaction, we can distinguish alcohol and phenol as well. Because one reaction was bromine water test, this is another reaction. Then a third reaction is condensation of phenol with phthalic anhydride. Have a look. This is phthalic anhydride. This is phthalic anhydride. This is phthalic anhydride. Now, this on treatment with phenol. This on treatment with phenol. This on treatment with phenol. In presence of sulfuric acid, what will happen? Have a look. Simply, water will be lost. Water will be lost in presence of sulfuric acid. And it will result in the formation of this one. It will result in the formation of this one. That means phenol will be attached to this phthalene group with the help of amines at para position. Will be attached to this phthalene group at para position. This is known as phenolphthalein. And this acts as an indicator. It acts as an indicator during acid-base titration. Acid-base titration. It acts as an indicator during acid-base titration. Remember this. And remember one more point. If NaOH is added to this, then it will result in the formation of a pink color. Basically, it results in the formation of a compound like this. It becomes O minus, it becomes O minus first, then it O minus forms a double bond like this. Let me show you the product. This is pink color, and this pink color is because of this. It is because of this. It is because of this. Have a look. It is because of this. It is like this. Let me erase this. Let me show double bond over here. Let me show double bond over here so that it's much more understood to you. It's much more understood to you. Have a look. Have a look, my dear lovely students, have a look. Very, very, very simple. Very, very, very simple. have a look. So it is like this. So it is like this. So it's like this. This becomes O minus first, then that O minus forms a double bond over here. O minus forms double bond over here. This double bond will move towards this, and this double bond will form like this. It will be a double bond over here. Double bond over here, and this bond will be broken. That means it becomes like this. It becomes like this. So it is because of this. It is because of this. Color is due to this. This is having pink color. But if NaOH is added now, if NaOH is taken here in excess, if NaOH is taken now in excess, then there will be no color at all. So there will be no color at all. So this reaction can be used to distinguish alcohol and phenol once again. But this reaction will be shown by that compound which contains phenolic OH group. That means this test is known as phthalene dye test. This is known as phthalene dye test. Alcohols do not show this reaction. It first becomes pink color, then colorless. What happens after that? OH will be attached to this. OH will be attached to this, and this bond will form once again a ring like that. That means it will be once again an aromatic ring. It becomes O minus aromatic ring. This becomes single bond, and OH will be over here. So no need to write this or that. You just remember this phenolphthalein. After that, NaOH, adding NaOH, it becomes pink color. After that, if much more, say if NaOH taken in excess, then it becomes colorless. This test is known as phthalene dye test, and with the help of this test, we can distinguish, say phenols from rest of the compounds, or we can distinguish phenol from alcohols with the help of this. And phthalene dye test is used to identify phenolic OH. Then after that, reaction with ferric chloride. This is phenol. On treatment with ferric chloride, listen carefully. What will happen? What will happen? What will happen? Simple. It is Cl minus will abstract H positive. Another Cl minus will abstract another H positive from another phenol. Another CH will abstract another H from another phenol. So it will result in the formation of 3 times HCl. So it becomes C6H5O having a negative charge, that 2 thrice, and Fe tri positive. So it is ferric phenoxide whose color is violet. So violet color ferric phenoxide is obtained, but it is obtained only if it is ferric phenoxide. That means once again this reaction can be used to distinguish phenol and alcohol, because phenol forms violet color, alcohol does not form violet color at all, under the name ferric chloride test. After that, reaction of phenol with zinc dust. Reaction of phenol with zinc dust, very simple reaction. Reaction of phenol with zinc dust. When it is heated with zinc dust, we get benzene. We get benzene and zinc oxide. Very simple reaction. After that, oxidation of phenol. Remember, if phenol is oxidized by using sodium dichromate in acidic medium, or potassium dichromate in acidic medium, or chromic acid, then we will get benzoquinone or parabenzoquinone as the product. Then distinction between alcohols, oxidation reaction already done. Then action of hot copper already done. Lucas test already done. Now next is Victor-Meyer's test. What is Victor-Meyer's test? It is test to distinguish primary, secondary and tertiary alcohols. That means it will distinguish whether our alcohol is primary, secondary or tertiary. How? Have a look. First of all, we will add simply iodine in red phosphorus. Second, we will add nitrous, this silver nitrite. Third, we will add nitrous acid. Fourth, we will add NaOH. If after adding these, blood red coloration or red coloration takes place, blood red color appears. If blood red color appears, our alcohol is primary alcohol. If blue color appears, our alcohol is secondary alcohol. if, my dear lovely students, colorless product is obtained at that time, alcohol is 3-degree alcohol. So that is why this Victor Mayer test is also known as RBC test. Why RBC? Red, blue and colorless test. I hope this is clear. After that, litmus test, distinguishing test between alcohol and phenol. Phenols are much more acidic than alcohol. That's why phenols turn blue litmus to red. But alcohols have no effect on blue litmus paper. Now, orange dye test already done. Ferric chloride test, that is already done. Phenols can show this, but alcohols cannot show. Bromine water test is shown by phenol, not by alcohol. Phthalene dye test is shown by phenol, not by alcohol. Now, next is Lieberman's nitroso test. What is Lieberman's nitroso test? Listen carefully. When we treat phenol with nitrous acid, but this nitrous acid is actually formed within the reaction when it is treated with, when NaNO2 is treated with H2SO4. Both will form HNO2 and this HNO2 will react and NO will be, this electrophile goes to para position of phenol and we will get para-nitrosophenol. Listen carefully. Now this can undergo hydrogen migration. Now hydrogen can migrate from this oxygen to this oxygen. Then we will get a product like this. This is known as quinone oxime. This is para-nitrosophenol. Now, then phenol further reacts with that quinone oxime. Now it's N double bond, then it is this ring, then here double bond and O in presence of H2SO4. Once again, a dehydration takes place like this. Dehydration takes place and we get a structure like this. In which this N double bond and then this ring, this is known as indophenol. After that, my dear lovely students, if indophenol is treated with NaOH is base, it will abstract this H as H positive. It will abstract OH minus will abstract this H in the form of water and we will get sodium salt of this indophenol. So I will write down NaO and then this phenol ring, this benzene ring like this. After that, it's having N, then it's having double bond, then it's having this ring like this. So this is sodium salt of indophenol and its color is blue. But this color appears only if we take phenol. That's why sodium salt of indophenol will be obtained. But this reaction is not shown by, alcohol. With the help of this, we can distinguish alcohol and phenol, and this reaction is known as Lieberman's nitroso test. Then we will be having ether. Only 3 reactions are there, so this chapter will be completed. Now have a look. Now first is by dehydration of alcohols, but remember this dehydration will be now intermolecular dehydration. Because intramolecular dehydration results in the formation of alkene, and that is an E1 reaction that is already been discussed. Now intermolecular dehydration, have a look. If you are having an alcohol like this, primary alcohol, and if alcohol is taken in excess, so let me write down one more alcohol molecule. Alcohol is basically taken in excess and it is treated with H2SO4. Alcohol is taken in excess, treated with H2SO4, at a temperature of approximately 413 Kelvin. Now, what will happen? Ether formation takes place. A symmetrical ether will be formed. A symmetrical ether will be formed. Symmetrical ether will be formed. Listen carefully. Symmetrical ether will be formed. And rate of this reaction will be simply 1 degree, then 2 degree, then 3 degree. Rate of the reaction will be this one. 3 degree will not show, say this reaction will not form ether at all, or will show very less, but the rate of reaction will be very less. So primary alcohols are considered as best method to prepare this symmetrical ether with the help of this reaction. After that, Williamson's synthesis. What is meant by Williamson's synthesis? Listen carefully. It is actually reaction of alkoxide or reaction of phenoxide. You can use sodium or you can use potassium. So let me write down sodium phenoxide, sodium alkoxide. But it is reaction of alkoxide or phenoxide. It can be sodium, it can be potassium with alkyl halide. With alkyl halide. Listen carefully. And this is simply SN2 reaction. This is simply SN2 reaction. This is an example of SN2 reaction. Listen. If this is an example of SN2 reaction, that means this R prime can never be what we call tertiary alkyl halide. Tertiary alkyl halide do not show SN2 reaction, or this alkyl, this group can never be aryl or vinyl halide, because aryl or vinyl halides also do not show this reaction. Now, what will happen? This will attack and this will leave. That means NaX will be lost over here. Similarly, this will attack, it will act as a nucleophile, and this will act as an electrophile, so NaX will be lost. Then, what will happen over here? ROR prime. Similarly, what will happen over PHOR? That means ethers will be formed. So this is ether, this is ether. So what is Williamson's ether synthesis, or what is Williamson synthesis? It is simply alkoxide, reaction of alkoxide or phenoxide with alkyl halide resulting in the formation of ether, and it is SN2 reaction. It is an SN2 reaction. That means the rate of alkyl halide towards this reaction will be simply, it will be simply 1 degree greater than 2 degree greater than 3 degree, because we know during SN2 reaction, if steric crowding is increased, then reaction will be very slow. I hope this is clear. I hope this is clear. Now, after that, have a look. If we take simple example like this, CH3CH2X, this is 1 degree alkyl halide. This is a 3 degree alkyl halide. Have a look. This is 1 degree alkyl halide. And this is 3 degree alkyl halide. When, my dear lovely students, when alkoxide or phenoxide is treated. Now, I have written alkoxide, you will try phenoxide. Instead of R, you have to write down pH. That's the only difference. Now, what will happen? What will happen? What will happen, my dear lovely students? If we want to perform Williamson synthesis, we know that is SN2 reaction. That is SN2 reaction. So this is SN2. This is SN2. But we know this alkoxide will attack this position, alpha carbon, and X will be lost. So it will become CH3CH2, O and R, CH3, CH2, O and R. This R can be any alkyl group. It can be any, aryl group as well. Now, so ether will be obtained. But here, no Williamson synthesis takes place. No ether formation takes place. No ether formation takes place. Because ether formation takes place via SN2 mechanism. As this is tertiary alkyl halide do not show SN2 reaction. So no ether formation takes place. Now, what will happen? Now, what will happen, my dear lovely students? Have a look. That means this cannot act as a nucleophile. If it cannot act as a nucleophile, it will act as a base. Have a look. Have a look. Now, it can act as a base. That means it will abstract hydrogen now. It will abstract hydrogen now, but from beta position. From one of the beta positions, it will abstract hydrogen. That means it becomes ROH. This electron pair will form a double bond between alpha and beta position and X will be lost. That means there will be no SN2 reaction, but this reaction is E2 reaction. That means in presence of alkoxide, this tertiary alkyl halide undergoes E2 reaction, and the product from this substrate is CH2. That means alkene, double bond C, single bond CH3 and single bond CH3. Plus side products will be ROH and NaX. So, can I say, to prepare ether during Williamson synthesis, primary alkyl halide is best substrate, but tertiary alkyl halide is not, because it cannot form ether. If it undergoes reaction, it undergoes E2 reaction instead of SN2, it will form alkene, not ether. After that, if we talk about secondary alkyl halide, what will happen over here? This RO minus Na positive, that means this alkoxide, this nucleophile can act as a nucleophile and it will attack on alpha position. But by doing so, it simply shows SN2 reaction, and product of this reaction will be CH3, CH, and then this is CH3, and to this C, OR will be attached, and side product will be NaX. That means here ether is formed, but when this acts as a nucleophile, this CH3 and CH3 electron cloud will repel electron cloud of this one. That means it can face electronic repulsions, steric repulsions when it acts as a nucleophile. That means it can also act as a base. It will try to act as a base, because by acting as a nucleophile, it will feel steric repulsion. So by acting as base, it will abstract this hydrogen, and this is at terminal position, so there will be no repulsion. So it will form this product by E2 reaction as well. So it can show SN2 as well as E2. So by showing E2, it will form alkene. It will form this alkene, CH2 double bond CH, CH3, and then ROH and NaX. Now tell me, can I say then, instead of these two reactions, can I write this reaction like this? RONA, that means alkoxide, whenever treated with, I mean to say, secondary alkyl halide, it can form this product as well as this product. That means it can form both the products. Let me write down both the products over here. This product is according to SN2 and this product is according to E2. Both products can be obtained when alkoxide is treated with secondary alkyl halide. But remember, this product is because of E2. But product formed because of E2 this product is formed because of E2 only if this alkoxide acts as a base. And when alkoxide acts as a base, there is no steric repulsion. But if alkoxide acts as a nucleophile, that means product formation of this, I mean say ether, due to SN2 only takes place if it acts as a nucleophile. And it acts as a nucleophile means it simply, there will be little bit steric repulsion, I mean say, which this alkoxide or nucleophile is facing when it acts as a nucleophile. So once it acts as a nucleophile, it's facing steric repulsion, but if it acts as a base, there is no steric repulsion. That means it will prefer to act as a base. So this will become the major product and this will become minor product. Now tell me. Secondary alcohols can form ether, but lesser in amount. Tertiary alcohols do not form ether at all. Primary alkyl halides easily form ether. Primary alkyl halides easily form ether. Tertiary will not form ether at all. Secondary alkyl halides form ether but lesser in amounts. That is why primary alkyl halides are considered best reagent, best substrates, after that secondary, after that tertiary. But we can say tertiary even not show this reaction at all. I hope this is clear. Now, after that, we will be having another reaction, that is chemical reactions of ether. A reaction of ether with HX. Have a look. This is ether. This is an ether, but this is an aliphatic ether, open chain ether, and that too symmetrical open chain ether. So this is symmetrical aliphatic ether. Now have a look. Whenever you are having symmetrical aliphatic ether and it is reacted with HX at high temperature, say for example 373 Kelvin, what we have to do is just break oxygen carbon bond, one of the oxygen carbon bonds. Which one? This one or this one? It's up to us. Give H to O and give X to this carbon. So what will be the product? Very, very simple. Product will be ROH plus product will be RX. Let's take few examples. This is very important reaction, that's why. Let's take this example, CH3OCH3. If HX is treated, then at a temperature of 373 Kelvin, then what will be the product? Obviously, HI will be much more reactive as compared to HBr as compared to HCl. Now, what will be the product? Very simple. Just break this, give H to this, give X to this. So, the product will be CH3OH and CH3X. Simple. Simple, my dear lovely students. But sometimes there are alicyclic ethers. I mean, say cyclic ethers are there. Then what will happen? Same type of trick. You should use same type of trick because this is also symmetrical. This part and this part, they are identical. So this is symmetrical. So at high temperature, what will be the product? Just break this bond, give H to this, give X to this carbon. So the product will be like this. It will be OH, then CH2, 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 and then X. So the product will be like this. So this is if your symmetrical ether is given. Now, second, if unsymmetrical ether is there, ROR prime is there. That means if unsymmetrical ether is there, unsymmetrical aliphatic ether is there. If unsymmetrical aliphatic ether is there, if unsymmetrical aliphatic ether is there, have a look, have a look, have a look. If unsymmetrical aliphatic ether is there and you want to react it with HX, what will you do? Simple. Listen carefully, listen carefully. Here you have to remember these points. Point number one, if R is not equal to tertiary alkyl, if this R is not equal to tertiary alkyl and R prime is not equal to tertiary prime, is not also equal to tertiary alkyl, neither this is tertiary alkyl nor this is tertiary alkyl, then reaction takes place via SN2 mechanism and X is attached to, goes to, I mean to say, smaller alkyl group, goes to smaller alkyl group. If neither this is tertiary nor this is tertiary, reaction takes place via SN2 and just break bond of oxygen and carbon in such a way that give X to larger alkyl group. That means H to, I mean say OH to smaller alkyl group at that time. Point number two. If R is tertiary and R prime is not, or we can simply say R is not tertiary and R prime is tertiary, that means at least one of these alkyl groups is tertiary or both are tertiary. Then at that time reaction takes place via SN1 mechanism and at that time X goes to larger alkyl group. Give X to larger alkyl group at that time, or that alkyl group which forms most stable carbocation. Now have a look, have a look. Very, very, very simple. CH3O CH2 CH3, number one. CH3O CH CH3 CH3, number second. Number third, CH3O C CH3 CH3 CH3. Listen carefully, listen carefully. Very, very, very important reaction is this. Listen carefully. If HX is there, heat, HX and heat is there, HX and heat is there, have a look, have a look. Neither this is tertiary nor this is tertiary, so this is SN2. Neither this is tertiary nor this is tertiary, so SN2. This part is tertiary. So one of the alkyl groups is tertiary, or both are tertiary at that time, SN1. Now, what we have to do is, we have to check this is smaller alkyl group, this is larger alkyl group. X goes to smaller alkyl group. That means break bond between oxygen in smaller alkyl group. Give oxygen to this and give H to this. Break bond between smaller alkyl group. Give X to this, H to this, if it is SN2. And if it is SN1, give X to larger alkyl group. That means you have to break bond between larger alkyl and oxygen. Give H to oxygen, give X to, say larger alkyl part. So the product of this reaction will be CH3X plus, this becomes CH3CH2OH. This becomes CH3CH2OH. Similarly, what about this? This becomes CH3X and this becomes CH3, CH3 and then OH. What about this? What about this? This becomes CH3OH and then this part becomes CH3, C, CH3, CH3 and then X. I hope this is very, very much clear to you. Let me know, is this clear to you? Because this is very, very, very simple. Let me know. But this is very important reaction. Let me know, is this clear? If symmetrical ether is there, if unsymmetrical ether is there, is this clear? Is this clear? Is this clear? Let me know quickly. Let me know quickly. Let me know quickly. Let me know quickly, my dear lovely students. Tell me, is this clear? Okay, that is great. That is great. That is great. That's great. God bless you. God bless you. God bless you. Now, after that, if you are having a symmetrical ether, if you are having a symmetrical ether, listen. If you are having symmetrical aliphatic ether and if you are having unsymmetrical aliphatic ether, then, and if HX is taken in excess, if HX is taken in excess, then what will happen? If HX is taken in excess, then what will happen? Whether it is symmetrical, whether it is unsymmetrical, break this bond, give X to this, H to this. Break this bond, give H to this, X to this. Similarly, break this bond, give X to this, H to this. Break this bond, give X to this, H to this. I hope this is clear. Now tell me, what will be the product over there? What will be the product over there? Here product will be alkyl halide, but as this is symmetrical, both alkyl groups are identical, so I will write down twice plus H2O. What will be the product over here? This R and R, they are different, so I will write down Rx plus R prime X plus H2. This is very, very, very easy. For example, if you are having CH3OCH3 and you are having CH3OCH2CH3, then what will be the product if HX is taken in excess? What will be the product if HX is taken in excess? Excess. What will be the product? Very simple, very simple. Just break this, give this X and give H to this. Break this, give H to oxygen and X to carbon. Break this, give X to carbon, H to oxygen. Break this, give H to oxygen, X to carbon. So here product will be twice CH3X plus water. And my dear lovely students, here it will be CH3X plus CH3CH2X plus water. I hope this is clear. I hope this is clear. After that, if we are having aromatic ether in which oxygen is attached to benzene rings on both sides, remember, then there will be no reaction. Then there will be no reaction whether HX is taken in excess or not. There will be no reaction. Why is it so? Because it is not easy to break oxygen and carbon bond because of resonance, as this bond is strong due to partial double bond character. So there is no reaction at all. Similarly, If your aromatic ether, by the way, let me tell you, aromatic ether means that ether in which oxygen is directly attached to aromatic ring, at least on one side. If aromatic ether is such that on one side it is aromatic ring, another side it is alkyl part, then it's not necessary that aromatic part only, it can be carbon double bond, it can be vinylic part as well. Then what will happen? If HX is treated, then what will happen? Or if HX is taken in excess, what will happen? Listen carefully. When aromatic ether is such that oxygen is attached to aromatic ring directly on one side and on another side it will be, say alkyl part, then you have to remember, you have to break oxygen carbon and oxygen alkyl part carbon. You have to break that and you have to give hydrogen to this, X to this. That means one of the products will be always phenol. One of the products will be always phenol. One of the products will be always phenol. Whether HX is taken in excess or HX is not taken in excess, because it will not react further, because this bond is not easy to break, because this bond is strong bond due to partial double bond, correct? But if you have this one, 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 then what will happen if it is treated with HX? Listen, we know that this, if we break this bond, it will form a very stable carbocation. That means this reaction takes place by SN1 and X goes to that position which forms more stable carbocation and H goes to this. Sir, you have told that in case of aromatic ether, one of the products is phenol, but this is not aromatic ether because oxygen is not directly attached to benzene ring, aromatic ring. So it will result in the formation of benzyl halide. It will result in the formation of benzyl halide plus, I mean to say, CH3OH. But if same reaction takes place with HX, same reaction takes place with HX, but in excess, this HX is taken in excess, then what will happen? Break this bond, give X to this, H to this. Break this bond, give X to this, H to this. That means it will result in the formation of benzyl halide. It will result in the formation of methyl halide and water. I hope this is clear. I hope this is clear. Now, this will be the last part of, say alcohol, phenol and ether. With the help of this chapter will be finished. Now, have a look. This is ether. In ether, this OR group is also ortho-para directing because it increases electron density of the ring at ortho and para position. Now, have a look. If it is treated, listen carefully. If it is treated with bromine in, say for example, acetic acid, what will happen? Br positive will go to that position whose electron density is rich, and that is ortho and para. That means we will get halogenation will take place, bromination will take place at ortho as well as para position, but major will be para. Major will be para. Major will be para because in ortho there will be repulsion. After that, if nitration takes place by using nitrating mixture, we know here electrophile will be nitronium ion. Here it was Br positive, here it will be electrophile will be nitronium ion, and that nitronium ion in the form of nitro group will be introduced at ortho as well as para position. And major product of this reaction is once again para product. So side product will be here HBr and here it will be water. Then if it is treated with alkyl chloride, in Lewis acid, electrophile will be R positive and we have to check whether rearrangement takes place or not. And finally, let me write down this as R prime. Finally, that R positive or R prime positive will go to ortho and para position. So let me write down R positive so that this R positive in the form of alkyl will be added to this benzene ring at ortho and para position. So this is simply alkylation reaction known as Friedel-Crafts alkylation reaction. This is bromination or halogenation. This is nitration. This is Friedel-Crafts alkylation. Finally, if it is treated with acid chloride or acid anhydride in presence of Lewis acid, electrophile of this reaction will be, say RCO, having a positive charge on carbon, that means acylium ion. Finally, this acyl group is introduced at ortho and para position of the ring. So this reaction is known as acyl group has been introduced. This is known as acylation reaction, known as Friedel-Crafts acylation. So Friedel-Crafts acylation, Friedel-Crafts alkylation, nitration, and then this is what we call halogenation. This is halogenation. Now, this is aldehydes, ketones, and carboxylic acids. So let's have a break till 9 p.m. So let's meet exactly at 9 p.m. and we will try to complete this chapter first, and after that we will try to complete this chapter. After that, after completing this chapter, I will give you a little break of 10 to 15 minutes as well, so that finally we will complete amine and diazonium salt chapter. So this is all for now. We'll be back exactly at 9 p.m. So let's meet at 9 p.m. Till then, you can have some food. So take care and bye-bye. But I would want you all guys to be present at 9, because aldehydes, ketones, carboxylic acid chapter is a very, 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 very important chapter. So take care. We'll meet exactly at 9 p.m. We'll meet exactly at 9 p.m. We'll meet exactly at 9 p.m. Okay. So welcome back again. But before we move ahead, let me know in the chats if I'm audible and visible to each and every one. Let me know in the chats, quick. Come on, come on, come on, let me know in the chats, quick. Okay, so without wasting much more time, it's a very, very important chapter. So first of all, methods of preparation of aldehydes and ketones are there. By oxidation of alcohols, this is already done in alcohols. Done in alcohols chapter. Now, after that, my dear lovely students, it's by dehydrogenation of alcohol. That means it is action of hot copper. It's action of hot copper on alcohol. Hot copper on alcohols. We have already discussed this reaction in alcohols as well. So done in alcohols. This is done in alcohols chapter. After that, from hydrocarbons by hydration of alkynes. Remember, this reaction is known as Kocherow's reaction. This reaction is known as Kocherow's reaction. And what is the reaction? Have a look. If you are having an alkyne and you want to add water, that means hydration of alkyne, then this reaction generally takes place in presence of HgSO4 and H2SO4 and at a temperature of 333 Kelvin. What will happen over here? Water will add across carbon-carbon triple bond according to Markovnikov's rule. So first it will result in the formation of enol, and this enol undergoes tautomerization and it will result in the formation of this keto product. I hope this is clear. After that, we have hydroboration-oxidation of alkynes. That means once again this is indirect hydration of alkynes. Now, reagents used here are B2H6 in presence of tetrahydrofuran. Number second, it is H2O2 followed by amines in basic medium. So whenever you are having these types of reagents, you have to add water across carbon-carbon triple bond, but according to anti-Markovnikov's rule. That means we will get RCH double bond CHOH. That means this enol will be first formed, then this enol will form a keto form and it will result in the formation of CHO over here. That means this will be the product. First of all, negative part of OH should go to this, but it will go to this according to anti-Markovnikov's rule. Okay. After that, by reductive ozonolysis of alkenes. First of all, remember, alkenes on treatment with ozone followed by zinc water. This is reductive ozonolysis. What we have to do is, we have to break carbon-carbon double bond. We have to give double bond oxygen to this, double bond oxygen to this. Then the product formation will be like this. Product formation will be like this. Let's take few examples over here. For example, you are having a structure like this. CH2 double bond CH2. You are having CH3 CH double bond CH2. Then what will be the product over here? What will be the product over here if reductive ozonolysis takes place? Very, very important reaction. Very, very important reaction. Now break this bond, give double bond over to this, double bond over to this. Break this bond, give double bond over to this, double bond over to this. That means here product will be formaldehyde, and that too 2 moles of formaldehyde. Here 1 will be acetaldehyde and another mole will be of formaldehyde. If these are given and you want to form the alkane from which you have to tell the alkane from which these aldehydes will be obtained, then remove these two oxygens and form a double bond, you will get this one. That means retro is also possible as per reductive ozonolysis is concerned. Similarly, if your product is like this, I mean say if reactant, if alkene is like this, then what will be the product during ozonolysis? What will be the product during ozonolysis? Similarly, if compound is like this, if alkene is like this, or it is like this, what will be the product? What will be the product? Just remove double bond. Just remove double bond, and instead of double bond, give double bond oxygen to both carbons. Similarly, give double bond oxygen and double bond oxygen to both carbons. Similarly over here, because there are two double bonds. So the product formed over here is like this. It is acetone, and that too 2 moles, because this is acetone, this is acetone. What about this one? It will result in the formation of this product. It will result in the formation of this product. And what about this one? This one will result in the formation of this product. And these are 2 moles of this. So this is very, very easy reaction. After that, there are methods of preparation of aldehydes only from acyl chloride. That means Rosenmund. It's Rosenmund. It's R-O-S-E-N. Rosenmund reduction. So what is Rosenmund reduction? If you are having aryl or alkyl, I mean say aliphatic or aromatic acid halides, acid chlorides, these on treatment with hydrogen in presence of Lindlar's or Rosenmund's catalyst, that means palladium barium sulfate with small amounts of sulfur or quinoline. Now what will happen? What we have to do is we have to replace Cl by hydrogen, then we will get aromatic or aliphatic aldehyde simply. So this reaction is known as Rosenmund's reduction. After that, from nitriles, have a look. Nitrile means cyanide. Whenever you are having cyanide, this cyanide on treatment with SnCl2, HCl. What will happen? First of all, it results in the formation of partial reduction takes place. It will result in the formation of imine first. So nitrile will form imine first, which upon hydrolysis form, just break this bond, add H and OH like this, H and OH like this. Both OH are present to same carbon, it will lose water molecule, and finally it will result in the formation of aldehyde. So in this way, aldehyde is obtained. This reduction is known as Stephen's reduction. This is known as Stephen's reduction. So in nutshell, this cyanide upon treatment with SnCl2 HCl followed by hydrolysis gets converted to aldehyde. Remember, cyanide group is converted to aldehyde group. Similarly, if you are having ester, if you are having cyanide, you can convert this cyanide to aldehyde by using another reagent, that is Di-H, diisobutyl aluminium hydride followed by hydrolysis. Then just convert Cn to CHO. That means you will get aldehyde with the help of Di-H also. Now, after that, if you are having an ester, or let me write down ester in this fashion. If you are having an ester, you can convert ester also to aldehyde by using Di-H followed by hydrolysis. That means you can convert ester to aldehyde as well. So you can convert cyanide to aldehyde, you can convert ester to aldehyde with the help of Di-H. You can also convert cyanide to aldehyde by using SnCl to HCl followed by hydrolysis. This reaction is known as Stephen's reduction. After that, from aromatic hydrocarbon by oxidation of methyl benzene, have a look. This is methyl benzene, that means toluene. When this toluene is treated with chromyl chloride, I mean say CrO2Cl2 in solvent, let's suppose CS2. First of all, what will happen? It will result in the formation of this one, OCrOHCl2. I mean, say OCrCl2, O and this H, this is whole twice. This is a brown chromium complex. Brown chromium complex. This upon hydrolysis. This upon hydrolysis simply results in the formation of benzaldehyde. And this reaction is known as Itard's reaction or Itard's oxidation. So this is Itard's reaction or Itard's oxidation. After that, my dear lovely students, when you are having toluene or methyl benzene, when this methyl benzene or toluene is treated with CrO3 in acetic anhydride, then what will happen? First, it will form a geminal diacetate, OCOCH3, whole 2. Geminal diacetate will be obtained, but this upon hydrolysis forms aldehyde group, that means benzaldehyde. So with the help of this, we can oxidize CH3 to CHO by using chromium trioxide in acetic anhydride. After that, if our toluene is treated with halogen, with chlorine, say for example, but it's a controlled side chain halogenation which takes place. Say for example, 2 moles of this is used. With the help of 1 mole, it will replace 1 hydrogen by 1 Cl. Another mole will replace another Cl. That means it will be CHCl2. So followed by hydrolysis. Say for example, I will take NaOH, aqueous NaOH. So OH will replace these Cl groups, that means CHOH whole 2 will be there. Finally, it will lose water molecule and we will get aldehyde like this. So benzaldehyde is also obtained in this reaction. After that, Gattermann-Koch reaction. What is meant by Gattermann-Koch reaction? A very simple reaction. Benzene on treatment with COHCl and AlCl3CuCl3. AlCl3CuCl. Then these will form this as an electrophile. Now this electrophile will be introduced into the ring. In nutshell, formyl group is introduced into the ring. That's why this reaction is also known as Gattermann-Koch formylation reaction, Gattermann-Koch reaction, Gattermann-Koch aldehyde synthesis. After this, my dear lovely students, we will be having another reaction known as Gattermann formylation reaction. The only difference here is, instead of CO, we use HCN over here. And here, the electrophile of the reaction is like this. It is HC double bond NH with a positive charge. This is the electrophile. This electrophile is introduced within the ring and it will form CH double bond NH, that means an imine, which upon hydrolysis yields simply this bond will be broken, H, and this will be OH, then H, this will be OH, and this will result in the formation of benzaldehyde. So it will result in the formation of benzaldehyde. This is also known as Gattermann, what we call aldehyde synthesis. After that, methods of preparation of ketones from acyl chloride. Have a look. This is acyl chloride. This acyl chloride on treatment with dialkyl cadmium, in presence of dry ether, what will happen? What will happen over here? This Cl and Cl, they will react with this cadmium, so CdCl2 will be lost. And then finally, this is RCOR prime ketone, so I will write down twice RCOR prime. That means ketone will be obtained when acid chloride or acyl chloride reacts with dialkyl cadmium. From nitriles, this is nitrile. When nitriles are treated with Grignard's reagent, RMGX, we know to differentiate this R from this R, let me write down R prime. Grignard reagent is having negative part, this is having positive part. It will act as a nucleophile, it will attack to this carbon and reaction takes place in this fashion like this. Have a look. In presence of dry ether, what will happen? What will happen? This R remain as it is, C triple bond becomes C double bond N is having negative charge, MgX will be attracted towards this negative charge, and R prime of, I mean say Grignard reagent will be added to this. After that, finally hydrolysis takes place. And this bond will be broken and we will add two OH groups to this and we will give hydrogens to nitrogen. So it is NH3 MgXOH. So it is NH3, it is MgXOH. And finally, this will form a ketone over here. C double bond O and R prime. So ketones are obtained when alkyl magnesium halide, I mean say Grignard's reagent, reacts with, I mean to say, nitriles. But remember, if RCN is equal to H, if it is equal to H, if this R is equal to H, that means if this R is equal to H, then we get aldehyde. At that time we get aldehyde instead of ketone. At that time we get aldehyde instead of ketone. Remember this as well. After that, from benzene by Friedel-Crafts reaction. This is Friedel-Crafts. By Friedel-Crafts, I mean say acylation. Have a look. This is benzene ring. Now, this is acyl chloride or acid chloride. Similarly. This is anhydride. So whether acid chloride or anhydride is used in presence of Lewis acid, say for example AlCl3, then what will happen? This Cl will be lost in the form of HCl, this will be lost in the form of RCOH. Then instead of this HCOR means acyl group is introduced. So we will get ketone. Similarly, we will get ketone over here. Here side product will be HCl, here side product will be RCOOH. But if benzene is treated with phosgene, I mean say carbonyl chloride, phosgene, a poisonous gas, in presence of Lewis acid, now what will happen? Here, twice HCl will be lost. I mean, say HCl will be lost and we will get benzophenone. That means a ketone. We will get benzophenone as well. That means ketones are obtained with the help of Friedel-Crafts acylation reactions. Now, chemical reactions of aldehydes and ketones. Number first reaction is nucleophilic addition reactions. What are nucleophilic addition reactions? I mean say what we have to remember in this is that rate of nucleophilic addition reactions depends on two factors. One is electronic factor. And another is steric factor. And remember, point number one or formula number one is rate of nucleophilic addition reaction is directly proportional to magnitude of positive charge present on carbon of C double bond O. This is, I mean say first formula. So magnitude is directly proportional to this one. So magnitude is directly proportional to this one of C double bond O. Second point, rate of nucleophilic addition reaction is inversely proportional to steric crowding. Steric crowding near C double bond O, because in case of aldehydes and ketones we have to check steric crowding near C double bond O group and magnitude of positive charge present on this carbon of C double bond O. Now by doing so we will simply say that rate of nucleophilic addition reactions among aldehydes and ketones will be simply, it will be formaldehyde first, then it will be aldehyde other than formaldehyde, that means aliphatic aldehyde other than formaldehyde, then it will be aromatic aldehyde, then it will be ketones. That means first it will be aldehydes, then ketones. First aldehydes, now ketones. In case of ketone, it will be aliphatic ketone first, then aromatic ketone in which C double bond O group is attached to alkyl as well as aryl or aromatic ring. After that, that ketone in which C double bond O group is attached to ketone on both sides. Remember this as well. After that, addition of HCN. Remember, addition of HCN. So HCN in presence of basic medium, what will happen? Have a look. This is positive part, this is negative part. This is positive part, this is negative part. Negative goes to positive, positive goes to negative. And you just break this double bond into single bond, then give negative part, that means Cn to this one, and positive part, that means H to this one. So we will get cyanohydrin. During this reaction. After that, it is C double bond O which has to be reacted with Na positive and OSO2H negative. So this is negative part, this is positive part. Now, here this is positive part, this is negative part. Give positive to negative, negative to positive. Then what will be the product over here? Product will be ONA and here it will be OSO2H. Finally, proton transfer takes place. And it becomes OH, and here it becomes OSO2Na. And remember, this OSO2H having a negative charge is considered bulkier nucleophile. It's considered as bulky nucleophile. SO3H is considered as, or OSO2H is considered as bulky nucleophile. That's why, if this is considered as bulky nucleophile, that's why aldehydes react with NaHSO3. Next point. Glucose does not react with NaHSO3. Remember this. Aromatic ketones do not react with NaHSO3. After that, aliphatic ketones which are sterically less crowded, for example, methyl ketones. That means those ketones in which there is CH3, in which there is COCH3 bond. Such ketones are sterically less crowded. So aliphatic ketones which are sterically less crowded, for example, methyl ketones, react with NaHSO3. Other aliphatic ketones which are sterically, very much crowded, they will not react with NaHSO3. After that, reaction with Grignard's reagent, it is done in alcohol. It's done in alcoholic part. Okay. Addition of alcohol. Have a look. If you are having an aldehyde like this, if you are having an aldehyde like this, and a reaction now takes place with, listen carefully, reaction takes place with a monohydric alcohol. This monohydric alcohol is not that strong nucleophile. That's why reaction takes place in presence of acid. Now what we have to do is, this is positive part, this is negative part, this is positive part, this is negative part. Give positive to negative, negative to positive. Now what will be the product? Product will be RCH. Give negative part to this, that means OR. Give positive part to this oxygen, that means OH. After that, if this is further treated with alcohol, that means if alcohol is taken in excess in presence of acid, then what will happen? Once again, this negative part will replace this OH, because OH will react with H positive, it becomes OH2 and it will leave, and instead of that, negative part of alcohol will come. That means it will result in the formation of this one. And this is geminal dialkoxy compound. Geminal dialkoxy compound obtained from, I mean say aldehyde. Geminal dialkoxy compound obtained from aldehyde is known as acetal. So whenever aldehyde reacts with monohydric alcohol, it forms acetal via hemiacetal. So if only 1 mole is used, we get hemiacetal. If alcohol is taken in excess, we get, I mean to say, acetal. Similarly, if aldehydes or ketones, react with ethylene glycol, say for example, it reacts with ethylene glycol, a dihydric alcohol, and reaction generally takes place in presence of C6H6, that means benzene and paratoluene sulfonic acid. Then here water will be lost, and we will get at that time cyclic acetal or cyclic ketal, depending upon cyclic acetal or cyclic ketal, that depends upon if aldehyde is taken, we get cyclic acetal. If ketone is taken, if ketone reacts with ethylene glycol or dihydric alcohol, we get cyclic ketal, not cyclic ketone, cyclic ketal. Cyclic geminal dialkoxy compound. After that, nucleophilic addition reactions followed by elimination of water molecule. Have a look. This is C double bond O. If this is treated with NH2G, that means ammonia derivatives. Ammonia are derivative of ammonia. Ammonia are its derivatives. Now at that time, remember. At that time, remember, reaction takes place in acidic medium. First of all, what will happen over here is it becomes OH and it becomes NHG. Now, first of all, nucleophile is added to this, and after that, it will lose water molecule, and it results in the formation of C double bond Ng. Now what is this G? G can be anything. If G is H, then this is ammonia. If G is R, then this is primary amine. If G is OH, then it is hydroxylamine. So all those values are here in this table. So you have to remember this reaction only. Whenever you are having ammonia and its derivatives reacting with carbonyl compound, you just remove hydrogens from this and oxygen from this, form C double bond Ng. So if this value of G, is, I mean say these, then reagent name will be this and product will be this and the name of the product will be this. But the only thing you have to remember is, if you react, I mean say this aldehyde or ketone with 2,4-DNP, that means 2,4-dinitrophenylhydrazine, also known as Brady's reagent, we will get 2,4-DNP, we will get 2,4-dinitrophenylhydrazone, and the color of that is yellow, orange, or what we call red. And this can be used as a distinguishing test between aldehyde, ketone and rest of the compound. So remember, 2,4-DNP test is given by, 2,4-DNP test is given by 1 aldehydes, another ketones, and number 3rd is formic acid. So you can distinguish these compounds from rest of the compounds with the help of this test, because With the help of color, you can simply say that what we call 2,4-dinitrophenyl hydrazone has been formed. You have to remember this table so that the value of G will be understood to you. Now, after that, it's reduction to alcohols. This is done in alcohol. Reduction to alcohols is done in alcohols. Reduction of aldehyde and ketone to alcohol by different reducing agents. Now then, Clemmensen reduction. Remember, it is C double bond O. That means either aldehyde or ketone upon, reduction, by using zinc amalgam, in acidic medium, say for example HCl. What we have to do is, we have to replace this C double bond O by CH2. Replace double bond O by H2. But this should be of either aldehyde or ketone. So whenever you are having aldehyde or ketone and reagents are, zinc amalgam in acidic medium, we get CH2. This is known as Clemmensen reduction. After that, if you are having C double bond O and then reagent is hydrazine, NH2, followed by, in basic medium, then it will first result in the formation of hydrazone. Finally, it will result in the formation of CH2 plus N2. Nitrogen gas is lost. This reaction is known as Wolff-Kishner reduction. After that, if you are having C double bond O of aldehyde and ketone, you can convert that into CH2. That means addition of hydrogen, removal of oxygen, reduction by using HI in presence of red phosphorus. After that, oxidation of aldehydes and ketones, that is done in alcohols. Oxidation of aldehydes and ketones done in alcohols, but which part is done? Let me tell you which part is done. Now, first of all, let me show you once again. This is an aldehyde. When strong oxidizing agent is used, this bond is broken, CH bond is broken, and we will get carboxylic acid. But ketones resist towards oxidation by using strong oxidizing agent. So no oxidation at all if ketones are used. But if ketones are used, ketones can be oxidized by strong oxidizing agents only in vigorous conditions. This has been discussed in alcohol. So this is done in alcohols. You can check that once again. Now, this is already done in alcohols. Now, listen carefully. As ketones do not show, oxidation easily, because in ketones we have to break CC bond, and CC bond is strong. But we can break CH bond. CH bond is weaker as compared to CC bond. That's why ketones only oxidize by using strong oxidizing agents, and that too in vigorous conditions. Ketones cannot be oxidized by mild oxidizing agents, but aldehydes can also be oxidized by mild oxidizing agents. Have a look. First of all, this is done. This is by using strong oxidizing agents. This is done in alcohols. Here, this is oxidation of aldehydes and ketones by using strong oxidizing agents. It's done. After that, by using mild oxidizing agents like Ag positive, that means Tollens reagent, Cu dye positive, that means Fehling solution, Benedict solution, then what will happen over here? Listen, this is reduction of Tollens reagent, because Tollens reagent itself gets reduced and it oxidizes aldehyde. Have a look. If you are having an aromatic aldehyde or aliphatic aldehyde, both aldehydes can reduce Tollens reagent, or Tollens reagent can oxidize both these types of aldehydes. Now, what is meant by Tollens reagent? It is basically AgNH3 whole 2 and having a positive charge, this type of cation, and anion is OH negative. These cations and anions came from Tollens reagent. So what is Tollens reagent? I will let you know. But first of all, what will happen over here? This aldehyde is oxidized to CO negative. And this Ag is precipitated, and this Ag got, it will get, deposited on the walls of the test tube in the form of a silver mirror. This silver will be deposited and it will behave like a mirror. So it is silver mirror plus 4 times NH3 plus oxygen here are 1 and 3, 4. Here 2 oxygens are there, so it is twice water. Now the question is, what is meant by Tollens reagent? Have a look. Tollens reagent means Ag, NH3, whole 2 and OH. It's an ammonical silver nitrate solution. Ammonical silver nitrate solution. It is obtained from silver nitrate and ammonia solution. It's obtained from this. That is why this is known as ammonical silver nitrate solution. I hope this is clear. I hope this is clear. But listen, it is shown by aldehydes, all types of aldehydes. It's not given by ketones. So let me write down over here. Point number 1. All aldehydes show this reaction. Whether aliphatic or aromatic, they will show this reaction. Point number 2. Ketones do not show this reaction. Ketones do not show this reaction. That's why this reaction can be used. This reaction can be used as a distinguishing test. As a distinguishing test between aldehydes and ketones. But remember these points as well. Alpha hydroxy ketones also show this test. Number 2, remember, hemiacetals also show this reaction. Point number 3, N-phenyl hydroxylamine or N-alkyl hydroxylamine also show this test. Number 4, remember. So, alpha hydroxy ketone, number 1 is aldehyde, show this reaction. Sorry. Number 2, alpha hydroxy ketones also show this reaction. Number 3, hemiacetal show this reaction. N-phenyl hydroxylamine or N-alkyl hydroxylamine shows this reaction. Formic acid shows this reaction. And number next is, what we call these, aldehydes, number 1, alpha hydroxy ketones, number 2. These all types show silver mirror test. These will show silver mirror test. Which one? Which one will show silver mirror test? This aldehyde, alpha hydroxy ketone, this and this. But if terminal alkyne is there, terminal alkyne also shows this test. Terminal alkyne also shows this test. But remember, it will not show silver mirror test. It will form white precipitate. It will form white precipitate on treatment with, what we call Tollens reagent. So aldehydes, alpha hydroxy ketones, hemiacetals, N-phenyl hydroxylamine or N-alkyl hydroxylamine as well as formic acid, they will show silver mirror test, but this will react with Tollens reagent, but it will not show Tollens test. It will show white precipitate. It will form white precipitate. It will not show silver. It will not form silver mirror, but it will form what we call white precipitate test. It will not form silver mirror. These will form silver mirror. These 5 will form silver mirror. 1, 2, 3, 4, and all types of aldehydes. They will form silver mirror test. They will form silver mirror, but this will not form silver mirror. It will form white precipitate. After that, Reduction of Fehling solution. First of all, what is meant by Fehling solution? Fehling solution means aqueous solution of copper sulfate, aqueous solution of copper sulfate containing some Rochelle salt. So when Rochelle salt is added, what is meant by Rochelle salt? Alkaline solution of what we call sodium potassium tartrate, then this aqueous solution becomes alkaline solution. So you can write down over here alkaline solution. So it is alkaline solution of copper sulfate, containing some Rochelle salt. What is Rochelle salt? Rochelle salt means sodium potassium tartrate, alkaline solution of sodium potassium tartrate. So it is sodium potassium tartrate. Now, how Fehling solution is obtained? Remember, Fehling solution A means aqueous copper sulfate solution. When we add Fehling solution B to this, that means when we add alkaline solution of sodium potassium tartrate to this, we get Fehling solution. Now have a look. If you are having an aliphatic aldehyde, not aromatic, when this is treated with Cu di positive and OH negative, and I will balance the reaction, that's why I will write down twice and 5 times. These ions came from Fehling solution. Now what will happen? This RCHO group is oxidized to RCO negative. And this Cu di positive is reduced to Cu2O, that means Cu positive, and red precipitate of this is formed. If we balance the reaction, it was 5 and 1, 6 hydrogen of 6 oxygens were there. So 2 and 1, 3. So it is 3 times water. So we have to note down that aromatic aldehydes and ketones do not show this reaction. That means then we can distinguish then. Hence, we can distinguish aliphatic aldehydes, because only aliphatic aldehydes show this reaction. So we can distinguish aliphatic aldehydes from aromatic aldehydes and we can distinguish aliphatic aldehydes from ketones with the help of this test known as Fehling's test. Okay. This reaction or this test is also shown by number 1, alpha hydroxyketones and number 2, what we call formic acid. I hope this is clear. After that, Benedict's solution. It is Benedict's solution. Okay. So, similar type of reactions take place. In this as that of Fehling solution. Only difference is Fehling solution was aqueous copper sulfate plus sodium potassium tartrate. This is known as aqueous copper sulfate plus sodium citrate. This is the only difference over here. That means in case of, remember, in case of, say Fehling solution, Cu2 positive of copper sulfate forms complex with, say sodium potassium tartarate, that means with tartarate, but in case of Benedict solution, Cu di positive form complex with citrate ions. And reaction is once again same reaction, and this reaction is shown only by aliphatic aldehydes. Aromatic aldehydes or ketones do not show this reaction. Similarly, this reaction is also shown by alpha hydroxy ketones and formic acid. Similar type of reaction as that of, say Fehling solution. Then oxidation of aldehydes and ketones using sodium hypohalite. Sodium hypohalite means NaOX, or we can simply say it's halogenation in basic medium. Remember forever. This reaction is shown by those aldehydes or ketones which contain C double bond O group. So this reaction is shown by those aldehydes or ketones which contain C double bond O group. Or this reaction is shown by those which contains, say CH2X C double bond O group. This can also show. Or this reaction is shown by this one. Or this reaction is shown by this. That means if I talk about aldehydes, only one aldehyde known as acetaldehyde. Among aldehydes, it's the only one aldehyde we show this reaction. And among ketones, it is methyl ketones we show this reaction. Among ketones, methyl ketones can show this reaction. These can also show CH2X if alpha, say position is replaced, if alpha hydrogen is replaced by one hydrogen, by two hydrogens or three hydrogens, they will also show this type of reaction. And if the value of X, if X2 is I2NaOH, then reaction is known as iodoform test. At that time, reaction is known as iodoform reaction, iodoform test. Because this reaction is also known as haloform reaction. This is also known as haloform reaction. So this is point number 1 among aldehydes and ketones. But another point among alcohols. Among alcohols, remember this as well. This is very, very important. Among alcohols, only those alcohols will show this reaction which contains this, which contain this one, which contain this group. So what is R over here? R can be H or any alkyl or aryl group. Any alkyl or aryl group. So you have to remember this. You have to remember this. That means alpha carbon should be attached to one CH3 at least on two sides. There must be at least one CH3 and there must be one H, there must be one OH. If alcohol is having this, then it will show, iodoform reaction or iodoform test or haloform reaction. That means if I write down like this, it shows iodoform reaction or haloform reaction, but this will not show. But this will not show. But this will not show. Why? Because both are aldehydes, but in this aldehyde CO is attached to CH3, but in this CO is not attached to CH3, so it will not show. Similarly, if we compare ketones, CH3 C double bond O, CH3, it will show. But this type of ketone will not show. This type of ketone will not show. It will not show. So in a nutshell, you can simply say which type of ketone shows and which type of ketone will not show. Similarly, if we want to see among alcohols, this will show, but this alcohol will not show. It will not show. Why this shows? Because at this position, OH is attached to carbon, that means it's alpha carbon. There should be at least one H that is present. There should be at least one CH3 that is present. There should be at least one H that is present, but there should be at least one CH3. But to this alpha carbon, there is not any CH3 group attached. So it will not show, show what we call iodoform test. In a nutshell, these are the aldehydes, ketones and alcohols which can show this type of reaction. Now, which type of reaction is as per aldehydes, ketones is concerned? Have a look. We now know that this can show this reaction. It can show this reaction. It can show this reaction. Now have a look. If it is treated with halogen in presence of NaOH, or we will say it is treated with sodium hypohalite. Now what we have to do is, CH3 group attached to C double bond O. Just break that. Convert this CH3 into CHX3. Convert this CH3 into CHX3 and give ONA to this. That means product of this reaction will be CHX3 plus HCOONA. So this is if it is an aldehyde or it is a ketone. Have a look. CH3, C double bond O, CH3. This is a ketone. Now what we have to do is, we have to simply break one of the CH3 and C double bond O group, only one, because here CH3 groups are two, only one. Then convert this into CHX3 and give ONA to this. So it will become CHX3. So I will write down CHX3 and this is CH3COONA. CH3COONA. That's it. Similarly, we know this type of alcohol can show this reaction. Now listen carefully. Convert this alpha CHOH into COONA. This H is attached, that means it becomes HCONA, and break this bond. Convert this CH3 into CHX3. Convert CH3 which is attached to alpha carbon to CHX3. Convert that into one of the CH3 groups, attached to alpha carbon to CHX3, and then CHOH is converted to CONA. H is there, so it is HCOONA. So in this way, you have to oxidize or you have to convert, say aldehyde, ketone or alcohol to aldehydes. I hope this is clear. To halo forms. I hope this is clear. So aldehyde is converted to halo form, ketone is converted to halo form, and alcohol is converted to halo form. And here this alcoholic part is oxidized, this ketonic part is oxidized, this ketonic aldehydic part is oxidized. So this is oxidation of aldehyde, ketone and alcohol by using halogen in presence of NaOH. Then after that we are having aldol condensation. Now listen, this aldol condensation is of two types. One is acid catalyzed. And another one is base catalyzed. But in our syllabus, base catalyzed is important. This is not in our syllabus. Now, if we talk about base catalyzed, it's of two types. One is intermolecular. Another is intramolecular. And if we talk about intermolecular, it is of two types. One is self or simple. Another is crossed or mixed. Now, have a look. First of all, substrate of this reaction is either aldehyde or ketone containing at least two alpha hydrogens. But when I say containing at least two alpha hydrogens, that means for aldol condensation. For aldol reaction, it must contain, aldehyde or ketone must contain only one alpha hydrogen. But for condensation, there must be at least two alpha hydrogens. Number second, reagent used over here is a base. Reagent is a base. Which type of base is used? Mild base. Say for example, dilute NaOH or dilute KOH or 10% NaOH or 10% KOH, or you can say BaOH whole 2, you can say aqueous Na2CO3, so on and so forth. So mild bases are generally used. Now, for example, let's take an example of self or simple intermolecular aldol condensation. What is meant by that? Have a look. If we are having an aldehyde like this, say for example, we are having an aldehyde like this. This is acetaldehyde. If I treat another similar type of aldehyde with it, that means both the aldehydes, both the carbonyl compounds are of are same or identical, at that time we call this reaction as aldol reaction. But this is intermolecular aldol reaction, same molecules, that means simple or self-aldol condensation. Say for example, dilute NaOH is there. Listen, what is the trick? Have a look. This carbon is more electronegative than hydrogen. So let me say this is alpha carbon, and alpha carbon is partial negative charge. This is partial positive charge. First of all, check alpha carbon partial negative, alpha hydrogen partial positive. Then second molecule, this carbonyl part positive, this oxygen negative. Give positive to negative, negative to positive, and convert double bond into single bond. So what will be the product? Product will be CH3CH. This is OH, because O and H, this becomes single bond. Then single bond, alpha and this carbon will form CH2, CHO. This is aldehyde, this is alpha, this is beta hydroxyaldehyde. This is commonly known as aldol, Now, if I write down a ketone over here, like this, once again, alpha hydrogen and alpha carbon show positive and negative parts. Very, very simple. Now, say for example, BaOH whole 2. Now what will happen? Now give positive part to negative, negative to positive. So the product of this reaction will be like this. This is of ketone, this is alpha, this is beta. Beta hydroxyketone, commonly known as ketol. So that reaction of aldehydes or ketones containing at least one alpha hydrogen, resulting in the formation of aldol, that means beta hydroxyaldehyde, or ketol, that means beta hydroxyketone, is known as aldol reaction. So this is aldol reaction. But once this aldol or ketol is further heated, medium is basic. If it is heated, it will lose water molecule. Upon heating, aldol or ketol loses water molecule. That means when it loses water molecule, H from alpha position, hydrogen from beta position will lose, OH from beta position will lose water molecule, and they will form alpha beta unsaturation. Hydrogen from alpha position and OH from beta position. So they will form alpha beta unsaturated aldehyde, or here alpha from hydrogen from alpha position, OH from beta position, they will form unsaturation at alpha and beta position. So they will form like this, alpha beta unsaturated ketone or alpha beta unsaturated aldehyde. And listen carefully. Reaction from this to this or from this to this, it is known as aldol reaction. So for aldol reaction, we need at least one alpha hydrogen. But this reaction from this to this is known as aldol condensation. That means aldol reaction and dehydration of aldol means aldol condensation. So for aldol condensation, we need at least 2 alpha hydrogens. For aldol condensation, we need at least 2 alpha hydrogens in either aldehyde or ketone. And if both aldehydes are identical, both ketones are identical, this is known as simple intermolecular aldol reaction, and this is known as, from this to this is known as simple intermolecular aldol condensation. What is the end product of aldol condensation? It is either alpha beta unsaturated aldehyde or alpha beta unsaturated ketone. What is the end product of, aldol reaction? It is either aldol, it's either ketol. So I hope this is clear to each and every one. So this is simple intermolecular aldol reaction, and from this to this is simple intermolecular aldol condensation. After that, if now aldol reaction or aldol condensation takes place between, say for example, 2 carbonyl compounds, one is this one, acetaldehyde, another is this one, known as propionaldehyde. One is ethanol, another is propanol. Two different aldehydes are there. Then we call this as cross-aldol reaction if aldol is obtained, and we call this as cross-aldol condensation if alpha-beta unsaturated aldehyde is obtained. As we know, these are two different types of, what we call aldehydes. So first, let me tell you like this. Let me show you aldol condensation. Let me show you aldol condensation, and let me show you trick of aldol condensation. This is aldehyde. I will take another similar type of aldehyde. I will take another type of aldehyde. And then this is alpha position. From alpha, just 2 hydrogens will be removed, and from another one, oxygen will be removed. So CH3CH, double bond CH, CHO will be one of the products over here. Here, have a look. It's NaOH, dilute, but heat is also there. When heat is also there, aldol condensation will be the product. If heat is not there, then it will be aldol reaction. So what will be the product? First product will be CH3CH, double bond CH, single bond CHO. This will be between this and this, between these two identical species. Now, I will take this CH3CH2, C double bond OH, and another is CH2 like this of alpha, then it is CH3, then it is CHO. This is alpha, this is beta. We have to remove 2 hydrogens from alpha and oxygen from another one. So CH3, CH2, CH. So I will write down another product, that is CH3, CH2, then CH, then double bond C, CH3, CHO. Now, third one, that means these two are simple, these two are identical or same. That means this product is self-aldol condensation product. Now, mixed one will be like this. CH3, C double bond O, H, that means I will remove oxygen from this and I will remove hydrogen from this. That means like this. Oxygen from one and 2 hydrogens from another molecule. So like this. So what will be the product? Product will be CH3, CH double bond C, CH3, CHO. Another product will be, now I will remove oxygen from this, hydrogen from this now. So let me write down this one first. CH3, CH2, then C double bond O and H. That means oxygen of this one, and hydrogen from this one. I hope this is clear. So all the possibilities are 4 in number. So product will be here CH3, CH2, CH, double bond CH, single bond CHO. Now have a look. Alpha beta unsaturated aldehyde, alpha beta unsaturated aldehyde, alpha beta unsaturated aldehyde, alpha beta unsaturated aldehyde. So if both the aldehydes have 2 alpha hydrogens, then 4 products will be obtained as per aldol condensation is concerned, cross-aldol condensation is concerned. Now listen carefully. Among these, which one will be the major product? Listen carefully. This is what we call ethanol, this is propanol. This is having, this is according to nucleophilic addition reaction. According to nucleophilic addition reaction, this aldehyde is more reactive. That means this is more reactive aldehyde. CH3CHO is more reactive aldehyde as compared to CH3, CH2, CHO. This is nucleophilic addition order. Now remember, major product is always, listen carefully, major product is always that product from which we remove hydrogens from less reactive carbonyl compound towards nucleophilic addition reaction. That means one should be less reactive. One should be less reactive towards nucleophilic addition. That means this is less reactive towards nucleophilic addition. So it should be CH3, CH2, CHO. That means this hydrogen, that means these CH3, CH2, CHO, CH3, CH2OH. That means we should remove hydrogens from this. That means either it should be this or it should be this. Number one is that hydrogen should be removed from less reactive, say towards nucleophilic, what we call addition reaction. But we should remove oxygen. We should remove oxygen. That means we remove oxygen. We remove oxygen from more reactive carbonyl compound, more reactive towards nucleophilic substitution, towards nucleophilic addition reaction. So which one is more reactive? More reactive is this one. More reactive is this one. That means this, the product formed from this, that means CH3CH, double bond C, CH3CHO, this will be the major product. This will be the major product among these four. So from less reactive aldehyde or less reactive carbonyl compound towards nucleophilic addition, we should remove hydrogen, and from more reactive, we should remove oxygen. That means this one. Third product is the major product. Similarly, if you are having an aldehyde without any alpha hydrogen, but we are having another carbonyl compound, say for example that's a ketone, let's suppose that's this ketone known as acetophenone, then what will happen over here? Ketones are less reactive, so we have to remove hydrogens from this. So we will remove hydrogen, and aldehydes are most reactive, we will remove oxygen from that. That will be the major product. So major product of this reaction will be this one. Have a look. And whenever your aldehyde or ketone is having pi bond, carbon-carbon double bond, either in the form of C double bond C or in the form of ring, at gamma position, no need of heat at that time. No need of heat. That means this reaction can take place at 293 Kelvin. That means almost under room temperature. That means under cold conditions, it can form, what we call aldol condensation product. But this is, have a look, this is alpha, this is beta, this is gamma. This is alpha, this is beta, this is gamma. This is alpha, this is beta, this is gamma. This is alpha, this is beta, this is gamma. These gamma positions, have a look, these gamma positions does not have any carbon-carbon double bond. So heat is very, very important for that. If heat is not given, you have to form aldol or ketol. But if gamma contains already, if gamma contains in the product, say this alpha, what we call alpha beta unsaturated aldehyde or alpha beta unsaturated ketone, if gamma position contains double bond, then no need of heat. Why? Why is it so? Why this reaction takes place even absence of heat? Because here, because of this double bond, extra conjugation or extended conjugation takes place, due to which it becomes very much stable. That is the reason here driving force is stability. So no need to heat this aldol or ketol, which one will be formed, because it gets automatically converted to alpha beta unsaturated aldehyde or alpha beta unsaturated ketones. After that, if you are having a dicarbonyl compound like this, and here if you treat it with mild base without heating, then it will be aldol product. But if you heat it, then it will be aldol condensation. That means if we want to form aldol condensation product, then we will form like this. So let us suppose this is alpha position. We will remove 2 hydrogens from this and we will remove oxygen from this. That means if this is 1, 2, 3, 4, 5, 6, then we will form a 5-membered ring. Like this. And to this 5-membered ring, we will number. Say for example 1, 2, 3, 4, 5. We will number like this. At 5th position, 2 hydrogens have been removed, and at 1st position, oxygen has been removed, and there will be a double bond between 1 and 5. That means there will be a double bond between 1 and 5. At 5, there is carbon number 6 in the form of CHO. So in the form of CHO, carbon is like this. So this is alpha beta unsaturated aldehyde, or This is alpha beta unsaturated carbonyl compound. So this was all about aldol condensation. Now, after this, Cannizzaro reaction is there. Listen carefully. Cannizzaro reaction is of two types. One is intermolecular. One is intermolecular, another is intramolecular. One is intermolecular, another is intramolecular. Intermolecular is further of two types, self or simple, and another is cross or mixed. Listen carefully. This self or simple is disproportionation reaction. This is disproportionation reaction. But these reactions are oxidation reduction reactions. Now, what is meant by this? Oxidation reduction reactions. That is self-oxidation reduction. That's why that is disproportionation. Have a look. First of all, substrate. Which type of substrate can show Cannizzaro reaction? Only aldehydes, but without any alpha hydrogen. Without alpha hydrogen in general. After that, reagent, that means base. Reagent should be concentrated NaOH or concentrated KOH, or it should be 50% NaOH or KOH in general. Now have a look. What will happen? What will happen during this reaction? Have a look. First of all, as we know, this aldehyde does not have any alpha hydrogen. Then, if I take similar type of aldehyde, this is not having any alpha hydrogen, what will happen? One aldehyde is oxidized, another is reduced when it is treated with concentrated NaOH or KOH. So let us suppose this aldehyde is oxidized. So it will form HC double bond ONA. So convert CHO into CONA, and another is reduced like this. Break this bond, add H and add H to this. That means it will form CH3OH. That means one is oxidized to sodium salt of acid if NaOH is used, potassium salt of acid if KOH is used. Then another is an alcohol. Another is an alcohol. That means formaldehyde is oxidized, formaldehyde is reduced. That means it is self-oxidation reduction. That's why this is known as disproportionation. This is known as disproportionation. Similarly, if benzaldehyde is there, one benzaldehyde molecule is oxidized, another is reduced. That means one is oxidized to sodium salt of benzoic acid. Another is reduced to benzyl alcohol, like this. I hope this is clear. Now, after that, so this is simple or self-intermolecular Cannizzaro reaction. Another is, if one is, say for example, benzaldehyde without any hydrogen, any alpha hydrogen, another should be different from this aldehyde, but that should also does not contain any alpha hydrogen. So in case of cross Cannizzaro reaction, no aldehyde should contain any alpha hydrogen. If any one contains alpha hydrogen, at that time it's not cross Cannizzaro, it is cross aldol. So listen carefully. Now, here we have to oxidize one and we have to reduce one. Now the question is, which one is oxidized, which one is reduced? Have a look. Aldehyde, which is more reactive, towards nucleophilic addition reaction is oxidized. Remember it. Remember it forever. And we know formaldehyde is much more reactive towards nucleophilic addition. So this is oxidized. Obviously, this one will be reduced. So the product of this reaction will be like this. This one will be reduced. And this one will be oxidized. So any aldehyde which is more reactive towards nucleophilic addition reaction is oxidized. Another one will be obviously reduced. So this is cross what we call intermolecular Cannizzaro reaction. Sometimes we are having like this. dicarbonyl compound is like this. So what we have to do is, we will oxidize one and we will reduce one. We will oxidize one and we will reduce one. Both are identical. So let us suppose this is oxidized, this is reduced. So we will get like this. This is reduced, this will be oxidized now. For example, this is CH3, C double bond O, and then C double bond O, H. Or let me write down like this. Let me write down a benzene ring over here. This part is more, reactive towards oxidation, more reactive towards nucleophilic addition reaction as compared to this one. So we will simply oxidize this part and we will reduce this part. So product will be like this. CHOH, it will be reduced and this part will be oxidized. So oxidize that part which is more reactive towards nucleophilic addition reaction. So this was what we call intramolecular Cannizzaro reaction. After that, electrophilic substitution reactions, aromatic electrophilic substitution reactions. Let me write down like this, C double bond O. If this part is H, then it is aldehyde, aromatic aldehyde. If this part is not H, it is alkyl or aryl, then this is aromatic ketone. In nutshell, this part is electron withdrawing, it is meta-directing part. It is meta-directing. That means if we treat it with, say for example, Cl2 in presence of excess of anhydrous AlCl3. Now we know Cl positive will be generated, that electrophile will go to meta position because it is meta directing. So whether it is aldehyde, whether it is ketone, so it is there to that meta position, Cl will be introduced. So this will become halogenation, chlorination. Similarly, bromination can take place. After that, if nitration takes place, we know nitronium ion will be the electrophile, and that electrophile goes to once again meta position. So electrophile NO2 will go to meta position and water will be the side product. Similarly, if we treat it with sulfuric acid, SO3H will be introduced to meta position. So it will be like this. SO3H will be like this. So if we write down H over here, so here will be H, so aromatic aldehydes. If we remove this H and if I write CH3 over here, CH3, then it will be aromatic ketones. And product will be same once again. I hope this is clear. So this was all about aldehydes and ketones. Now it is carboxylic acids. From primary alcohols and aldehydes, by oxidation, it's already done. It is already done. It's already done in alcohols. After that, from alkyl benzene, listen carefully. This is alkyl benzene. Say for example, methyl benzene. But which type of alkyl benzene shows this reaction? Which contain at least one benzylic hydrogen. That means that alkyl group in which carbon attached to benzene, that means benzylic position, should contain one hydrogen. So it shows what will happen over here. Have a look. Suppose, and reagents generally used are strong oxidizing agents. For example, if I use KMnO4 in basic medium, KMnO4 will oxidize this CH3. So all these alkyl groups will be oxidized to COH, irrespective of their size. That means they will form COOH, but COH is acid. This KOH is base. This KOH, OH minus will abstract H positive from acid and it will become CO minus and K positive. That means it will form a potassium salt. This upon acidification. This O minus will abstract H positive from this and we will get COH. In nutshell, if I use like this, if I use alkyl benzene like this and I will use KMNO4 in basic medium first, followed by acidification. That means I will directly convert this alkyl to COH. Irrespective of whether this alkyl group is large, it contains more than one carbon or not, hardly matters. What matters is this alkyl part should contain at least one benzylic hydrogen. So what will be the product? What will be the product? Product will be once again benzoic acid. Product will be benzoic acid. Similarly, if I write down like this, this is also an alkyl group, but this alkyl attached to benzene does not contain any hydrogen at this benzylic position. So I will say no benzoic acid formation takes place. KMNO4, KOH followed by acidification. So I will say no benzoic acid formation takes place. No benzoic acid formation takes place, as there is no benzylic hydrogen present in this. Similarly, if I write down like this, orthoxylene, this is known as orthoxylene. This upon treatment will result in the formation of, as two alkyl groups are there, so one alkyl group is converted to COH, another is converted to COH. That means orthoxylene will form phthalic acid. Orthoxylene will form phthalic acid. Similarly, if I write down metaxylene, now what will happen? Convert alkyl part or that carbon which is benzylic carbon to which one hydrogen is attached, convert that part into COH. Similarly, COH. This is known as isophthalic acid. Similarly, if you are having paraxylene, under similar conditions, what will happen? Alkyl part or that carbon to which hydrogen is attached, I mean say that benzylic carbon to which hydrogen is attached, we have to convert that into COH. So this is terephthalic acid. Similarly, if I write down like this, so can I say this is the benzylic carbon to which hydrogen is attached, Convert benzylic carbon to which hydrogen is attached to COH. So what will be the product over here? What will be the product of this reaction? It will be simply convert this carbon into COH. Similarly, convert this into COH. Irrespective of other carbons. So you have to convert this into COH, this carbon into COH. So phthalic acid will be obtained. After that, from nitriles and amides, this is nitrile. And listen carefully. If hydrolysis of amide, this nitrile, takes place in acidic medium or in basic medium, what will happen first? One pi bond is broken, one H and one OH is added. Another pi bond is broken, another OH will be added to this. That means this C attached to two OH groups means C double bond O. Finally, it will form C double bond O. And there is one nitrogen single bond there with two hydrogens. That means it will get amide. We will get amide over here. So from nitriles, we will get amide first. If this amide is further hydrolyzed in acidic or basic medium, now listen carefully. What will happen? This bond will be broken. give H to this, OH to this. That means we will get carboxylic acid and ammonia. Now listen. Reaction from this to this is known as partial hydrolysis. Partial hydrolysis of nitriles. So partial hydrolysis of nitriles will give, say, amide, and from this to this is hydrolysis of nitriles, or we can say complete hydrolysis of nitriles. Whether you say hydrolysis of nitrile or you will say complete hydrolysis of nitrile, it will result in the formation of, cyanide upon partial hydrolysis will give amide, but upon hydrolysis it will give carboxylic acid. Similarly, this amide upon hydrolysis will also give, carboxylic acid. I hope this is clear. From Grignard's reagent, this is RMGX, Grignard's reagent, negative part, positive part. This on treatment with carbon dioxide, what will happen in presence of dry ether? What will happen in presence of dry ether? This R negative will act as a nucleophile. It will attack this carbon and it will form R single bond C, double bond O, single bond O minus. That means R single bond C, double bond O. R single bond C, double bond O. Then this is O minus. Then MgX with a positive charge. Finally, you will hydrolyze this. And we will get carboxylic acid. In addition to that, hydroxymagnesium halide. So, after that, my dear lovely students, we will be having acyl halides. Acyl halides are these one. Say for example, acyl chloride. If say for example, it is treated with water, what will happen? This bond will break, give H to this, OH to this. That means we will get carboxylic acid and HCl. And suppose same reaction takes place in basic medium. What will happen now? We will get once again carboxylic acid and HCl. But in basic medium, what will happen? What will happen in basic medium? Obviously, base will abstract H positive, from acid, and it will result in the formation of salt of that acid. It's very, very simple. So you can perform this easily. Now, after that, if you are having an anhydride like this, now, if this is treated with water, so these are nucleophilic acyl substitution reactions. So let me break this one and we will get OH to this, H to this. So we will get RCOH. If both are, similar groups, then we will get twice RCOH. Very, very simple reaction. Now, after that, from esters, ester is this one, RC double bond OOR prime. Now, first reaction is like this. On treatment with water, what will happen? Break this bond, give H to this, OH to this. So we will get carboxylic acid and alcohol. But my dear lovely students, if same ester undergoes basic hydrolysis, that means H2O in presence of basic medium or aqueous NaOH, you can say, then what will happen? First, it will form RCOH, but this base will convert that RCOH into RCONA, that means sodium salt. So, RCOH gets converted to sodium salt, water will be lost, and then it will form R prime OH. And we know higher fatty acids, that means if value of R is very higher, that means higher fatty acids having the same formula higher fatty acids having same formula, they can be called as, we will call that as soap. Those higher fatty acids will be called as soap. And this reaction with the help of which we can synthesize soap is known as saponification reaction. So this reaction can be known as saponification reaction. So this reaction can be known as saponification reaction. Listen carefully. Similarly, my dear lovely students, if ester is treated with alcohol, if ester is treated with alcohol, say for example, this is ester, this is alcohol. Now what will happen? What will happen? Now this negative part of this ester OR is replaced by this OR. That means it will be like this. Once again, ester will form ester and alcohol. Ester on treatment with alcohol will result in the formation of ester and alcohol. Only thing is that these groups are replaced. So it will come here, it will come here. This reaction is known as trans-esterification. Trans-esterification. Trans-esterification reaction. I hope this is clear. After that, chemical reactions of carboxylic acids, reactions involving cleavage of OH bond, reaction with metal. Simple reaction. Whenever any carboxylic acid reacts with any metal, say for example sodium, potassium, magnesium, aluminium, zinc, calcium, now what will happen? It will simply form, carboxylic acid will form salt of carboxylic acid. That means that metal carboxylate is obtained like this, RC double bond O, ONA, with evolution of hydrogen gas. That means hydrogen gas is also evolved. So if I take potassium over here, then it will give potassium salt of carboxylic acid and hydrogen gas will be evolved. After that, reaction of carboxylic acid with carbonates and bicarbonates. Have a look. This is carboxylic acid and this is sodium bicarbonate. This is negative, this is positive. What will happen? What will happen? This negative part will simply abstract H positive. It will act as a base. It will abstract this H positive. It becomes H2CO3 and that will become RCONA. So it will become RCOONA, sodium salt of carboxylic acid, plus H2CO3. This is known as carbonic acid. Then finally this carbonic acid gets converted to carbon dioxide and water. And we will get brisk effervescence of this carbon dioxide. Brisk effervescence. And this reaction is shown by all those acids which are stronger acids than, say carbonic acid. Say for example, carboxylic acid is stronger acid than carbonic acid. So it will show this reaction. Phenol is not that stronger as that of carbonic acid. So phenol will not show this reaction. So with the help of this reaction, we can distinguish carboxylic acid from phenol by using sodium bicarbonate or by using sodium carbonate, and reaction is known as sodium bicarbonate or sodium carbonate test. Similarly, if I take a carboxylic acid and this carboxylic acid is treated with Na2CO3. Now have a look. This is Na positive, but this is having CO3 2 minus. Once it will add H positive, except H positive, it becomes HCO3 minus like this. Then it will abstract another H positive from another acid and will result in the formation of H2CO3. So once again, it will first form RCONA plus H2CO3, and this carbonic acid gets converted to carbon dioxide plus water. Once again, brisk effervescence of carbon dioxide will be evolved, will be here. So brisk effervescence will be here. So these reactions can be used as a distinguishing test between acids which are stronger acids than carbonic acid and acids which are weaker acids than carbonic acid. For example, this reaction can be used to distinguish carboxylic acid and phenols under the name sodium bicarbonate test and sodium carbonate test. After that, reaction with alkalis. Say you are having carboxylic acid. On treatment with NaOH, what will happen? What will happen on treatment with NaOH? Sodium salt will be formed. That means acid-base reaction, normal acid-base reaction will form salt like this. Similarly, positive negative part. This is positive part, negative part. This is positive part, negative part. Just try to exchange positive, negative. Similarly, this is acid. Let me erase this one. This is for understanding only. Now, RCOH plus NH4OH. Now, negative part of this is OH minus. It will abstract H positive, so water. So this becomes negative part and NH4 positive will be there. So I mean to say it will result in the formation of ammonium salt of carboxylic acid, and water will be there. I hope this is clear. I hope this is clear. Then reactions involving cleavage of COOH bond, formation of anhydride. Say for example you are having an acid, carboxylic acid, and if carboxylic acid reacts in such a way that in presence of say for example a dehydrating agent like P2O5 or a protonic acid like H2SO4 and this, then what will happen? It will lose water molecule. Once water molecule is lost, and it will result in the formation of anhydride like this. So anhydride is obtained here like this. Very, very simple reaction. After that, formation of acyl chloride. Listen carefully. If your carboxylic acid is there and it is treated with PCl5. Now what will happen? It will replace this OH by Cl. We will get RCOCl. Another product will be POCl3. Another product will be HCl. Simple reaction. Similarly, if carboxylic acid is treated with, PCl3, then what will happen? Replace this OH by Cl. So it will be RCOCl plus H3PO3. So to balance the reaction, we have to write this 3 times and this 3 times. Similarly, similar type of reactions are that of alcohols. RCOOH plus SOCl2. Then it will result in the formation of, just replace this by Cl. So we will get RCOCl plus SO2, which is a gas, and HCl, which is a gas. That means these are the gaseous side products. So this will be obtained in pure form. So to obtain acid chloride from carboxylic acid, this method is considered as best method. After that, formation of ester. It's very simple reaction, esterification reaction. It's carboxylic acid on treatment with alcohol, say for example like this, and in presence of, say for example H positive, what will we get? Simply OH is lost from, OH is lost from carboxylic acid and H is lost from alcohol. We will get carboxylic, we will get ester like this, and we will get water in which oxygen is O18. I hope this is clear to you. This is esterification reaction already done in, alcohols. Formation of amide, very, very simple reaction. It is actually whenever you are having, carboxylic acid upon treatment with ammonia followed by heating, it results in the formation of amide. Actual reaction is like this. Whenever carboxylic acid is treated with ammonia, it results in the formation of ammonium salt first. And once this ammonium salt is obtained, if it is heated, upon strong heating or upon heated, so it will lose water molecule and result in the formation of amide. So it will lose water molecule and will form amide. So you can remember this in this fashion. After that, it is reduction reaction to alkane. So whenever you are having carboxylic acid, you want to convert this into alkane. That means you want to convert this into CH3. Then you have to use HI in presence of red phosphorus. That means reducing agent. Simple reducing agent. Then reduction to alcohols, whenever you want to convert carboxylic acid to alcohol like this, RCH2OH, you have to use B2H6 followed by hydrolysis, or you have to use lithium aluminium hydride followed by hydrolysis, or you have to convert this acid first into ester and after that reduction of ester, as we have discussed this in alcohols already. Now, after that, decarboxylation. Decarboxylation of carboxylic acid means we have to remove carbon dioxide. When we remove carbon dioxide, we will get alkane. Now the question is, this carbon dioxide is removed in what form? Have a look. I mean, say by using soda lime. Reaction is known as Awkward process. Reaction is known as Awkward process. Have a look. If you are having sodium salt of carboxylic acid and this is treated with NaOH, CaO in the ratio of 3:1, I mean say soda lime, and heat, what will happen? It will result in the formation of Na2CO3 and RH. That means alkane is obtained and carbon dioxide is lost in the form of CO3 minus. That means Na2CO3 means carbonate ion, CO3 minus ion. Carbon dioxide is lost in the form of CO3 minus ion. This reaction is known as what we call decarboxylation by using soda lime. Another is decarboxylation by using Kolb's electrolysis, like this. Whether CONA or COK, you can use that. So this upon treatment with water and undergoing electrolysis, this upon electrolysis yields, remember, upon electrolysis yield what? Just break this bond, form a radical over here, these radicals will combine, that means it will form RR at anode, number one. Number second, it will result in the formation of carbon dioxide, that means carbon dioxide gas is also evolved at anode. Then hydrogen gas will be evolved at cathode. And after that, in solution, when this is CONA, then in solution there will be NaOH. If it is COK, then in solution there will be KOH. So as this is alkaline, so pH of the solution will be greater than 7. The only thing what you have to remember is, if the value of R is H, that means if it is sodium salt of formic acid, then at anode it will be H2, as well as at cathode H2 gas will be evolved at that time at anode as well as cathode. There will be no alkane formation at that time. I hope this is clear. So after that, there is a reaction known as Hell-Volhard-Zelinsky reaction. Hell-Volhard-Zelinsky reaction. Hell-Volhard-Zelinsky reaction. What is this reaction? Listen carefully. Any acid, any carboxylic acid containing at least one alpha acidic hydrogen or containing at least one alpha hydrogen, is treated with, I mean say halogen, and this halogen in presence of red phosphorus followed by hydrolysis takes place. But remember, X is either chlorine or bromine. That means chlorination or bromination in presence of red phosphorus followed by hydrolysis of any acid, any carboxylic acid containing at least one alpha hydrogen takes place. And then what will happen? Halogenation will generally takes place at alpha position by replacement of hydrogen. So this is the, I mean say, Hell-Volhard-Zelinsky reaction. So what is Hell-Volhard-Zelinsky reaction? It is simply alpha halogenation. That means the replacement of hydrogen by halogen at alpha position of acid. I hope this is clear. But chlorine is more reactive as compared to bromine. Remember that as well. Okay. After that, aromatic electrophilic substitution reactions. Listen carefully. As we know, COOH is electron withdrawing group. It is meta-directing group. That means if halogenation takes place, say for example, Br2 in presence of FeBr3 takes place, then what will be the product? Br positive electrophile goes to meta position because this is meta-directing. This is meta-directing. So this will be the product of this reaction. So this is bromination or halogenation. Then what will happen during nitration? What will happen during nitration? Nitration means nitronium ion is an electrophile. So nitro group will go to meta position like this. And after that, during sulfonation, sulfonic acid group goes to meta position. Sulfonic acid group goes to meta position like this. And meta-directing groups, electron withdrawing groups, deactivating groups do not show what we call Friedel-Crafts alkylation as well as Friedel-Crafts acylation reaction. So this was all about, aldehydes, ketones and carboxylic acids. I hope this is clear to each and everyone. Now, let me know in the chats quickly. Should we continue with amines and diazonium salts, because it will take maximum it will take 45 to 50 minutes. So should we continue? Should we complete whole organic chemistry within 45 minutes? Should we complete whole, this in 45 minutes? But this is not the time that I will show SN1 and SN2 separately. This is not the right time because SN1 and SN2 is already clear to you. They are very, very simple reactions and we have already completed those in the session in which we take haloalkanes most probably for 4 or 5 hours. We have completed that. It's not possible to complete biomolecules right now, but yes, I will try to record that biomolecules within, 1 hour most probably. So I will try to complete that in a recorded session. Don't worry, I will try. If biomolecules is still bothering you, don't worry, because biomolecules is very, very easy as per, medical students or NEET students are concerned, because that is already in your biology as well. So don't worry, if you want me to complete biomolecules, I will try to record that. And I will try to complete that in 1 hour. I will try to complete that in 1 hour or 40 to 45 minutes. Now, this is the last chapter for today's session, and that is amines and diazonium salts. Now, have a look. First reaction is methods of preparation of amines. That is Hofmann's ammonolysis method. It is simply like this. When you are having primary amine on treatment with alkyl halide, but excess of alkyl halide, what will happen? It will simply result in the formation of secondary amine. Then this secondary amine on treatment with, excess of alkyl halide, and it will result in the formation of tertiary amine. And then this tertiary amine on treatment with alkyl halide. That means alkyl halide should be present in excess. On treatment with alkyl halide, reacts in the formation of quaternary ammonium salt. This is what we call Hofmann's ammonolysis method. After that, reduction of nitro compounds by using catalytic reduction. Remember, whether you are having aromatic or aliphatic nitro compound, by using catalytic reduction, that means H2 in presence of catalyst. Can use different catalysts, but simple type of catalyst, Raney nickel, platinum or palladium. Simple type of catalysts. So what we have to do is we have to convert NO2 into NH2. That is it. We have to convert NO2 to NH2. You have to remember this. Conversion of NO2 to NH2. That's it. Whether aliphatic, whether aromatic. Now, after that, reduction by using active metal. By using active metal in acidic medium, in H positive or in HCl. Have a look. Whether you are having aromatic or aliphatic nitro compound, what you have to do is, you have to once again convert this NO2 to NH2. You have to convert this NO2 to NH2 by using active metals like tin in acid, say for example HCl, or iron in presence of HCl, or you can use zinc in acid. You can use any active metal, but generally iron, tin and zinc can be used. After that, next reaction is reduction by using lithium aluminium hydride. Just a moment. It's reduction by using active metal in HCl. Then it is reduction by using lithium aluminium hydride. Have a look. Reduction by using lithium aluminium hydride. If you are having nitro compounds, aliphatic nitro compound, reduction by using lithium aluminium hydride converts NO2 to NH2. But when aliphatic nitro compound is there. But if you are having aromatic compound, say for example nitrobenzene, then listen carefully and try to remember this. This is very important. Lithium aluminium hydride at that time does not form amine. It forms azobenzene. Listen carefully. After that, reduction in neutral medium. Say for example, you are having RNO2, that means say nitro compound like this. Say aliphatic nitro compound. When this is treated with zinc in ammonium chloride, neutral medium, then convert NO2 into NHOH. Listen carefully. Convert NO2 into NHOH. Similarly, if it is aromatic, then once again it will be converted to aromatic NHOH. But say for example, you are having nitrobenzene. Example. This is simple example. Then what will happen over here? If this is treated with zinc ammonium chloride, you will get this one. NHOH. That means hydroxylamine first. But listen carefully, if it is treated with Tollens reagent, if it is treated with AgNH3 whole 2 OH, say Tollens reagent, then what will happen? Listen carefully. Then what will happen? It will result in the formation of NO. That means removal of hydrogen from this has been taken place. Removal of hydrogen means oxidation, so it will get oxidized. But silver mirror is also obtained. So with the help of this silver mirror, we can simply detect this nitro compound, and this test is known as Baker-Mulliken test. It's test to identify nitro compounds. So Baker-Mulliken test, or sometimes it's also written sometimes in different literature that Baker-Mulliken test. So it's Baker-Mulliken test, or sometimes it's written as Baker-Mulliken test. So with the help of this test, we can find out whether our compound contains nitro or not. Because if our compound contains nitro group, what will we do? Say for example, we have to check whether the compound is this test tube contains nitro compound or not, what will we do? We will simply add zinc and ammonium chloride. After that, we will add silver, ammonical silver nitrate solution, that means Tollens reagent. If silver mirror appears, that means our compound, that test tube contains nitro compound. So this is test for nitro compound. After that, electrolytic reduction of nitrobenzene. This is nitrobenzene, listen carefully. Electrolytic reduction of this, that means electrolytic reduction. Electrolytic reduction. Try to remember these reactions. Try to remember these reactions. Electrolytic reduction. In weakly acidic medium. In weakly acidic medium, it results in the formation of aniline. It results in the formation of aniline. So nitro compound is converted to aniline. But in strongly acidic medium, we will get NHOH, but this NHOH is not obtained, not isolated, it rearranges. It rearranges to form para-amino phenol. That means this is the product. That means if nitro compound is undergoing electrolytic reduction in strongly acidic medium, product will be at that time para-amino phenol. Para-amino phenol will be the product. This will not be the product, para-amino phenol will be the product. After that, selective reduction. Say for example, simple example of this is xenin reduction. Xenin reduction. The simple example, xenin reduction. Have a look what will happen. If you are having more than one nitro group and you want to reduce only one nitro group, then we generally use sulfides or polysulfides. Say for example, ammonium sulfide or sodium sulfide or sodium bisulfide. You can use like this. Then what will happen? One of the NO2 group is reduced to NH2. One of the NO2 group is reduced to NH2. Say for example this one. Another remain as it is. So it is selective reduction. One will be reduced, another will not. So for this, these types of sulfides or polysulfides can be used and the reaction is known as xenin reduction. After that, reduction of nitriles and isonitriles. Have a look. This is nitrile, means cyanide. When cyanides are reduced, remember what will happen? Just try to break two bonds and try to add two hydrogens to carbon, two hydrogens to nitrogen. That means we will get a primary amine. We will get a primary amine over here. Primary amine over here. And the reducing agents are lithium aluminium hydride. Or you can use what we call H2 in presence of catalyst, say for example nickel, or you can use sodium amalgam in alcohol. This reaction, you can use different reducing agents, but these reducing agents are written in your NCERT, and your NCERT is very, very, very important. Try to remember NCERT as much as you can. This type of reduction, that means reduction of cyanide or nitrile to primary amine by using sodium in alcohol, but this sodium amalgam or sodium in alcohol is known as Mendeus reduction. I hope this is clear. After that, reduction of isonitrile. Have a look. This is isonitrile. Reduction of isonitrile. We know when isonitrile is reduced, it results in the formation of RNHCH3. That means it results in the formation of secondary amine. And we can use lithium aluminium hydride. We can use, say H2 in presence of catalyst. We can use even sodium amalgam in, say alcohol as well. But listen carefully. Here is the limitation that all types of secondary amines are not obtained. Only those secondary amines are obtained in which one of the alkyl part is methyl. That means methyl secondary amines are obtained. I hope this is clear. After that, reduction of amides. If you are having amide like this is known as primary amide. If you are having amide like this is known as substituted or alkylated amide or secondary amide. If you are having amide like this is known as di-substituted, or this is known as what we call di-substituted amide or a tertiary amide. So whenever you are having primary amide, you are having secondary amide or substituted amide, you are having tertiary amide or di-substituted amide, when they are treated, when amides are treated with lithium aluminium hydride followed by hydrolysis, what will happen? What will happen? C double bond O of amide is converted to CH2. That means we will get primary amine. From primary amide, we will get secondary amine. We will get secondary amine from secondary amide. We will get tertiary amine from tertiary amide, but with similar number of carbons. With same number of carbons in amine as that of amides. Remember this. After that, reduction of azide. Azide is this one, N3. Say for example, it is like this. This is azide, alkyl azide. One of the structures of alkyl azide is this. Now, we want to convert this into RNH2. I mean, say primary amine. Then, what are the reducing agents? Number one, either lithium aluminium hydride, or you can use H2 in presence of catalyst. Say for example, palladium with small amounts of carbon. You can use this one. After that, my dear lovely students, you have to remember reducing agents. Reduction of oxime. Oxime can be aldoxime, it can be ketoxime. So, this is an oxime, it can be aldoxime, it can be ketoxime. What we have to do is, we have to convert it into like this. CHNH2. CHNH2. NH2 means it's primary amine. So, after that, that means we have to break this, give hydrogen to this, give hydrogen to this, break one pi bond, give hydrogen to this, give hydrogen to this. So, it's like this. So, reducing agents are lithium aluminium hydride, or reducing agents are sodium in alcohol. So, you can use these reducing agents. After that, it is Hoffman-bromamide degradation reaction. Have a look. Whenever you are having amide, your amide should be primary amide. Your amide should be primary amide, whether aliphatic or aromatic, but it should be primary amide. This on treatment with bromine in presence of NaOH or KOH, like this, then what will happen? What will happen? Just try to remove this C double bond O. That means we will get here amine, and that too a primary amine, but with one carbon lesser than the primary amide. After that, we will get Na2CO3 if NaOH is there. Otherwise, we will get K2CO3 if KOH is here. Similarly, we will get twice NaBr if NaOH is used. We will get KBr if KOH is used, and then we will get water. Now, is reaction balance? You can have check on oxygen, 1 and 4, 5 oxygens, 3 and 2, 5 oxygens. So, reaction is balanced. So, try to understand intermediate of this reaction. Try to remember intermediates of this reaction. First intermediate, you can say, is this one. This is the first intermediate, N-bromamide. Second intermediate, you can say this, RC double bond ON. This is known as acyl nitrene. Third intermediate is this one, RN double bond C double bond O. This is known as alkyl isocyanate. So on that basis, if sometimes this is given, this is known as methyl isocyanate, and this is responsible for Bhopal gas tragedy. Bhopal gas tragedy. This is responsible for that. This is responsible for Bhopal gas tragedy. Try to remember this point. This is not the point of Hoffman bromamide reaction, but as alkyl isocyanate is, I mean to say, the one of the intermediates of Hoffman bromamide reaction. So if I give value CH3 to this R, then it becomes methyl isocyanate, which is responsible for Bhopal gas tragedy. So these are the, I mean to say, what we call intermediates of this reaction. After that, and remember, this is a rearrangement reaction as well. This is a rearrangement reaction as well, in which this alkyl part is, I mean say, from this alkyl part or aryl part, it is migrated to nitrogen, from this carbon to nitrogen. Remember this. After that, we will be having Gabriel-Thalamide reaction. We will be having Gabriel-Thalamide reaction. Just a moment. We will be having Gabriel-Thalamide reaction. So Gabriel-Thalamide reaction is this. It's Gabriel-Thalamide reaction. Okay, now have a look. Actually, thalamide is this one. This is thalamide. CO, NH, and then CO like this. This is known as thalamide. Thalamide, I mean to say. When this is treated with alcoholic potassium hydroxide, when this is treated with alcoholic potassium hydroxide, OH will remove this H in the form of water, and we will get this one, potassium thalamide, and potassium thalamide, or simply potassium thalamide, like this, potassium thalamide. Then it is treated with alkyl halide, and this reaction is SN2 reaction. So remember, this R can never be aryl, because aryl halides will not undergo SN2 reaction. It can never be vinyl halide, because vinyl halides do not take part in SN2 reaction. It cannot never be what we call tertiary alkyl halide, because tertiary alkyl halide do not show SN2 reaction. So it will attack on this, and it will be lost in the form of X minus, and this KX will be lost, and we will get this one. We will get this one. We will get this one. Finally, this is treated with, say for example, NaOH, aqueous. Now what will happen? What will happen? This bond will be broken, give H to this, ONA to this. Similarly, break this bond, give H to this and ONA to this. So what will be the product? Product formed will be simply sodium salt of phthalic acid. Sodium salt of phthalic acid. So it will be CONA, CONA. If it is COH, COH, it's known as phthalic acid. So here it is sodium salt of phthalic acid plus it will be primary amine. So during this reaction, we will get primary amine. During Gabriel-Thalamide reaction, we will get primary amine, but listen carefully. Primary amine, RNH2, primary amine obtained during Gabriel-Thalamide reaction can never be aniline. It can never be aniline. It can never be aniline. Why? Because for aniline, this R should be aromatic ring. That means this should be aromatic. But aryl halides never show, I mean say, this reaction. And one more thing, you have to remember this one. You should remember this one. This is phthalic acid. This is phthalic acid. This is phthalic acid. You should remember this. This is phthalic acid. This phthalic acid on treatment with ammonia and upon heating will result in the formation of CONH2. CONH2. That means thalamide. That means thalamide. But If this is strongly heated, then this upon strong heating loses what we call ammonia molecule, and it will result in the formation of phthalimide. So it will result in the formation of phthalimide. So phthalimide is actually obtained from phthalic acid on treatment with ammonia in strong heating. If ammonia is there and strong heating is there, we will directly get phthalimide. But first, basically, we will get phthalimide, but upon heating, we will get phthalimide. And it is this phthalimide which is the starting material for Gabriel phthalimide synthesis, Gabriel phthalimide reaction. After that, we will be having chemical reaction of amines. First, reaction of amine with acids, that means basic character of amine. Any amine can react with, say for example, acid like HCl, HNO3, I mean say it can be H2SO4. So it will be a very simple reaction. It will act as a base, it will donate a lone pair and will accept H positive and will form salt. That means acid base reaction resulting in the formation of salt. After that, it is alkylation. Once again, it is alkylation. Primary amine, alkylation means on treatment with alkyl halide. Here, this alkyl halide will act as a electrophile and it will act as a nucleophile. HX will be lost. Primary amine will result in the formation of secondary amine. Then, if alkyl halide is taken in excess, then HX will be lost. We will get tertiary amine. And if alkyl halide is taken in excess, it will further react with alkyl halide and it will result in the formation of quaternary ammonium salt. Once again, Hoffman ammonolysis method is what we call alkylation. Why this is known as alkylation? Because H has been removed and replaced by alkyl. Alkyl group is introduced. So this is alkylation of amines. After that, acylation. Have a look. This is RNH2, I mean say primary amine. When it is treated with acid chloride, say for example acid chloride like this, what will happen? This lone pair will attack this, that means this will act as a nucleophile, this will act as an electrophile, finally it will be lost. Reaction generally takes place in presence of base. Now what will form? It will result in the formation of RNHCOR. Then what has happened basically? This, instead of this hydrogen COR, acylation has been taken place. Acyl group has been introduced, so acylation has been taken place. Similarly, acylation can be done with the help of anhydride as well. Now, what will happen? Instead of this H, acyl group will be introduced. Now, it will result in the formation of RNH, C double bond O and R prime. Here it will be HCl and here it will be R prime COOH. So this will be the reaction. Similarly, the value of this acyl, if R is CH3, reaction is known as acetylation. If R is C6H5, reaction is known as benzoylation. Similarly, this is primary amine, aliphatic amine. Similar secondary amines, I mean say primary aromatic amine can also show the same type of reaction. Say for example, like this, aniline can show also similar type of reaction. Say for example, reaction takes place in presence of base, say for example, pyridine. What will happen? Replace this H by COR. So we will get this one. We will get simply this one. So acylation has been taken place. Similarly, this acylation can be taken place by acid anhydride as well. But if the value of this is C6H5 and reaction takes place in presence of, I mean say aqueous NaOH, that means that is benzoylation of this acidic hydrogen containing compound in NaOH, aqueous NaOH. That reaction is known as Schotten-Baumann reaction. I have already told you that in case of phenol. After that, reaction with chloroform. Listen carefully. Whether you are having aromatic or aliphatic primary amine, aromatic or aliphatic primary amine. Whenever it is treated with chloroform in presence of alcoholic potassium hydroxide. Now what will happen? What will happen over here? Here, isocyanides or carbyl amines or isonitriles will be obtained, and we know they are having very bad smell or unpleasant smell. Then this reaction can be used as a distinguishing test. So remember, this reaction can be used as a test for primary amines under the name isocyanide test. Isocyanide test. So this reaction can be used as a test to distinguish primary amine from rest of the amines, because secondary amine or tertiary amine cannot form this bad smell compound. Bad smell compound is basically isocyanide, carbyl amine or isonitrile. So with the help of this smell, we can distinguish whether compound is primary amine, secondary amine or tertiary amine, and that test is known as carbyl amine test or isocyanide test. This is very, very simple. But you have to remember this point once again, that here amines will act as, I mean, say nucleophile, but remember, electrophile of this reaction is, electrophile is not chloroform. Electrophile of this reaction is dichlorocarbene, like that of Reimer-Tiemann reaction. Electrophile is dichlorocarbene, like that of Reimer-Tiemann reaction. After that, reaction with nitrous acid. Listen carefully. If a reaction of primary aromatic amine, aromatic primary amine, say for example aniline is there, if it undergoes a reaction with NaNO2 HCl or any acid like HBF4, HNO3, H2SO4, now, or we will simply say nitrous acid will be generated within the reaction in situ in excess of HCl, then what will happen? At 0 to 5 degrees Celsius, benzene diazonium salt is obtained, and this reaction is known as diazotization reaction. This is known as diazotization reaction. This is very, very important reaction. A reaction is known as diazotization. This is known as diazotization reaction. So diazotization reaction means preparation of benzene diazonium salt from aromatic primary amine, bond treatment with this at a temperature of 0 to 5 degrees Celsius. Remember, this is considered as stable diazonium salt, but up to 5 degrees Celsius. After that, if we heat it greater than, I mean say at a temperature higher than 5 degrees Celsius, then it will decompose. It is not stable after that. Similarly, if you are having an aliphatic primary amine, listen carefully. If you are having an aliphatic primary amine, this is aliphatic primary amine. On treatment with same these things, it will result in the formation of alkane diazonium salt. Alkane diazonium salt. Listen carefully. Alkane diazonium salt. But this alkane diazonium salt is highly unstable. It's unstable, and after that, what will happen? It will break this bond and it will evolve, I mean say nitrogen gas, and it will form a carbocation, then rearrange it if possible. Finally, it will react with water molecule and it will result in the formation of alcohol. In nutshell, primary amines generally form alcohol. It will not form this because even at 0 degrees Celsius, it is unstable even at 0 degrees Celsius. But this is not unstable, it is stable up to 5 degrees Celsius, but this is not stable. So can we say under ice cold conditions, this is the only amine, aliphatic primary amine is the only amine which evolves nitrogen gas under ice cold condition, because it will not evolve on nitrogen gas. It will evolve on nitrogen gas, but after 5 degrees Celsius upon heating. But up to 0 to 5 degrees Celsius, this is the only amine, aliphatic amine is the only amine which will evolve, say nitrogen gas. Similarly, if you are having a secondary amine like this, R2NH, or you are having a secondary amine like, say for example, this one, then what will happen? On treatment with nitrous acid, secondary amines on treatment with nitrous acid form nitroso compounds, and these are yellow oily nitroso compounds. These are yellow oily nitroso compounds. That means these are yellow oily compounds. So can we say we can distinguish primary amine from secondary amine with the help of this reaction? Even we can distinguish aliphatic as well as aromatic primary amine with the help of this reaction. After that, listen carefully. If tertiary amine is there, aliphatic tertiary amine is there, it can react with nitrous acid and it will form water soluble nitrite salt. It can form water soluble nitrite salt. So these nitrite salts are water soluble. So let me write down water soluble nitrite salt will be obtained over here. Water soluble nitrite salt is obtained. Similarly, if you are having an aromatic tertiary amine like this, now it will undergo electrophilic substitution reaction at para position, and then nitroso group is introduced to para position. Have a look. And these are generally green color compounds. That means we can distinguish primary amines, secondary amines and tertiary amines with the help of nitrous acid. Even we can distinguish aliphatic and aromatic tertiary amines. We can distinguish aliphatic as well as aromatic primary amines with the help of nitrous acid or with the help of this reaction. After that, reaction of amine with Grignard reagent. Say for example, you are having aliphatic primary amine or aromatic primary amine. Similarly, you are having what we call aliphatic or aromatic secondary amine. You are having aliphatic or aromatic secondary amine. On treatment with Grignard's reagent, RMGX, what will happen? Aliphatic or aromatic primary amine and secondary amine can lose H positive. That means such compounds are acidic hydrogen containing compounds, and Grignard reagent will react with such compounds and will abstract H. That means Grignard reagent will act as base, such compounds will act as acid. So this is normal acid base reaction taking place in presence of dry ether. So what will happen? Alkane. So any reaction of Grignard reagent with any acidic hydrogen containing compound in which alkane is obtained, this such type of reaction is known as Zeri-Vatanov reaction. After that, what will be the side product over here? It will be ARR, then it will be NH-MgX. Then here it will be AR2NH, it will be AR2N or it will be R2N. Then on third side it will be MgX. So these are the side products, but alkane will be the major product, or alkane will be the product formed during this reaction, and such reactions are Zeri-Vatanov's reactions. Then reaction with carbon disulfide. Have a look. If you are having aliphatic primary amine, what? Aliphatic primary amine, and it is treated with carbon disulfide, it will first result in the formation of this one, RNH, C double bond S, single bond SH. So it will be like this. After that, this on treatment with HgCl2 will lose HgS, will lose HCl and HCl, that means twice HCl, and it will result in the formation of Rn double bond C double bond S. This is known as alkyl isothiocyanate, and its smell is mustard oil smell. Its smell is mustard oil smell. Mustard oil smell. And this reaction is known as, Hoffman's mustard oil reaction. Hoffman's mustard oil reaction, and is used as a test for aliphatic, not aromatic, aliphatic primary amines. Aliphatic primary amines only, not aromatic primary amines. Remember this. After that, we will be having aromatic electrophilic substitution reactions of, amines. Now have a look. When we talk about this aniline, aromatic amine, we know this aniline will donate its electron and it will increase electron density of the ring. And this is considered as strong activating group. NH2 is considered as strong activating group. It's considered as strong activating group. That means it can increase electron density of the ring at ortho and para position very strongly. Now have a look. Number first reaction is halogenation. So whenever you react aniline with, say for example, bromine or with bromine water. Now as this is strong, activating group, so there is no need of a catalyst. So with the help of this, we can generate Br positive, and that Br positive goes to both the ortho positions and to para position. In nutshell, we will obtain 2,4,6-tribromoaniline as white precipitate of that is obtained. As this is very strong, activating group, polybromination will take place over here. But if we want monobromo products, then what we have to do is, listen carefully. Then for that purpose, if we want monobromo products, monohalogenated products, then we have to treat it with acetic anhydride first. That means we have to do acetylation of this. So it will result first in the formation of NHCOCH3. Then after that, we will perform, bromination reaction. Now this bromine Br positive will goes to ortho as well as para position, but para will be the major product. Para will be the major product because of less repulsion, or ortho will be very less minor product because of more repulsion. So we will get this one. After that, finally, we will do hydrolysis of that. During hydrolysis, what will we do? We will simply break this bond, give H to this and OH to this one. Break this bond, give H to this and OH to this. That means CH3COH will be lost. And finally, we will get two products. One is ortho product or orthobromo product or orthobromoaniline. Another is para product, that means parabromoaniline, but we know para 1 will be the major product. So this will be the major product. This is the major product. After that, there is nitration reaction. Nitration. Have a look. As we know, this NH2 group is a very strong activating group. If it is treated with HNO3 and H2SO4, nitrating mixture, then nitronium ion goes to all these positions which are electron rich. That means to both, and I mean say this NO2 positive can go to ortho position. That means NO2 can go to ortho position. NO2 can go to para position. Have a look, have a look. NO2 go to meta position as well. Now the question is, meta is something unusual product because this NH2 increases electron density at ortho and para position. That's why it should be ortho and para. But when we check the percentage, it's only 2% which is formed. It is only 51% which is formed. Meta is approximately 47% which is formed. That means this unusual product. Why this unusual product is formed? Reason is, actually this aniline is ortho-para directing, but in acidic medium, it is para. In acidic medium, it is meta directing because in acidic medium it forms anilinium ion, and this anilinium ion is meta directing group. Now the question is, as it is meta directing, now the question is why ortho is less, meta is more, para is much more. Have a look. NH3 will withdraw electron, it will decrease electron density at ortho, then it will not decrease that electron density at meta as compared to ortho, but it cannot decrease electron density at para, or it will decrease electron density at para very less because of larger distance. So para is rich in comparison to meta, meta is rich in comparison to ortho. That's why para is more product, para is major product, after that it's meta, after that it's ortho. Now if we want these usual products without this unusual product, then what we have to do is we have to first do protection of amino group. That means we have to react this with acetic anhydride. That means acetylation will take place first. Acetylation will take place, then it will result in the formation of NHCOCH3. Now we will perform our reaction. Our reaction was nitration. That means HNO3, H2SO4. Now what will happen? Nitronium ion will go to ortho as well as para position now. Now it will go to ortho as well as para position. So nitro will go to ortho as well as para, but para will be the major product. Para will be the major product. Para will be the major product. Finally, what will we do? Finally, we will do hydrolysis. And upon hydrolysis, what will happen? What will happen upon hydrolysis? This bond will be broken. Give H to this, OH to this, H to this, and OH to this. That means acetic acid will be lost. And finally, we will get ortho products. Finally, we will get orthonitroaniline and paranitroaniline. And paranitroaniline will be the major product. Paranitroaniline will be the major product. After that, there will be another, that is sulfonation. Listen carefully. Sulfonation is like this. Aniline is a strong activating agent, and sulfonation takes place in presence of H2SO4, and sulfonation is always what we call a reversible reaction. First of all, what will happen? It will first form this one, NH3 positive, and then OSO3H minus or HSO4 minus. That means this one, like this. Now, upon heating at a temperature of 453 to 473 Kelvin, we know at high temperature, major product will be formed because reaction is overall reversible, and most stable product, thermodynamically controlled product is para product. That is why para will be the major product in this reaction. para 1 will be the major product. Para 1 will be the major product, means it will result in the formation of this one. Para product will be the major product. Para amino benzene sulfonic acid, commonly known as sulfanilic acid. Sulfanilic acid is the major product. Sulfanilic acid is the major product. That means sulfonation will take place at para position of, I mean, say this, and this will be the major product. Now, after that, it will lose H positive and it will abstract that H positive, so its Zwitter ion can be obtained like this. NH3 positive, and this will become SO3 negative. So this is the Zwitter ion or dipolar ion of para-amino benzene sulfonic acid or sulfanilic acid. So this is the Zwitter ion of that. After that, there will be Hinsberg's method. What is Hinsberg's method? Now listen, this is method with the help of which we can distinguish 1 degree, 2 degree and 3 degree amines. With the help of this method, with the help of this test, we can distinguish primary, secondary and tertiary amines. Have a look. We have benzene sulfonyl chloride, and this benzene sulfonyl chloride is considered as Hinsberg's reagent. Benzene sulfonyl chloride is considered as Hinsberg's reagent. Benzene sulfonyl chloride is considered as Hinsberg's reagent. Now, when this is treated with primary amine, so can I write down primary amine like this? So it will result in the formation of a solid, and that solid is actually like this. That solid is like this: S double bond O, N, H and R. This is N-alkyl, this is N-alkyl benzene sulfonamide. This is the solid named as N-alkyl benzene sulfonamide. Now, if secondary amine reacts with, I mean, say benzene sulfonyl chloride or Hinsberg's reagent, it will result in the formation of NN dialkyl benzene sulfonamide. It will result in the formation of NN dialkyl benzene sulfonamide. Benzene sulfonamide. NN dialkyl benzene sulfonamide. And there will be no reaction with tertiary amine, as it does not have any acidic hydrogen. So no reaction. So with the help of this, there will be no reaction, but these two will be the solids. But this is having acidic hydrogen, active hydrogen. This does not have any active hydrogen. That means when it is treated with alkali, say for example aqueous potassium hydroxide, when it is treated with alkali, here no reaction will take place. But here OH will replace this H, OH will remove this H in the form of water, and we will get a product like this. It is S double bond O, then it is Nr having negative charge on nitrogen and K positive. I mean to say this solid is soluble. It is soluble in alkali. So the solid which is soluble in alkali is the solid of primary amine, is the solid obtained from primary amine, because this is the primary amine and this is the secondary amine. Solid obtained from secondary amine is insoluble in alkali. It is insoluble in alkali. Remember this. And this is tertiary amine. It will not react at all. So with the help of this test, we can distinguish, primary, secondary and tertiary amines. After that, methods of preparation of diazonium salts is diazotization. Have a look. This is aromatic primary amine. Diazotization reaction is this one. Aromatic primary amine, for example this. On treatment with NaNO2 and acid, say for example HA, Or we can say it is HNO2 in presence of excess of H acid, say for example HA. At a temperature of 0 to 5 degrees Celsius, we will get benzene diazonium salt, for example like this. We will get benzene diazonium salt like this. Now the question is, what is this HA? This HA can be HCl, it can be HNO3, it can be H2SO4, but I will write down HOSO3H so that you will get that this is A, this is A, this is A, or it can be HBF4, that means BF4 is A. So if it is HCl, then it is Cl minus. If it is HNO3, then this is NO3 minus. If it is H2SO4, then this is OSO3H minus. If this is HBF4, then this is BF4 minus. So this reaction is known as diazotization reaction. After that, there are chemical reaction of benzene diazonium salts in which reactions involve displacement of nitrogen. Have a look. That means if you are having a reaction like this, say for example you are having benzene diazonium chloride. When this benzene diazonium chloride is treated with, listen carefully, when it is treated with H3PO2 and water or ethanol, these reagents will replace N2 by hydrogen. That means here product will be benzene and N2 gas will be evolved. Remember, this N2 will be replaced by hydrogen by these reagents. Similarly, if you treat it with water and warm it, warm means above 5 degrees Celsius. After that, this N2 will be replaced by OH group. N2 will be replaced by OH group. I hope this is clear. N2 will be replaced by OH group. That means N2 will be replaced. That means there will be evolution of amines and nitrogen gas. Similarly, if you treat it with Cu2X2 HX, or you will write CuXHX, I mean say cuprous halide. Listen carefully. At that time we will get haloarene, but here X is either Cl or Br. Similarly, if you treat it with CuCN-KCN, then we will get benzonitrile. That means here nitrogen is replaced by halogen, that means chlorine or bromine. Here nitrogen is replaced by cyanide. This type of reaction in which nitrogen of benzene diazonium salt is replaced by chlorine or bromine or cyanide by using cuprous halide and cuprous cyanide. Remember, cuprous, Cu positive. This type of reaction is known as Sandmeyer reaction. Sandmeyer's reaction. And if CuHX is used where X is Cl or Br, or we use copper and KCN, not cuprous, copper is used, not Cu positive, copper is used, then we will get haloarene and nitrogen gas will be evolved. Here we will get benzonitrile and nitrogen gas will be evolved. But this type of reaction is known as Gattermann's reaction. That means we can obtain chlorobenzene, bromobenzene or benzonitrile from Sandmeyer reaction. We can obtain chlorobenzene, bromobenzene and what we call benzonitrile by Gattermann reaction. But yield of these products in Gattermann is less and in Sandmeyer reaction yield is always more. Now, only difference is in case of Sandmeyer reaction we use Cu positive and in case of Gattermann we use copper. After that, listen carefully. If you use aqueous potassium iodide and warm, then this N2 will be replaced by iodine. N2 will be replaced by iodine. Listen carefully. And if you use Na3ASO3, then N2 will be replaced by ASO3Na2 first. N2 will be replaced by ASO3Na2 first. After that, If it is treated with dilute HCl, then this Na2 will be lost in the form of twice NaCl, and finally we will replace this N2 by AsO3H2 group. This is known as arsenic acid group. AsO3H2 is known as arsenic acid group, and reaction from this to this, reaction is known as, from this to this, reaction is known as Barth reaction. Reaction is known as Barth reaction. Similarly, if we treat it with, say for example, aromatic compound in presence of NaOH, then what will happen? That N2 will be replaced by aryl, N2 will be replaced by aryl, and this reaction is known as Gomberg-Bachmann reaction. This is known as Gomberg-Bachmann reaction. Similarly, if it is treated with HBF4, we will get benzene diazonium tetrafluoroborate first. Benzene diazonium tetrafluoroborate first. Let me write down once again, N triple bond N, BF4 having a negative charge on boron, then positive charge on nitrogen. Now this, on treatment with NaNO2, sodium nitrite, we will get nitrobenzene. That means nitrogen is replaced by NO2 group. And if we heat this reaction, if we heat this compound, we will get fluorobenzene. That means nitro group here is replaced by fluorine. And this reaction is known as Bals-Schimmann reaction. In nutshell, we can replace nitrogen by hydrogen. We can replace nitrogen by a hydroxyl group. We can replace nitrogen by chlorine or bromine. We can replace, this reaction by iodine, by fluorine. We can replace this by cyanide. We can replace this by AsO3H2, that means arsenic acid group. We can replace this by, this aryl group, that is known as Gomberg-Bachmann reaction. So we can replace this N2 by different univalent species. Similarly, there are few reactions in which nitrogen group is retained. For example, if you are having this reaction, and if you want to reduce it with the help of SnCl2HCl, or you treat it with Na2SO3, then it will result in the formation of N-phenylhydrazine. N-phenylhydrazine like this. But listen carefully, if, however, vigorous reducing agent like zinc HCl is used, then what will happen? Have a look. This benzene diazonium salt is then, first of all, when it is treated with vigorous or a strong reducing agent as compared to this, it will first form N-phenylaniline, but it will not stop over here. It will further react. With this, and it will result in the formation of aniline and ammonium chloride. Because first it will result in the formation of ammonia, which reacts with this HCl and will result in the formation of ammonium chloride. Then another is coupling reaction. Have a look. Listen carefully. If you are having a benzene diazonium salt, for example, you are having benzene diazonium salt like this. This on treatment with aniline, in presence of acidic medium, at pH of 4 to 5, what will happen? What will happen? It is an electrophilic substitution reaction in which this is an electrophile and electrophile goes to para position of aniline. Electrophile is added to para position of aniline like this. It is added to para position of aniline. So we get 4 amino azobenzene. That means this is once again an azodie like that of 4-hydroxyazobenzene. So this is azodie. But the only difference is for hydroxyazobenzene on treatment with phenol, I mean say benzene diazonium salt on treatment with phenol gives 4-hydroxyazobenzene. That is azodie, but that was orange in color. This is yellow in color. That means this is yellow dye as this is yellow in color. And on treatment with phenol or on treatment with aniline, this benzene diazonium salt couples at para position. But if para position is blocked, for example like this, if para position is blocked, for example like this, suppose you are having like this, this is phenol and its para position is blocked by NH2. This is aniline, its para position is blocked by OH group. Then what will happen? Have a look. This on treatment with pH N2Cl. What is this pH N2Cl? Benzene diazonium chloride. Now this N2 group should go to para position of OH, but para is blocked. Now it should go to para position of NH2, but para position of NH2 is also blocked. Now what will happen? Have a look. This is basic medium. Say for example pH is equal to 9 to 10. When basic medium is there, always coupling with phenol takes place. That means this N2 should go to para position of phenol, but para position of phenol is blocked. Hence, it will go to ortho position of OH. I mean say ortho position of phenol. That means it should go to this position. So it is N2PH. So coupling will take place at ortho, but ortho with respect to OH because this is basic medium. But if reaction takes place in acidic medium, that means approximately at a pH of 4 to 5, then what will happen? This is basically the coupling reaction of NH2 group, but it should go. Now it should go to para position of NH2, but NH2 position is blocked. Para position of NH2 is blocked. That's why it will go to ortho position of this. I hope this is clear. So this is all about today's session, my dear lovely students, and I'm really very thankful to all of you for your patience, because your patience is very much important for you to get into GMCs. I hope this is clear to you all. This was all about today's session, and I would want you all guys to comment from which place you are watching today's session after I end this stream. And thank you very much, and God bless you all. My wishes are always for you. My prayers are always for you, and I will be always there for you as well. So God bless you all. Take care and good night, and love you all. Take care. Bye-bye.